Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, doing good. So let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone quickly in the chat. Yes. Welcome back, people. Welcome back. Welcome back. So quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Everyone in the chats. Perfect, guys. Perfect. So, as you all must be knowing, that today we are starting the new chapter, and the name of the chapter is going to be Chemical Kinetics, right? It is one interesting chapter, and it's simple at the same time. It's not that difficult. So, I was reading your chats. Some students were saying, sir, if we have not completed the equilibrium yet, can we join the session? Absolutely, you can join the session, because I'm exactly going to start from the basics only, right? Which I keep on doing always. So this chapter also will be started from the basics, from the scratch, so that you won't be having any issue, any problem in understanding this particular chapter. Yeah? Welcome guys, welcome. Good evening and welcome back. I'm doing good. Thank you so much. Thank you so much. So dear students, one more thing. This chapter, it might take some 2 to 3 sessions to complete, right? Minimum 2 sessions, maximum 3 sessions. Every session will be of the duration approximately 3 hours, right? I'll be covering all the theory as well as all the problem patterns which can be asked from this chapter as far as your NEET, even JEE examination is concerned, right? No, it's not tough chapter, it's easy only. You'll get to know in some time, because I'm going to start from the scratch only, from the basics. So imagine as if you have never studied this chapter before, okay? That's my guarantee. After doing this chapter, you'll be able to solve majority, 99% of the questions you should be able to solve on your own. Right? Perfect, guys. So before starting this particular session, the ones who have not liked the session yet, I would want you guys to like the session. Do share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025, this particular session is for every single one. Right? And at the same time, the ones who have not subscribed to Unacademy NEET English channel yet, I would want you guys to subscribe to the channel right now. Okay? My dear students, this session duration will be approximately 3 hours or even more, right? 3 hours or 3.5 hours. So just let me know before starting whether you guys are ready to be with me till the end of the lecture 1 of kinetics. Let me know once in the chats. Quickly, dear students. Quickly. Vanakkam, Balahari, vanakkam. Nice. So let me know quickly in the chats. Everyone. Are you ready? Perfect. So people, whatever I'll be mentioning on the screen, whatever I'll be writing on the screen, I would want every one of you to take a note of every single thing, because every single thing is going to be very, very important as far as this particular chapter is concerned. Yeah? Right? So take a note of every single thing. Perfect. So let's get going then. Let's get started with the chapter Chemical Kinetics, right? Chemical Kinetics. First of all, let me give you the brief introduction of the chapter Chemical Kinetics. A brief description about the chapter, like what all things we are going to cover in this chapter. My dear students, this particular Chemical Kinetics, it deals with what? Let me tell you, it deals with the rates of the reactions. Number 1. Number 2, it deals with the factors. It deals with the factors affecting the rates of reactions. Factors affecting the rates of reaction. And at the same time, it deals with the mechanism involved in the reaction as well. Okay. So basically, three things we have to discuss in this chapter. Just give me a second. Let me change the pen. Okay. So three things we have to discuss in this particular chapter in detail. So this particular chapter is going to let us know about the rates of the reaction, about the speeds of the reactions. This chapter is going to let us know why some reactions are slow, why some reactions are fast, why some reactions have got the moderate speed, right? This particular chapter is going to let us know the factors on which the rates of the reaction depends and what are the mechanisms involved in a particular reaction. So all those things we have to discuss here in this particular chapter in detail. Perfect. So quick definition of the chapter, chemical kinetics, right? Now, my dear students, before starting the first topic of the chapter, before starting the first topic of the chapter, I would want to write one statement over here. And what is the statement all about? Have a look on the statement which I'm writing over here. The statement is very simple. When the reaction starts, concentration of reactants keeps on decreasing with time, and the concentration of products, it keeps on increasing with time. What this particular statement exactly means, let's try to understand this. Have a look, people. When the reaction starts, the concentration of reactants decreases with time, and the concentration of products, it increases with time. Now, you must be thinking, what is concentration, first of all, right? You must be thinking, what is concentration? Concentration is represented by square brackets. Either square brackets, or you can directly represent it with C. And how do we define it? It is simply defined as number of moles per unit volume. Number of moles per unit volume. Now, what it means exactly? Try to understand. My dear students, for example, you have got the reaction A gives B. Let's assume this is the reaction. A gives B. Imagine that this particular reaction is taking place in a container. This reaction, for example, has to take place in a container whose volume is, let's assume, V liters. Okay. Now, for example, at time t is equal to 0. At time t is equal to 0. Time t is equal to 0 means the reaction has not started yet. That means the reactants have not got converted into products yet. So at time t is equal to 0, in the container, there will be only reactant present because the reaction has not started yet. B has not formed yet, right? Let's imagine that at time t is equal to 0, we have got some 10 moles of A. So therefore, we'll be having some 0 moles of B in the container because the reaction has not started yet. Now, with time, when the reaction will start, when A will start getting converted into B, what will happen to the moles of A? I'll say moles of A will start to decrease. And at the same time, moles of B, it will start to increase. As simple as that. When the reaction starts, moles of reactants will keep on decreasing and moles of products, that will keep on increasing, right? My dear students, if I define the term concentration of reactant, what is concentration of reactant? Concentration of reactant is going to be number of moles of reactants divided by volume of system in liters, right? If I define the concentration of products, it's going to be number of moles of products divided by volume of system in liters, right? Now you tell me one thing. As the reaction starts, number of moles of reactants, that decrease with time. Now you tell me, if number of moles of reactants decrease with time, can I say concentration of reactant will decrease with time? Absolutely. Concentration of reactant is going to decrease with time. In the similar way, as the reaction starts, number of moles of products, that increases with time. And if the moles of product increases with time, what happens to the concentration of product? Concentration of product also increases with time, right? So as I told you, as the reaction starts, the concentration of reactant keeps on decreasing with time, and concentration of product, it will keep on increasing with time, right? And at the same time, if you want to have a look over the same statement graphically, you can do that as well. For example, I'm making a graph between concentration versus time. I'm going to make two graphs. between concentration versus time. One is going to be for reactants and one is going to be for products. For reactants, we know with time the concentration of reactant decreases. So concentration versus time. As the time passes by, the concentration of reactant is going to decrease with time, right? Similarly, as the time passes by, the concentration of product is going to increase with time. So this particular graph, it is valid for reactants, and this particular curve, it is valid for products. Let me know first of all in the chats if you got to know this particular concept. Quickly in the chats. Sir, voice is not clear. Can you just let me know in the chats if you all can properly hear me? Let me just check it out. Similarly, as the reaction starts, number of moles of products that increases with time. And if the moles of product increases with time, what happens to the concentration of product? Concentration of product so in time. It's absolutely clear, right? Looks like the RJ's voice. Yeah. Okay, is this particular statement clear? As the reaction proceeds, the concentration of reactant will keep on decreasing and concentration of product will keep on increasing. Yeah. Perfect. And these are the two graphs which I would want all of you to remember from now onwards. I hope this particular thing is clear to everyone. My dear students, there is one more thing. There is one more thing which I want to share with you. And what is that particular thing? Let's have a look. Understand. I told you I'll be starting from exactly basics. I don't want you guys to have any confusion in between. Try to understand what I'm going to say. Let's say the state of this A is gas. The state of this B is also gas. Right? Let's say A is in gaseous phase. B is also in gaseous phase. Can you let me know at time t is equal to 0? At time t is equal to 0. How many gases will be there in the container? At time t is equal to 0, there is only A present in the container. There are 10 moles of A in the container. So I can say, initially there is only one gas in the container. Initially there is one gas in the container. Right? Now, as the reaction proceeds, the number of moles of A will start to decrease. The number of moles of products will start to increase. Right? Right? Now people, if I ask you, if the moles of A are decreasing with time, that means particles of A are decreasing with time, right? So pressure due to A is decreasing with time, yeah? And pressure due to B, that's increasing with time. So if I ask you to plot a graph between pressure versus time, for the reactants, what this curve will look like? Since the moles of reactants are decreasing with time, therefore, the pressure due to reactant, that will also decrease with time. Right? That will also decrease with time. Similarly, if I ask you to make the same graph for the products, pressure versus time. You know, as the reaction proceeds, the moles of product increase with time, hence pressure due to product, that will increase with time too. Right? This graph is particularly valid for products. Yeah? As simple as that. Whether you want to make the graph between concentration versus time, or pressure versus time, or moles versus time, the nature of the graph will be the same. The nature of the graph will be the same, right? If you are making moles versus time, the nature of the curve will be absolutely the same. So this was the first point which I wanted to share with you, right? Let's have a look on one more thing. Right? This was, my dear students, the first point. Now, let's go into our first topic. Let's try to see the first topic which we are going to cover. I'm starting with a topic that is average rate of reaction. R average. If you ask me, how do we define this R average? How do we define this R average? How do we define the average rate of reaction? Let's try to write its definition. Then I'll make you understand what it exactly means. Try to understand things. Average rate of reaction is defined as it is defined as the change in the concentration of either reactants or products. Change in the concentration of either reactants or products in a given time interval. In a given time interval. In a given time interval. This is one of the definition of the average rate, right? Well, there are many ways to define average rate. Right now, I'm defining it with respect to concentration. I can define it with respect to pressure, with respect to moles, etc. But this is something which I want you guys to remember. Average rate of reaction, it's defined as the change in the concentration of either reactant or product in a given time interval. Since we have seen that the concentration of reactant decrease with time and the concentration of product increase with time, right? Yeah? Right, people? Someone is asking about something. Let me tell you, these are not one shots which are completed in 1 hour. These are detailed marathons, right? Okay, these are detailed marathons. Every single topic is discussed here. Okay? So someone has come here to take something. So please, you shut your mouth and let others concentrate, yeah? I hope you got it. Okay. So average rate of reaction, it is defined as the change in the concentration of either reactants or products in a given interval of time. Let's try to understand. Let's try to understand what exactly I'm saying. My dear students, before making you understand this particular statement, I'm going to write it in the mathematical formulation. Average rate of reaction, it is equal to change in the concentration, delta C, change in the concentration of either reactant or product divided by time interval delta T. Now, in the beginning, I'm going to use a sign, plus and minus. What is the significance of this plus and minus? You'll get its idea in just few minutes, right? In just few minutes. Try to understand what exactly I'm saying now. See, for example, you have got a reaction A gives B. Let's say you have got a reaction A gives B, for example. Okay. My dear students, let's assume that at time T is equal to 0. The concentration of reactant, for example, is C1. The concentration of product will be 0 because the reaction has not started yet. Okay. Now what is going to happen with time? As the reaction will start, the concentration of reactant will keep on decreasing with time. So, for example, at time T2, the concentration of reactant left is, for example, C2. And the concentration of product formed, that is C3. So, first of all, be careful with the terms which I'm telling. C1 is the initial concentration of reactant at time T is equal to 0. This is the concentration of product at time T is equal to 0. Now, at time T2, let's assume that the concentration of reactant left is C2 and the concentration of product formed is C3. Now, you tell me just one thing. Already we have discussed that as the reaction proceeds, the concentration of reactant that decreases with time. So tell me whether C2 is greater than C1 or C2 is less than C1. I would say C2 will be less than C1, right? Absolutely, C2 will be less than C1 because we know the concentration of reactant that decreases with time. Perfect. My dear students, if I choose this particular time interval, I'm choosing this particular time interval, right? In this particular time interval, the concentration of reactant changes from C1 to C2 and the concentration of product, it changes from 0 to C3. Now, average rate of reaction in this particular time interval, the average rate of reaction in this particular time interval can be defined either with respect to reactant or can be defined with respect to product. For example, I'm defining average rate of reaction with respect to reactant. What I'll be writing? I'll be writing change in the concentration of reactant. Change in the concentration of reactant, which will be final concentration of reactant minus initial concentration. Final concentration of reactant minus initial concentration of reactant divided by time interval. And the time interval here is T2 minus T1. Simple. Time interval here is T2 minus T1. As simple as that. Right? Now you tell me one thing. I have already told you that C2 is less than C1. My dear students, if C2 is less than C1, the difference between these two, will it come out to be positive or negative? I would say C2 minus C1, it will come out to be negative for sure, right? But have you ever heard that rate comes out to be negative? What is rate? Speed. Is the speed negative? Speed cannot be negative. Rate cannot be negative, right? But here it's coming out to be negative. So in order to make it positive, I'll be starting with the minus sign. So that the minus which we get from here, that minus and this minus, finally it makes it positive. Perfect. So this is how you write the average rate of reaction with respect to what? With respect to reactants. Perfect. Now, if I ask you, what about the average rate of reaction with respect to products? With respect to products. In the same time interval, you can calculate the average rate of reaction, but with respect to products, yeah, it's going to be change in the concentration of products, which is final concentration of product minus initial. Final is C3, initial is 0, divided by time interval is T2 minus T1. Time interval is T2 minus T1. And this value, automatically, it will come out to be positive only. So is there any need to multiply with minus? No, there is no need to multiply with minus. Instead, you can write plus here. Okay? Right? I hope this is again super clear to everyone. So my dear students, just try to understand one thing. Average rate of reaction can be defined either with respect to reactants or with respect to products. You just have to do one thing. Change in the concentration of reactants divided by time interval, or change in the concentration of products divided by time interval. That's it. Okay, that's it. Now, people, one more thing. What is the significance of this negative sign and what is the significance of this positive sign? This negative sign, first of all, signifies, this particular negative sign, it signifies that we are measuring the rate of reaction with respect to reactants. This negative sign, first of all, signifies that we are measuring the rate of reaction with respect to reactants. Yeah? Okay? And at the same time, the same negative sign signifies that the concentration of reactants decrease with time. The same negative sign signifies that the concentration of reactant decrease with time. In the similar way, this positive sign over here, it first of all signifies that we are calculating rate of reaction with respect to what? With respect to products. And this positive sign also signifies that the concentration of product, it increases with time. So I hope you got to know why I mentioned positive and negative here, right? That means whenever you want to calculate the average rate of reaction with respect to reactants, you'll be starting with a minus sign. Whenever you'll be calculating the average rate of reaction with respect to products, you'll be starting with the positive sign. As simple as that. And why negative, why positive? You already know it now. Because the rate of reaction can never be negative. We always have to make it positive. Yeah? Perfect. Let's try to understand the same scenario in the form of a graph so that you get its actual feeling. Try to understand what exactly I'm going to say. Try to understand what exactly I am going to say. See guys, have a look now. I'm going to make you understand by graphical representation. For example, the reaction is again A gives B. Imagine at time T1, the concentration of reactant is C1, for example. The concentration of reactant at time T2, that's for example C2. At time T1, the concentration of reactant is C1. At time T2, the concentration of reactant is C2. At time T1, let's assume that the concentration of product is C3. And at time T2, let's assume that the concentration of product is C4. We already know the concentration of reactant decreases with time. The concentration of product, it increases with time. So can I say C2 value will be less than C1, first of all, and at the same time, C4 value will be greater than C3. This is something which is understood. Now, my dear students, in this particular time interval, which is T2 minus T1, in this particular time interval, I want to define the average rate of reaction. First of all, average rate of reaction can be defined either in terms of reactants or you can define it in terms of products. If you are defining the average rate of reaction with respect to reactants, you'll be starting with the minus sign. Then change in the concentration of reactant. Final concentration of reactant minus initial concentration. divided by time interval, which is T2 minus T1, right? Average rate of reaction in the same time interval with respect to products, which is going to be, start with the plus side, final concentration of product minus initial concentration of product divided by time interval, which is T2 minus T1, correct? This is something which we have discussed. Now, for example, the same thing I'm going to draw in the form of a graph. Same thing I'm going to draw in the form of graph. For example, I'm making a curve between concentration versus time for reactants. You know, as the time proceeds, the concentration of reactant decreases with time. For example, the concentration of reactant, we know it decreases with time. I'm selecting this particular point. Let's say this particular point represents T1. Let's assume this particular point, it represents T2. It represents T1, this represents T2. So if I ask you, what about this particular interval? What about this particular interval? This interval is going to be simply T2 minus T1. This particular interval is going to be T2 minus T1. Now, my dear students, whether this graph is for reactant or product, it's absolutely for reactant. Now tell me, at time T1, what will be the concentration of reactant? At time T1, the concentration of reactant is C1. At time T2, the concentration of reactant is, the concentration of reactant is C2. Perfect. Right? Now, from this particular graph, if you want to calculate the average rate of reaction, you can do that. Average rate of reaction. Are you calculating with respect to reactant? Yes, you are calculating with respect to reactant, which will be equal to minus times final concentration, that is C2, minus initial concentration, that is C1. So minus times C2 minus C1. And the time interval is T2 minus T1. Perfect. Right? And at the same time, my dear students, for example, I'm going to do the same thing with respect to products. Concentration versus time. When it comes to products, we know concentration of product increases with time. Now, I'm again going to mark 2 points. This is T1, for example. This is T2, right? So at T1, what is the concentration of product? At T1, the concentration of product is C3. And at the same time, at time T2, what is the concentration of product? At time T2, the concentration of product is C4. Now, if you want to calculate the average rate of reaction in this particular time interval, this particular time interval is T2 minus T1. If you want to calculate average rate of reaction in this particular time interval, how you are going to calculate it? You'll be starting with the positive sign. Then, change in the concentration of product. Final concentration of product minus initial. This is final concentration and this is initial concentration of product. So, final C4 minus initial, that is C3, divided by time interval, that's T2 minus T1. Yeah? Perfect. Right, my dear students? Sir, do you remember Shimon Joseph? Absolutely, I do remember. He's a very good friend of mine. Yeah? He's a very good friend of mine. We have started the teaching journey together from Chennai. Perfect, people. Is every single thing clear till here? Is every single thing clear till here? Yeah? So I hope you got the concept of average rate of reaction. So finally, I would want you guys to remember one thing. Average rate of reaction, you can define either with respect to reactant or with respect to product. When you are defining it with respect to reactant, you'll start with a minus sign. Then, change in the concentration of reactant divided by time interval. Average rate of reaction with respect to product, you'll start with a plus sign. Change in the concentration of product divided by time interval. That's all. Nothing else. Its application part you will see in a while. But before talking about its application, there is one more thing that I would want all of you to know right now. What is that? That is instantaneous rate of reaction. Now, my dear students, how do you exactly define the instantaneous rate of reaction? How do you exactly define it? What about its definition? Let me tell you, instantaneous rate of reaction. It is defined as similar thing. The change in the concentration of either reactants or products in a very small time interval. In a very small time interval. And I'm mentioning as delta T approaching towards zero. Delta T approaching towards zero. Okay, tell me just one thing. How do you write the average speed? Average speed I'm talking about. Average speed in physics. How do you write it? You write it like this. Delta X divided by delta T. Right? Delta X divided by delta T. It represents your average speed. Perfect. It represents your average speed. Right? How do you write instantaneous speed? How do you write instantaneous speed? What you exactly do, you use the limit. Limit. Delta T approaching towards zero. Then you write delta X divided by delta T. And this is something which you represent with dx divided by dt. And this dx upon dt is something which you call as instantaneous speed. I hope you know it. I hope you know it, right? I hope you know it. Now, my dear students, in the similar way, the way you convert average speed into instantaneous speed, in the similar way, you can convert average rate of reaction into instantaneous rate of reaction. How do you represent average rate of reaction? Average rate of reaction you are going to represent like this. Change in the concentration divided by time interval. Now, if I ask you, how do we represent instantaneous rate of reaction? What you exactly do? You'll be using the limit. Limit delta T approaching towards zero. It's going to be delta C divided by delta T. Right? And this whole term, finally, you are going to represent like this. dC upon dt. dC upon dt. Perfect. dC upon dt, what kind of idea it's going to give me? dC upon dt, what kind of idea it's going to give me? Let me tell you, it gives me the slope of the tangent. It gives me the slope of the tangent at a point on concentration versus time curve. On concentration versus time curve. On concentration versus time curve. Let's try to understand this particular thing. Let's try to understand this particular scenario. Have a look, people. Have a look. For example, I'm going to make a graph. I'm going to make a graph between concentration versus time. For example, I'm making it for reactants. Or let me make it for products. Right? We know with time, the concentration of product increases. Right? We know the concentration of product increases with time. So this particular graph, it is valid for products. It's valid for products. Now, my dear students, if I choose a very, very, very small time interval, if I choose a very, very, very small time interval, that means, am I trying to define average rate or instantaneous rate? I'm trying to define the instantaneous rate. Yeah? Okay. So basically, I'm choosing a very small time interval, right? Very small time interval. For example, from here to here, very small time interval, right? My dear students, very small time interval I'm choosing. If I'm choosing a very small time interval, it looks like a point to me. Even this particular, it looks like a concentration to me, right? It looks like a point to me as well. I'm choosing a very small time interval. Now, in this very small time interval, I'm asking you to calculate the instantaneous rate of reaction. How do you calculate the instantaneous rate of reaction? Slope of the tangent at a point on concentration versus time curve. This is concentration versus time curve, right? This is concentration versus time curve. Now, at this particular point, what you'll be doing? You'll be drawing a tangent. At this particular point, you'll be drawing a tangent. You will be drawing a tangent since you have drawn a tangent, right? Slope of the tangent. How do you calculate the slope of the tangent? Slope of the tangent is going to be nothing. That's going to be tan of theta. Tan of theta. What is theta? Theta is the angle which this tangent makes with the positive x-axis in the anti-clockwise direction. So this is theta. This is your theta. Once you get theta, you can take the tan value. Tan of theta is going to give you what? Tan of theta is going to give you instantaneous rate of reaction. And my dear students, try to understand one more thing. Whether theta is acute or obtuse, the theta which we are forming here, it's acute. And tan of acute angle is always positive. Right? Tan of acute angle will be positive. Right? What does that mean? What does that mean? That means the instantaneous rate is directly coming out to be positive. So that indicates you have calculated the instantaneous rate of reaction with respect to products. Absolutely, you have measured it with respect to products, right? Yeah. Right, people? SRP, can you just leave the chats? Right? It's my complete discretion. Where do I want to teach? None of your business. If you want to study, just study here or leave. Or I have the option of blocking you as well. Yeah? I hope you get it. Okay. So my dear students, try to understand it in a different way now. Try to understand it in a different way now. For example, I'm making one more graph, which is again concentration versus time. Right? Which is again concentration versus time. Now, my dear students, if I make the graph for reactants, you know, the concentration of reactant that decreases with time. So this is how the curve will look like. This is how the curve will look like. Perfect. Now, for example, imagine I'm choosing a very, very, very small time interval from here to here. From here to here. Very, very, very small time interval. And I want to calculate the instantaneous rate of reaction in this very, very, very small time interval. I want to calculate the instantaneous rate of reaction in this very small time interval. How exactly I'm going to do it? How exactly I'm going to do it? Slope of the tangent at a point on concentration versus time curve. My dear students, at this particular point, I'm going to draw a tangent. This is the tangent, right? I'm going to measure the angle with which the tangent makes with the positive x-axis in the anti-clockwise direction. So this is theta. Once I get theta, I'm going to calculate tan of theta. I'm going to calculate tan of theta, right? I am going to calculate tan of theta. But is the theta acute or obtuse? The theta is obtuse. Or tan of obtuse will be negative, right? So tan of theta will be coming out to be negative. What does that signify you? What does that tell you? That means you have calculated the instantaneous rate with respect to reactants or products. Absolutely with respect to reactants, right? Perfect. So in short, let me tell you one simple thing which you are going to remember from now onwards. Instantaneous rate of reaction with respect to products will come out to be positive because theta comes out to be acute. Theta is acute. Tan of theta is always positive. So it's plus tan theta. It's always plus tan theta. Instantaneous rate of reaction with respect to products. But if I ask you, what about instantaneous rate of reaction with respect to reactants? Right? Is it going to be tan theta or minus tan theta? It is going to be minus tan theta. Why? Because if you only write tan theta, if theta is obtuse in case of reactants, then tan theta will be negative. But rate cannot be negative. So in order to make it positive, I'll be multiplying with minus sign over here. Right? Perfect, people? Yeah? Is this clear to everyone? So these are two more important things which I would want you guys to take a note of from now onwards. So I hope you got to know the difference between average rate and instantaneous rate. Average rate, the time interval is big. Instantaneous rate, the time interval is very, very, very small. Delta T approach towards zero. Yeah? Whenever you want to calculate either average or instantaneous rate with respect to reactant, you'll be starting with minus sign. Average or instantaneous rate with respect to product, you'll be starting with the positive sign. Right? And all the things are in front of you. Its application part, we'll see in a while. Yeah? Okay, guys? Is it clear to everyone quickly? Is it clear to everyone? Perfectly done. Now, dear students, I'm going to mention a topic that is the rate of reaction as per stoichiometry. rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. Try to understand few new terminologies now. For example, I have got a balanced chemical equation as N1A plus N2B. For example, it gives N3C plus N4D. This is a balanced chemical equation in which N1, N2, N3, N4. These are the stoichiometric coefficients of reactants and products, respectively. Now, people, we know reactants, they disappear with time. Reactants are consumed with time, right? So reactants, they disappear with time. What about products? Products, they get formed with time. They appear with time, right? So, if I mention a term rate of disappearance, the rate with which reactants disappear. The rate with which reactants disappear. I'm using the term rate of disappearance. Disappearance is the term which is used for reactants because reactants, they keep on disappearing with time, right? Because their amount keeps on decreasing with time. So reactants keeps on disappearing with time. So rate of disappearance, for example, of A, how do I write it mathematically? Whenever you have to mention the rate of disappearance, you'll be starting with a minus sign. Right? This minus sign indicates that this A, its amount, its concentration decreases with time. Yeah? So you'll be starting with a minus sign. Then, since you are writing rate of disappearance of A, so starting with a minus sign, then you'll be writing change in the concentration of A divided by time interval. Right? Perfect. This is something which I call as average rate of disappearance of A. If you want to write it in the instantaneous form, you can write it as minus d of A divided by dt. This particular term, it represents average. This particular term, it represents instantaneous. That is the difference, nothing else. For example, if I want to write the rate of disappearance of B, B is one more reactant. Rate of disappearance, I'll be starting with the minus sign. Right? I'm starting with the minus sign. Now, it's going to be change in the concentration of B divided by time interval. Perfect. This is how you represent, how you write the rate of disappearance of B. Now, my dear students, should I use the term rate of disappearance for C, or I'll be using the term rate of appearance? Either you write rate of appearance or you write rate of formation. Rate of appearance or rate of formation of what? Of C. It is going to be equal. Since you are writing rate of formation, rate of appearance, you'll be starting with a positive sign. And then it's going to be change in the concentration of C divided by time interval. Right? And in the similar way, if you want to write rate of appearance or formation of D, you'll be starting with a positive sign, change in the concentration of D divided by time interval. This is how you write rate of disappearances and appearances. Okay? This is how you write rate of disappearances and appearances. I hope it is super clear to everyone. Yeah? Right? Now, my dear students, remember one more thing. If I talk about the rate of reaction, till now I was talking in terms of rate of appearance or rate of disappearance of product reactant respectively. Now, what about rate of reaction? My dear students, in a particular time interval, every reaction has got a particular rate of reaction value. In a particular time interval, every reaction has got a fixed rate of reaction value. And rate of reaction, rate of a particular reaction, since it's fixed, no doubt it's fixed, it's constant. In a particular time interval, it's fixed, right? Now, rate of reaction, how do we calculate the actual rate of the reaction? Till now, I told you how to write the rate of disappearance, rate of appearance. Now, I'm going to show you how to write the actual rate of the reaction. Actual rate of reaction is written as rate of disappearance or appearance of reactant or product divided by stoichiometric coefficient of reactant or product. For example, Let's say you are trying to calculate rate of reaction. You are trying to calculate rate of reaction. You want to calculate rate of reaction with respect to A. You want to calculate rate of reaction with respect to A. In the numerator, you'll be using rate of disappearance of A because A is a reactant which disappears with time. Yeah. So rate of reaction with respect to A, it's going to be rate of disappearance of A. How do you mention rate of disappearance of A? You start with minus, then you write change in the concentration of A divided by time interval, right? Whole divided by stoichiometry coefficient of A, which is N1. Absolutely, right? Now, my dear students, finally, I can write it like this. Minus 1 divided by N1, change in the concentration of A divided by time interval, that's delta T. This particular term is something which you call as the rate of reaction. This particular term is going to give you the actual rate of reaction in the time interval delta T. Well, you can calculate rate of reaction with respect to B as well. You can calculate rate of reaction in the same time interval with respect to B as well. B is again the reactant. So again, you'll be starting with the minus sign. Now you'll write 1 divided by stoichiometric coefficient, that's N2. And over here, you'll write change in the concentration. You'll write change in the concentration of B divided by time interval, that's delta T. So this particular term is also going to give you the rate of reaction only. Since the time interval is same, so whatever rate of reaction you will be getting after solving this particular term, same is the value of rate of reaction which you get after solving this particular term, because rate of reaction is always fixed. It's always constant at a particular temperature. Yeah. Similarly, rate of reaction with respect to C. C is the product. So should I use rate of disappearance or rate of appearance? I'll use the term rate of appearance. Rate of appearance of what? Rate of appearance of C. So I'll be starting with plus 1 divided by stoichiometric coefficient of C, that's N3. Change in the concentration of C divided by time interval. Perfect. Now again, rate of reaction with respect to D, plus 1 divided by N4. Change in the concentration of D divided by time interval. Now, my dear students, in all these terms, first, second, third, and fourth, in all these terms, have a look, time interval is same. If the time interval is same, that means whatever rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, because at a particular temperature, rate of reaction always has a fixed value, right? Let me know in the charts if it is super clear to you. Quickly. Let me just give you the quick summary of what I said. I'm taking a balanced chemical equation N1A plus N2B. It gives N3C plus N4D. My dear students, first of all, rate of reaction I can calculate with respect to A, as well as B, as well as C, as well as D. If I'm calculating rate of reaction with respect to A, I'll be starting with minus sign. 1 divided by stoichiometric coefficient, that's N1. Change in the concentration of A. Divided by time interval, that's delta T. You can calculate the same rate of reaction with respect to B. B is again the reactant, so minus 1 by stoichiometric coefficient. Change in the concentration of B divided by time interval. Similarly, with respect to C, it's going to be plus 1 divided by. What's happening with this pen? It's going to be plus 1 divided by N3. Change in the concentration of C divided by time interval. Similarly, with respect to D, it's going to be plus 1 divided by N4. Change in the concentration of D divided by time interval delta T. Right? And this particular equation which you wrote, this is something which you call as differential form of rate. Okay, differential form of rate. So you take any term, right? Take any term, solve it, you'll be getting the rate of the reaction. That's it. Right, people? Is this clear to everyone quickly? Is this clear to everyone? Quickly. Let me know once in the chats, everyone, if every single thing is clear till here. Perfect. Okay, one more thing. If I write rate of disappearance, if I write rate of disappearance of A, how am I going to write it? Whenever we will write the rate of disappearance or rate of appearance, we are not supposed to divide with the stoichiometric coefficient. Whenever you want to write rate of appearance or disappearance, you are not supposed to divide with the stoichiometric coefficient. But when you want to write the rate of reaction, at that point of time, you have to divide with the stoichiometric coefficient. Yeah? Now people, rate of disappearance of A. How? Start with minus sign, which represents disappearance. Change in the concentration of A, divide by time interval. Do not divide with the stoichiometric coefficient. This is going to give you the rate of disappearance of A. Similarly, the rate of appearance. The rate of appearance of C. How you are going to write it? Appearance you are writing. So start with plus. Change in the concentration of C, divide by time interval. This particular term is going to give you rate of appearance of C. As simple as that. Right? Perfect. Now people, tell me the answer of this particular question. Tell me the answer of this particular question. One simple question. And you cannot believe it was asked in your NEET examination 2 years back. The reaction was like this. N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. We were supposed to write the differential form for this particular equation. Can't you write? Can't you write differential form of rate? Absolutely, you can do that. Rate of reaction with respect to N2. N2 is the reactant. So start with minus. 1 divided by. Stoichiometric coefficient is 1. So it's going to be change in the concentration of N2 divided by time interval. That's delta T. Now in terms of H2, start with again minus. 1 by stoichiometric coefficient. It's going to be change in the concentration of H2 divided by what? Divided by time interval. That's same delta T. With respect to NH3, start with a plus sign because NH3 is the product. 1 divided by stoichiometric coefficient. Change in the concentration of NH3 divided by time interval. That's delta T. Right? Perfect. Okay. This was like 2 years back. The same question was asked in your NEET examination. Okay. Now comes a point. Now comes a point. Try to understand what the point is. For a homogeneous gaseous phase reaction. Gaseous phase reaction carried out at temperature T. Rate can be expressed. Rate can be expressed either in terms of, or let me write it like this. Rate can be expressed in terms of pressure as well. What does this mean? What does this mean? Try to understand what it means. My dear students, for example, I'm taking the reaction N1A gas plus N2B gas. It gives N3C gas plus N4D gas. This is your reaction. Okay. Now, first of all, say every reactant and product has got the same state, right? Every reactant product has got the same state. So it is the example of homogeneous reaction. And every reactant product that's in gaseous phase. So I would call this particular reaction as the homogeneous gaseous phase reaction, which is carried out at temperature T. The reaction is carried out at temperature T, right? Now, first of all, as far as your ideal gas equation is concerned, you know PV is equal to nRT. This is something which all must be knowing. Can you write P is equal to N divided by VRT? Absolutely. P is equal to N by VRT. Now, P will be equal to N by V, number of moles per unit volume. We call that as concentration. So P is equal to concentration multiplied by R multiplied by T. So basically for gases, pressure as well as concentration, both the terms are defined. We define pressure for gas as well as we define the concentration for the gas. For gases, pressure as well as concentration, both the terms are defined. Now, rate of reaction can be expressed either in terms of concentration or you can express it in terms of pressure as well. You can express it either in terms of concentration or you can express it in terms of pressure. How exactly? Try to understand. If I write pressure of A, that's going to be equal to concentration of A multiplied by R multiplied by T. Similarly, pressure of B, that's going to be concentration of B multiplied by R multiplied by T. Similarly, pressure of C, concentration of C multiplied by R multiplied by T. Pressure of D, that's going to be equal to concentration of D multiplied by R multiplied by T. As simple as that. Yeah, you know it now. Now, my dear students, if I want to write the differential form of rate, start with A, minus 1 divided by N1. Change in the concentration of A divided by time interval. With respect to B, minus 1 divided by N2. Change in the concentration of B divided by time interval delta T. With respect to C, plus 1 divided by N3. Change in the concentration of C divided by time interval delta T. Plus 1 divided by N4. Change in the concentration of D divided by time interval delta T. Correct? Okay. Now guys, try to understand one thing. Rate of reaction can be written as minus 1 divided by N1. Delta. Concentration of A. So instead of concentration of A, can I write pressure of A divided by RT? Right? Instead of concentration of A, I can write pressure of A divided by RT, whole divided by what? Whole divided by delta T is equal to minus 1 divided by N2. Delta of concentration of B is going to be pressure of B divided by RT, whole divided by delta T is equal to plus 1 divided by N3. Plus 1 divided by N3. Delta of concentration of C is going to be pressure of C divided by RT, whole divided by delta T. Right? Similarly, in terms of D as well. I do not have space here. That's why I'm leaving D aside. Now, guys, I can write it further like this. Since you know, this reaction is carried out at constant temperature. So temperature is constant, R is already constant. So they'll come out of the delta. So it will come out to be like this. Minus 1 divided by N1. Minus 1 divided by N1. RT will be in the denominator. It's going to be change in the pressure of A divided by time interval, which is equal to minus 1 upon N2. RT will come in the denominator. It's going to be change in the pressure of B divided by delta T. Similarly, plus 1 divided by N3. It is going to be change in the pressure of C divided by delta T. Same thing in terms of D as well. So RT everywhere, it will get cancelled out. And when RT gets cancelled out, you get the final expression minus 1 upon N1, change in the pressure of A divided by time interval, which is equal to minus 1 divided by N2, change in the pressure of B divided by time interval. You can write it in terms of C as well. Plus 1 divided by N3, change in the pressure of C divided by time interval. You can write it in terms of D as well. Plus 1 divided by N4, change in the pressure of D divided by time interval. Right? Perfect. That's something which I already told you. For a homogeneous gaseous phase reaction, rate can be expressed either in terms of concentration. It can be expressed either in terms of concentration or it can be expressed in terms of pressure. Now, one thing which you have to remember here. What is that? One thing which I want you guys to remember. Whenever you are using these terms to calculate rate, at that point of time, you are calculating rate in terms of moles liter inverse. Let's assume time is in seconds. So second inverse. If you are using, for example, this particular term to calculate rate, so in the numerator you have got concentration, in the denominator you have got time. Concentration units will be moles per liter. Time units, for example, seconds. So moles per liter per second, right? If you are using this term, or you are using this particular term, or you are using this particular term, or you are using this particular term. So you are calculating basically the rate of reaction in terms of moles per liter per second or moles per liter per minute, whatever, right? But if you are using this particular term to calculate rate, or you are using this particular term to calculate rate, or you are using this particular term, or even you are using this particular term, in the numerator you have got pressure, In the denominator, you've got time, right? So basically, you are calculating rate in terms of, let's say pressure is in ATM. So it's going to be ATM. Let's say time is in seconds. So it's going to be an ATM second inverse or ATM minute inverse, ATM hour inverse, bar minute inverse, bar second inverse. So this is all yours, right? Is every single thing clear till here? Quickly. Quickly, guys. Yeah? Perfectly done. So, whenever you are supposed to calculate rate of reaction in terms of moles per liter per second, take any term out of these terms. Whenever you are supposed to calculate rate of reaction in ATM second inverse, for example, take any term out of these terms and get the rate of the reaction. Now, let's try to utilize all these concepts in the questions. But before solving the questions, let me know everyone in the chats with yes or no, so that I'll get to know whether you got the concept or not. Quickly. Yeah? Let's try to use all these concepts in the questions so that you can understand it properly. The first question which is on your screen. The first question which is on your screen. If the concentration of H2O2 changes from 0.5 molar to 0.05 molar in 15 seconds, then calculate rate of reaction, rate of appearance of O2. Two things we have to calculate. See, these sort of questions frequently you would have seen. Now, first of all, I'm given with a balanced chemical equation. Can I write the differential form of rate? Write with respect to H2O2. Start with minus sign. 1 by stoichiometry coefficient, that's 1. Change in the concentration of H2O2 divided by time interval delta T. In terms of water, water is the product. So start with plus 1 by stoichiometry coefficient. Change in the concentration of H2O divided by time interval, that's delta T. Now, O2, which is the product, start with plus 1 by stoichiometry coefficient. So 1 divided by 1 by 2, which makes it 2. Change in the concentration of O2 divided by time interval delta T. So first I wrote the differential form of rate. Okay. Now, my dear students, try to see what is given to us. The concentration of H2O2 changes from 0.5 molar to 0.05 molar in 15 seconds. So time interval is 15 seconds. Time interval is 15 seconds, right? Let's try to calculate the rate of reaction. Rate of reaction can be either calculated by solving this term or by solving this term or by solving this term. Now, which term I'll take out of the three? The one whose data is given. The data for H2O2 is given. So I'll take the first term and try to solve this. Done and dusted. So it's going to be minus times change in the concentration of H2O2, which is going to be final concentration of H2O2 minus initial concentration of H2O2 divided by time interval is 15 seconds. Now solve it. The answer is going to be in moles, liter inverse, second inverse. This is the rate of reaction. This is the rate of reaction. Yeah. Perfect. Perfect, people. This is the rate of reaction. Okay, number one. First question is done and dusted. What about the second question? Calculate the rate of appearance of O2. First of all, how do I mathematically denote rate of appearance of O2? Rate of appearance of O2. How do I denote it? Rate of appearance of O2. I'll be starting with a positive sign. Whenever I will have to calculate rate of appearance of disappearance, do I need the stoichiometry coefficients? No way, right? It is simply going to be change in the concentration of O2 divided by time interval. This is something which you call as the rate of appearance of O2, which you are supposed to calculate, right? Now, my dear students, in this particular differential form, the data for H2O2 is given. The data for O2 is to be calculated. The data for H2O2 is given and the data for O2 is to be calculated. Just try to equate these two terms. That's it. Just try to equate these two terms. It's going to be minus delta H2O2 divided by delta T is equal to 2 times delta of O2 divided by delta T, right? Now from this particular equation, can I write something like this? I write delta O2 divided by delta T first. Delta O2 divided by delta T is equal to, this 2 will be here in the denominator, so it's going to be minus 1 divided by 2, and you're going to write delta of H2O2 divided by delta T, right? Perfectly done. So this delta O2 divided by delta T, is this something which we call as the rate of appearance of O2? Absolutely. Rate of appearance of O2 will be equal to minus 1 by 2 change in the concentration of H2O2, which is equal to final concentration of H2O2 minus initial concentration of H2O2 divided by time interval, that's 15 seconds. The answer is going to be in moles, later inverse, second inverse. So both equations are done and dusted. Simple. Correct? Correct, guys? Is every single thing clear till here? Just give me a second. Just give me a second, guys. Perfectly clear? All right. So let's try to solve a few more questions. Let's try to solve a few more questions. Look at this particular question. If the rate of appearance of O2 is 0.5, rate of appearance of O2. First of all, in this particular reaction, how do you write the rate of appearance of O2? Rate of appearance of O2 is equal to, I'll be starting with the plus sign, change in the concentration of O2 divided by delta T. This rate of appearance of O2. And this rate of appearance of O2 is given to me as 0.5 moles, later inverse, second inverse, right? Calculate the rate of disappearance of N2O5. How do I represent the rate of disappearance of N2O5? Rate of disappearance, you'll start with minus sign, right? Change in the concentration of N2O5 divided by delta T without dividing by stoichiometry coefficient. This term is called as rate of disappearance of N2O5. Okay? And this particular term, the rate of disappearance of N2O5, we have to calculate this term. Right? We have to calculate this term. Now, my dear students, the reaction which is given to us, it is given to us in balanced format. The reaction is given to us in balanced format. Right? Now, what I'll be doing, just write the differential form of rate. Rate of reaction is equal to, in terms of N2O5, start with minus 1 by stoichiometry coefficient. Change in the concentration of N2O5 divided by delta T. Similarly, with respect to N2O4, start with plus 1 by stoichiometry coefficient. Change in the concentration of N2O4 divided by delta T. Similarly, it's going to be plus 1 by stoichiometry coefficient, that's 1. Change in the concentration of O2 divided by delta T. Correct? So all these terms are going to give me the rate of reaction. All these terms are going to give me the rate of reaction. Okay? Now, which two terms among these three I'm going to take? Which two terms among these three terms I'm going to take? The data for O2 is given. The data for N2O5 is to be calculated. Right? The data for O2 is given. The data for N2O5 is to be calculated. So I'm going to relate these two terms, nothing else. So I'm going to write minus 1 by 2, change in the concentration of N2O5 divided by delta T is equal to plus delta O2 divided by delta T. Right? Now, what exactly? Delta O2 divided by delta T. What do I have to calculate? I have to calculate minus delta N2O5 by delta T. So, take this 2 from here. Take this 2 from here and multiply this term with 2. That's it. I mean, just cross multiply things. Nothing else. Just cross multiply things. The 2 which was here in the denominator, that 2 goes here. This was plus, multiplied with 2. Right? Now, 2 I'm writing as such. Delta O2 by delta T is given, I believe. That's 0.5. So the value comes out to be 1. And it's going to be mole, liter inverse, second inverse. So what is this term? What did we calculate? What did we calculate? We calculate the value of this particular term. And what do we call this particular term as? This is called as the rate of disappearance. This is called as the rate of disappearance. Rate of disappearance of what? Rate of disappearance of N2O5. Right? Is it clear? Is it clear, people, quickly? And this was something which I was supposed to calculate. That's all. Look at this particular question. Look at this particular question. Try to solve this as well. We are given with a reaction. For the following reaction, calculate the rate of reaction in the time interval 5 to 15 seconds. Time interval 5 to 15 seconds. So this is the time interval. This is the time interval, which I'm representing with delta t. So delta t, let's call this as t1. Let's call this as t2. So time interval is t2 minus t1. So 15 minus 5 comes out to be 10 seconds. So in 10-second time interval, we have to calculate the rate. Right? In 10 seconds of time interval, we have to calculate rate. Now, first of all, try to understand. The graph is between concentration versus time. And the concentration is decreasing with time. So this graph has to be for the reactant. Because we know concentration of a reactant decrease with time. And in the reaction, which one is your reactant? It's NH3 which is your reactant. So this graph has to be for NH3. This graph has to be for NH3. What are we supposed to calculate? Calculate the rate of the reaction in this particular time interval. So let me calculate rate of reaction with respect to NH3. NH3 is reactant, so start with minus 1 by stoichiometry coefficient. Change in the concentration of NH3 divided by time interval, that's delta t, right? Now the question is done and dusted. So minus 1 by 2, change in the concentration of NH3. That's going to be final concentration of NH3 minus initial concentration of NH3. Final concentration of NH3 is 0.2. Initial concentration is 0.6 divided by time interval is 10 seconds. Now solve it. Get the value of the rate of reaction. That's all. That's something which we're supposed to calculate. That's it. Nothing else. Isn't it simple, people? Isn't it simple? One more question. One more question. It might look difficult to you, but it's not difficult. Try to understand. For the reaction, there are some parameters which are given. Find the relation between K1, K2, K3. Reaction is also given. How? How you are going to get the relation between K1, K2 and K3? See guys, it's also simple. The reaction which we are given with, just write the differential form of rate with respect to N2O5. Start with minus, right? Change in the concentration of N2O5 divided by time interval. Now here we are not using delta, so I'm not also going to use delta. I'll use D for example. So it's going to be minus D of just a second. What did I do? Okay. All right. Okay. So write the differential form of rate. It's equal. Start with minus because you are going to write with respect to N2O5. So it's D of N2O5 divided by dt, which can be also written as plus 1 divided by stoichiometry coefficient. It is D of NO2 divided by dt, which can be written as plus 1 divided by stoichiometry coefficient, that's 1 by 2. So 1 by 1 by 2 makes it 2, D of O2 divided by dt. This is how you wrote the differential form of rate. This is how you wrote the differential form of rate. Now guys, tell me this minus D of N2O5 by dt, minus D of N2O5 by dt, that's given to me as K1 multiplied by concentration of N2O5, right, is equal. Plus 1 by 2 I'm writing as such. Now plus D of NO2 by dt, plus D of NO2 by dt, that's given to me as K2 multiplied by concentration of N2O5, which is equal to 2 times D of O2 by dt. D of O2 by dt is also given to me. That's K3 multiplied by concentration of N2O5. So all these parameters are basically given to me as the equation, right? So can I say this N2O5 got cancelled out. So the values K1 is equal to K2 divided by 2, which is equal to 2 times K3, right? Now, look at the denominators. 1 to 1. The LCM of denominator will be 2. LCM of denominator will be 2. So, multiply throughout with the denominator. So, this will be 2 times K1. This will be K2. This will be 4 times K3. Right? This is the relationship between K1, K2 and K3 which you were supposed to calculate. Is it clear? Is it clear, people? Quickly, let me know in the chats. Is it clear? Yes? Perfect. Okay, tell me whether this question you can do on your own. It is a similar type of question. Calculate rate of reaction in moles per liter per second and ATM per second. Can you solve this question on your own? Can you solve the question on your own? Yeah? Quickly, quickly. You sure you can watch it? Absolutely. There is no issue. Perfect. Let me give you one more question. Just a second. For example, the question is like this. X times A gives Y times B. X times A gives Y times B. It is given that, just a second. It is given that minus log of dA divided by dt is equal to log of d of B divided by dt plus 0.3 plus 0.3. Find the value of X and Y. Can you give it a try? Can you solve this question? You should be, I believe. You should be able to solve this question. See guys, we are supposed to get the value of X and Y, correct? The reaction that's given to us, that's XA gives YB. Can you write the rate of reaction with respect to A? It's going to be minus 1 divided by X, change in the concentration of A divided by dt. Write the rate of reaction in terms of B. It's going to be plus 1 divided by Y, change in the concentration of B divided by dt. Let me call this as equation number 1. Okay. Look at this particular equation. It is minus times log of d of A divided by dt is equal to. This is log of, or just have a look. Wait, just have a look. See guys, this term is in log, this term is in log, and this term is not in log. Can you make this term in the logarithmic form? Can you write this particular term in the logarithmic form? So instead of 0.3, you can write log of 2. Because you know, log of 2 to the base 10, that's 0.3 only. Log of 2 to the base 10, that's 0.3 only, right? Now it is the log of m plus log of n, which is going to be log of m into n, right? So log of 2 multiplied by d of B divided by dt. Correct? So if I take anti-log on both the sides, it has to be minus d upon A upon dt, which is equal to 2 times d of B divided by dt. Or this 2 you can take here. It's going to be minus 1 upon 2 d of A divided by dt has to be equal to d of B divided by dt. Perfect. Look at this particular equation now. Just compare these two equations. Just compare these two equations. My dear students, when you compare these two equations, you will be getting the value of x as 2 and the value of y as, this will be 1 by 1, right? The value of y you got to know as 1. And these were the things which you are supposed to calculate. I hope this is clear. Yeah? Is it clear? I did nothing. See, this was in logarithmic form. This was in logarithmic form. And over here, it was given as 0.3. 0.3, I converted it in the logarithmic form, right? 0.3 is nothing. That's log 2, basically. Then log of m plus log of n, which is the log of m into n, right? Multiplying both sides by the antilog, taking antilog on both the sides, it'll be log will get cancelled out. It'll be minus d upon dt is equal to 2 times dv upon dt. This 2, I'm taking the denominator. I got this equation. This equation already I had formed. If I compare these two equations, I'll be getting the value of x as 2, the value of y as 1. That's it. Right? Similar type of question I'm giving you, and you are going to write me its answer in the comments. The question is x times a gives y times b. And I'm giving you minus log of d of a divided by dt. Guys, just a second. I think there was one mistake which we did. This is not minus here. Just a second. This is not minus here. It is minus here, basically, okay? It is minus here. Then when you take the antilog, right? Then it becomes minus d upon dt. So do the correction. It was not minus outside. It was minus inside, right? It was minus inside. Okay, it was minus inside. All right. So it's going to be log of minus d of a upon dt is equal to log of d of b upon dt plus 0.6. This was given data. It was given data. We are supposed to get the value of x and y. Right? X and y you are supposed to calculate. Clear? Can you do it? Yes? Will you be able to solve this question? It's simple now. Can you give it a try? Quickly, guys. No, Niranjan, it's not deleted yet. Okay, you have to follow the old syllabus only for NEET as well as JEE. Is it 3 and 1 or 4 and 1? See, 0.6 is log 4 basically. Log 4 is 0.6. Log 4 is 0.6. Okay. So give this question a try, guys. Okay, and let me know its answer in the comments. And I think I'll end the session right here only. Okay, because my head is, I don't know why it's aching. Okay, so what is day after tomorrow? Saturday. So Saturday at 6 p.m. we'll have Kinetics part 2. Okay. Saturday at 6 p.m. we'll have Saturday's day after tomorrow, Kinetics part 2, in which we shall be discussing law of mass action, rate law, order, etc., etc. So this session, now it's going to take 3 sessions, including this one, right? I thought to take this session for like 3-4 hours, but suddenly I am going to end this. Okay. Perfect. But day after tomorrow, on Saturday, we are going to resume from here. Is that cool? Okay, and give this question a try. Do let me know its answer in the comment section afterwards. So my dear students, quickly let me know if all of you can see me, if I am perfectly audible to everyone. Good evening, everyone. Good evening, and welcome back. So let me know in the chats quickly if all of you can hear me, if I'm perfectly audible, visible to everyone. Welcome back, people. Welcome back. Welcome back. So all set, everything is perfect. Yeah? All right, wonderful. So dear students, just let me know once in the chats whether you watched the first session of chemical kinetics or not. Just let me know once in the chats quickly. Are you done with the part 1 of chemical kinetics? Like which I took 2 days back? Yes, Anish, I'm doing better, thank you. I'm doing better. So I believe everyone is done with the part 1 of chemical kinetics, right? Perfect. So my dear students, today it's going to be the part 2 of chemical kinetics, right? As I've told you in the last session, this particular chapter I'll be completing in total in 3 sessions. So first session I've already taken. Today is going to be the second session. And on Tuesday, it's going to be the third session for chemical kinetics, right? And at the same time, a lot of students were asking me to start the inorganic chemistry after this. Yeah. And let me tell you, from next week only, I'll be starting the inorganic chemistry. Perfect. But my dear students, those classes will happen in the special classes. Those will be the special classes on Unacademy platform, which are absolutely free of cost. I'll let you know exactly how to join those sessions, right? I'll be sharing the link with you on the Telegram group so that you remain updated about that as well. Okay? Perfect. So quickly recapping the things which we discussed in the last session, if you remember, we started with the average rate of reaction. We talked about the instantaneous rate of reaction. Then we talked about the homogeneous gaseous phase reaction carried out at constant temperature. We talked about rate of reaction on the basis of stoichiometry. Did a lot of questions based on that. And that was just the basics which is involved in the chapter chemical kinetics, right? Yeah. And my dear students, what all things we shall be covering today? Let me quickly give you the overview of the things. We shall be starting with the law of mass action. After completing law of mass action, we'll be going to the rate law. After rate law, we'll see the types of reactions, your elementary reactions, the complex reactions. Then we'll talk about the molecularity. We'll talk about the order. We'll exactly see how do we calculate the order of the reaction experimentally. And at the same time, we'll be covering the zero order reactions and its characteristic features as well. So this is going to be these are the topics basically which I shall be covering in the today's session. Okay? Perfect. All right, people. So without wasting a lot of your time, let's get going then. Let's get started with the today's session. So the topic which we have to cover today first, that's going to be the law of mass action. Right? Law of mass action. Let's exactly get to know what this law of mass action is all about and how do we deal with this law of mass action. My dear students, the first point about the law of mass action. What this law of mass action is all about, let me tell you, it is first of all a theoretical concept. This law of mass action, it is basically a theoretical concept. It does not have any experimental background, right? Before knowing what the law of mass action is, let me tell you this particular law of mass action concept, it is a theoretical concept. It does not have any experimental background. Point number 1. But dear students, point number 2. This law of mass action, it was basically given by two scientists. One is called as Gullberg and Laway. Gullberg and Laway. These were the two scientists who exactly gave this concept of law of mass action. Now you must be thinking what this law of mass action exactly is all about, right? What it means. Let's have a look. My dear students, as per the law of mass action is concerned, rate of the reaction rate of the reaction is directly proportional. Rate of the reaction is directly proportional to the product of active masses, of reactants raised to the powers of their respective stoichiometric coefficients. Raised to the powers of their respective stoichiometric coefficients. Now, what it exactly means? Let's have a look what it exactly means. My dear students, try to understand one simple thing. For example, I have got a balanced chemical equation, which is like this: N1A aqueous plus N2B aqueous. Let's say it gives products. I'm assuming this as the balanced chemical equation. Let's assume that it's a balanced chemical equation, right? It's a balanced chemical equation. Now, what this law of mass section suggests? As per the law of mass section is concerned, rate of the reaction, it is directly proportional to the product of active masses of reactants. So I'll write active mass of A multiplied by active mass of B, product of active masses of reactants, raised to the powers of their respective stoichiometric coefficients. What is the stoichiometric coefficient of A? That's N1. So active mass of A raised par N1 multiplied by active mass of B raised par N2. Perfect. This is something which is your law of mass section. So basically, with the help of law of mass section, what do we get? With the help of law of mass section, we get the rate of reaction. As simple as that. And I'm sure all of you must be knowing about the fact any reactant or product which is present in aqueous form, its active mass is taken as its concentration. Any reactant or product which is present in gaseous form, its active mass can be taken either its concentration or pressure, right? And any reactant or product which will be in solid or pure liquid form, their active masses are generally taken as constant, and that constant is taken as unity to reduce the calculations. So basically any reactant or product which will be in aqueous form, its active mass is taken as its concentration. Any reactant product which will be in gaseous state, its active mass can be its concentration, or you can take its pressure as well. And any reactant product which will be in pure solid or pure liquid form, its active mass is constant, which is taken as unity, which is taken as 1 to reduce the calculations basically. Yeah? Now try to understand. My dear students, since A and B right now, they are present in their aqueous forms, right? A is present in aqueous state, B is present in aqueous state. So as per law of mass section, I can write rate of the reaction is directly proportional. I'll write active mass of A raised par N1, that is the concentration of A. Similarly, active mass of B I can write as concentration of B raised par N2. Perfect. Now, eventually you can remove the proportionality sign and you can take the constant also, right? Now, my dear students, try to understand what I'm going to say. Whenever we'll be using the law of mass section to calculate the rate of the reaction which we get with the help of law of mass section, that is something which you call as theoretical rate. Whenever you'll be given with a balanced chemical equation, and for example, you'll be using the law of mass section to calculate the rate of the reaction. Do remember, whatever rate of reaction value comes with the help of law of mass section, that rate of reaction is something which you will be calling as theoretical rate of reaction, right? That's something which you will be calling as theoretical rate of reaction. So whenever from now onwards, for a particular reaction, you will be using the law of mass section. With the help of law of mass section, what do we get? We get the rate of reaction. And whatever rate we get with the help of law of mass section, that is something which we call as theoretical rate of the reaction. Correct? Point number 1. Point number 2. My dear students, let me tell you one more important thing. See, try to understand. Whenever I talk about the rate of reaction, rate of reaction can be measured theoretically. With the help of law of mass action. And at the same time, the rate of the same reaction, it can be measured experimentally as well. Right? It can be measured experimentally as well. Perfect. Rate of reaction, you can calculate with the help of law of mass action, or you can do certain experiments with the help of which you can calculate the rate of reaction. So basically, we have got two ways to calculate the rate of reaction. One is theoretical approach, one is experimental approach, right? My dear students, there are certain reactions in which theoretical rate and experimental rate, they come out to be equal. There are some reactions like that. But there are some reactions as well in which theoretical rate and experimental rate of reaction, they do not come equal. Right? What I'm trying to say is, we have got two ways to calculate the rate of the reaction. One is the theoretical approach with the help of law of mass action. One is the experimental approach, right? So, for example, you are given with a reaction. I'm going to calculate its rate with the help of law of mass action. So that rate is something which I call as theoretical rate. Then I'll be doing certain experiments with the help of which I'll be getting the rate of the same reaction. And that rate is something which I call as experimental rate. There are certain reactions in case of which the theoretical rate and experimental rate, they come out to be equal. But there are some reactions as well in which theoretical rate and experimental rate, they do not come out to be equal, right? Well, when you talk about the experimental rate, it is the actual rate of the reaction. Because this particular rate of reaction you have calculated with the help of experiments basically. This is the theoretical rate of reaction, right? This is the theoretical rate of reaction. Again, I'm telling you, there are certain reactions in which theoretical and experimental rate, they come out to be equal. But there are certain reactions in which both the two, they do not come out to be equal. What can we get from this? What are we trying to understand from this? My dear students, from this point, what I'm trying to convey that from the law of mass action, you do not always get the actual rate of the reaction. You do not always get the exact rate of reaction. You do not always get the correct rate of reaction, right? From the law of mass action, you do not always get the correct rate of reaction. So there are certain modifications which are to be done in this expression. Right? So that we can always get the correct rate of the reaction. Yes? So let me know once in the chats if it is clear. Let me know quickly in the chats if this is clear to everyone. Quickly, my dear students. So basically, again, I'm trying to tell you that there are certain reactions basically in which the theoretical rate, which is calculated with the help of law of mass action, and experimental rate, they will come out to be equal. But there are again some type of reactions in which the theoretical and experimental rate, they do not come out to be equal, right? That means from the law of mass action result, from this particular expression, you do not always get the correct value of rate of the reaction, right? So that means in order to get the correct rate of the reaction, we have to do certain changes in this expression, right? So that we always get the correct rate of reaction with the help of this particular expression, right? So that is the reason we are going to study rate law now. That is the reason we are going to understand rate law now. What is rate law exactly? Rate law, it is based on law of mass action. Rate law, it is based on law of mass action. And as per rate law is concerned, rate of reaction is calculated. Rate of the reaction is calculated by using rate law, which is an experimentally determined quantity. What it exactly means? Try to understand. For example, I'm taking the reaction N1A aqueous plus N2B aqueous. Let's say it gives products. It is a balanced chemical equation, right? Now, my dear students, if you use law of mass section to calculate rate, that will give you the theoretical rate. So theoretical rate of reaction will be equal to concentration of it will be directly proportional to concentration of A raised power N1 multiplied by concentration of B raised power N2, correct? But with the help of this particular result, you do not always get the correct rate of reaction. So certain modifications are to be done. And what are the modifications which we are going to do in this particular expression? In this particular expression, there are slight modifications to do, my dear students. Now, the modifications are like this. I'll be writing rate of reaction is directly proportional to concentration of A multiplied by concentration of B. Instead of N1, N2, I'll be writing X and Y. Instead of N1, N2, I'll be writing X and Y. And let me tell you, this X and Y over here, these two terms, they are measured experimentally. They are measured experimentally. They are measured experimentally, right? This is something which we call as the law of mass action. This is something which we call as law of mass action. And this is something in which the powers are X and Y, which are measured experimentally. This is something which you call as a rate law, which is called as a rate law, right? So what are the modifications which we exactly did? Instead of N1, we are using X. Instead of N2, we are using Y. And this X and Y, they are calculated experimentally, basically. And how they are calculated experimentally, that you'll get the idea in some time, right? So let me quickly know in the chats whether you got the difference between law of mass section and rate law, right? So from law of mass section, you get theoretical rate. From rate law, you get experimentally determined rate. Because in the rate law expression, you have got X and Y, and this X and Y, they are calculated experimentally, basically. Yeah? Perfect? Perfect, people. Let me know once in the chats if it is clear. Let me know once in the chats if it is super clear to everyone quickly. Quickly, my dear students. Quickly, my dear students. Perfect. So now, let's try to understand one thing. Let's try to understand one simple thing over here. Have a look. My dear students, for example, I'm writing a reaction. N1A aqueous plus N2B aqueous. It gives products, for example. It's a balanced chemical equation. Now, I want to write the rate law for this particular reaction. How exactly you're going to write? Rate of reaction is directly proportional to concentration of A raised per X, concentration of B raised per Y, right? Remove the proportionality sign. It's going to be a constant. Concentration of A raised per X, concentration of B raised per Y. Okay? This particular expression is something which you exactly call as, you call it as the rate law. You call it as the rate law. And my dear students, this rate law always gives you the correct value of rate for a particular reaction, right? This particular rate law, it always gives you the correct value of rate of reaction. Try to understand a few more things. What this R indicates over here? R indicates the rate of reaction. R indicates the rate of reaction. What this K indicates over here? K indicates rate constant. K is something which we call as rate constant, right? Now, you must be thinking, how do we define this rate constant? You must be thinking, how do we define this rate constant? Before defining the rate constant, let me tell you one more thing. Before defining the rate constant, let me tell you one more important thing now to understand what exactly I'm going to say. My dear students, in order to calculate the rate of reaction, we have got two ways basically. Either I'll be using the law of mass action or I'll be using the rate law. Either I'll be using law of mass action or I'll be using rate law. When I use law of mass action, rate of reaction will be equal to K, concentration of A raised power N1, concentration of B raised power N2. But when I use the rate law, I'll say rate of reaction will be equal to K. It's going to be concentration of A raised power X, concentration of B raised power Y. And for example, imagine that you have got the reaction as N1A plus N2B it gives products. This is the reaction which we have. Correct? So we have got two ways to calculate rate. Either with the help of law of mass action or with the help of rate law. With the help of law of mass action, which rate do we calculate? Theoretical rate. Which rate do we calculate here? Experimental rate. I told you in some reactions, the theoretical rate and experimental rate. Rate of reaction as per law of mass action. Rate of reaction as per rate law. In some reactions, they will come out to be equal. And those reactions in which the theoretical rate as determined by law of mass action and experimental rate as determined by rate law, those reactions in which these two terms come out to be equal. Can I say for those reactions, X will be equal to N1 and Y will be equal to N2? As simple as that, right? And for those reactions in which the theoretical rate and experimentally determined rate, if they do not come out to be equal, for those reactions, X value won't be equal to N1 and Y value won't be equal to N2. So let me know quickly in the chats if this is again clear to everyone. Quickly, my dear students. Let me know quickly if this is clear. I'll be giving you the details of it in some time, right? You'll understand it in more detailed manner in some time. Yeah? Perfect. Now, try to understand one more thing. My dear students, over here, it's time to define the rate constant first of all. How do you define the rate constant? How do we define the rate constant K for a reaction? For example, imagine that if the concentration of A is equal to the concentration of B and both are taken as 1 molar. Let's say I'm taking the concentration of A and concentration of B both as 1 molar. At that point of the time, I can say rate constant is equal to rate. Right? At that point of time, I would say rate constant is equal to the rate of reaction. So how can I define it? How can I define it? I can say rate constant is actually the rate of reaction only. It is the rate of reaction. It is the rate of reaction when the concentration of all the reactants, when the concentration of all the reactants, when the concentration of all the reactants is taken as unity, is taken as 1 molar, right? Perfect. This is how you're going to define the rate constant. So what is the rate constant basically? Rate constant is nothing. It is the rate of reaction. It is the rate of reaction when the concentration of all the reactants is taken as unity, right? So imagine, my dear students, you are taking the concentration of all the reactants 1 molar. At that point of time, you are calculating the rate of reaction. Let's imagine that you are taking the concentration of reactants and 1 molar, right? At that point of time, you are calculating the rate of reaction. So whatever rate of reaction value you will be getting, that is something which you will be calling as rate constant, right? Perfect. Is this clear to everyone quickly in the chats? Is this clear to everyone quickly in the chats, my dear students? Quickly, let me know in the chats. One more thing which I want to discuss with you. My dear students, when you write the rate law for a particular reaction, you get the powers X and Y, which are calculated experimentally. These powers have got a special name basically. These powers have got a special name. And what is the name? Let me tell you this X over here. It is called as order of the reaction with respect to. X is something which you call as order of the reaction with respect to A. Y is called as order of the reaction with respect to B. And by chance, if I add them up, X plus Y is something which you call as overall order of the reaction. By chance, if you add them up, this X plus Y is something which you call as overall order of the reaction, right? So what is this order exactly? Detailed explanation you'll get in some time when I'll be teaching you order specifically, right? But right now, I would want you guys to understand few things. When you'll be given with a reaction, you'll be directly writing its rate law. in the rate law expression, you'll find certain powers which are calculated experimentally, right? When you add these powers, you'll be getting the number. When you add these powers, you'll be getting a specific number, a particular number. That number is something which you call as overall order of the reaction, right? Perfect. Right, people? And how do we get this X and Y? This X and Y, it's calculated experimentally. How it's calculated experimentally, that also will be taught in some time, right? So till now, let me know in the chats if every single thing is clear or not. Let me know quickly in the chats if every single thing is clear or not. Quickly, my dear students. Quickly, my dear students. Yeah? Perfect. Now, if you ask me about the general features, or I think we have got the slide already made here. Just a second. The slide is already made here. General features of rate constant. What are the general features of rate constant? What kind of idea the rate constant gives us? Yeah, let's get to know about that. My dear students, the first and the important point. Rate constant K. It gives us the idea about the speed of the reaction. It gives us the idea about the speed of the reaction. More the rate constant of the reaction, faster will be the reaction. More the rate constant of the reaction, faster will be the reaction. Lesser the rate constant of the reaction, slower will be the reaction. Right? More the rate constant of the reaction, faster will be the reaction. Lesser the rate constant means slower will be the reaction. Point number one. Point number two. Every single reaction has got a particular value of rate constant at a particular temperature. Every single reaction has got a unique value of rate constant at a particular temperature. So every reaction has got a particular rate constant value at a particular temperature. Yeah? Right? And at the same time, people, rate constant, it changes on changing the temperature of the reaction. When you change the temperature of the reaction, the value of rate constant changes. How it exactly changes, that is something also which we have to discuss in this chapter only, but afterwards, when I'll be teaching you Arrhenius equation, right? So right now, you just have to remember one thing. Rate constant, it is dependent on temperature. When you change the temperature of the reaction, the value of rate constant automatically changes. And you can remember one thing right now. And what is that? You can remember it like this. On increasing the temperature of the reaction, the rate constant of the reaction that increases. Why it increases? What is the logic behind that? That is something which is to be taught, right? That's something which I'll be teaching you. Yeah? Perfect? Perfect, people? So upon changing the reaction, upon changing the temperature of the reaction, the value of rate constant, it automatically changes. How it changes? Why it changes? Again, that's something which is to be discussed in the Arrhenius equation, right? Perfect. And my dear students, how did we define the rate constant? What is the rate constant? It is the rate of reaction. It is the rate of reaction when the concentration of reactants is taken as 1 molar, right? So rate constant is only defined, it's only defined when the concentration of reactants is taken as 1 molar. So rate constant, it is the rate of reaction when the concentration of each reactant is 1 molar. Perfect. Now, my dear students, try to understand. The value of rate constant, should it be dependent on the concentration of reactants or not? Rate constant value, it is independent of the initial concentration of reactants. Rate constant, it is independent of the concentration of reactants, of the initial concentration of reactants, I must say, right? Because the value of rate constant, it is defined only, rate constant is defined only when the concentration of each reactant is taken as 1 molar, right? Yeah, is this point clear to you? Is this point clear to you? Is this point clear to you, people? Quickly. Is this point clear to you? Let me know once in the chats. So these are 4 important features which you need to remember about the rate constant. First of all, the value of rate constant. It gives me the idea about the speed of the reaction. More the value of rate constant, faster is the reaction. Lesser the value of rate constant, slower is the reaction. Every single reaction has got a particular value of rate constant at a particular temperature. the value of rate constant of a reaction changes on changing the temperature. And or increasing the temperature of the reaction, the value of rate constant increases, right? And since rate constant is the rate of reaction, when the concentration of reactants is taken as 1 molar, right? So my dear students, okay, let me tell you one more important thing here. Try to understand this particular point. It will automatically become clear to you. For example, you have got the reaction like this. A gives B. And over here, you have got the reaction like this. C gives D, right? You have got the reaction like this. C gives D. Or let me write the same reaction again. A gives B. Okay? Perfect. The temperature at which the reaction is taking place is, for example, T Kelvin. Here also the temperature is T Kelvin. Right? Now, my dear students, initially, for example, you have got the concentration of A as 5 molar. This will be 0. Perfect. Let's assume initially the concentration of this reactant over here is 10 molar. This is 0. Perfect. Now, what is going to happen with time? When this reaction will start, the concentration of reactants will keep on decreasing. Right? Eventually, there will be a point when the concentration of reactant will reach 1 molar. There will be a time when the concentration of reactant will reach 1 molar. At that point of time, when the concentration of reactant will reach 1 molar, at that point of time, whatever will be the rate of reaction, that is something which you call as rate constant. Similarly, over here, the initial concentration is 10 molar. Now, with time, the concentration of reactant will keep on decreasing. There will be a time when the concentration of reactant will reach 1 molar. At that point of time, whatever will be the rate of reaction, that's something which you call as rate constant. Right? Now, you can easily imagine whether the rate constant will be same or different. No doubt, initial concentrations were different, but I have got nothing to do with the initial concentrations. Rate constant is the rate of reaction when the concentration of reactants is taken as 1 molar, right? Perfect. No doubt, whatever initial concentration of reactants you take, rate constant has got nothing to do with that. Yeah? Right, people? Right, people? Is it clear? Is it clear to everyone? Say yes or no in the chats, because this is one important point. Quickly in the chats. Yeah? Perfect. Now, there are some types of reactions as per chemical kinetics point of view is concerned. We classify reactions into different types. Now, slowly you will see how we are going to increase the level. My dear students, we classify reactions into 2 types basically as per chemical kinetics point of view is concerned. One is called as elementary reaction. One is called as complex reaction. Right? Elementary reactions are also called as simple reactions. These are also called as simple reactions. Now, what these elementary reactions are? What exactly we have to remember about these elementary reactions? Similarly, what these complex reactions are and what do we have to remember about them? Let's get to know about that. So first of all, let's talk about the elementary reactions. Try to understand exactly what I'm going to say. Try to remember exactly what I'm going to say. Just give me a second. Try to remember exactly what I'm going to say. First of all, those reactions which are completed in a single step. Those reactions are what you call as elementary reactions. Point number 1. Any reaction which is completed only in one step, you'll be calling that reaction as the elementary reaction or simple reaction. Point number 1. Point number 2 is the most important here. Try to understand. Law of mass action is truly valid for elementary reactions. That is, the rate expression of the reaction can be written using stoichiometric coefficients. This point is very important. Let's try to understand this. First of all, elementary reactions are completed in a single step. Now, law of mass action is truly valid for elementary reactions. What does it mean? This is very important. Try to understand. For example, you have got the reaction like this. N1A plus N2B. It gives products. It's a balanced chemical equation. My dear students, we have got 2 ways to calculate the rate of the reaction. Rate of this particular reaction. Either I'll be using law of mass action or I'll be using rate law. If I use law of mass action, I'll be getting the theoretical rate, which will come out to be rate constant, concentration of A raised per N1, concentration of B raised per N2, right? This is something which I got with the help of what? With the help of law of mass action. Now, my dear students, I can use the rate law as well. If I use rate law, I'll be getting experimental rate, which is going to be K multiplied by concentration of A raised per X, concentration of B raised per Y. This is the only difference between law of mass action and rate law. Only difference. Here the powers are stoichiometry coefficients. Here the powers are X and Y, which are calculated experimentally. Now, my dear students, in case of elementary reactions, in case of those reactions which are completed in a single step, do remember theoretical rate and experimental rate, it will be always equal. Whether you are calculating rate with the help of law of mass action, whether you are calculating rate with the help of rate law, from both the things you'll be getting the same value. What can we conclude from here? We can conclude that in case of elementary reactions, the value of X is always N1 and the value of Y is always N2. Right? That's what is written here. Law of mass action is truly valid. Law of mass action is truly valid for elementary reaction. Right? Perfect, people. Is this clear to everyone? Let me know quickly in the chats. Let me know quickly in the chats if it is super clear to everyone. Right, people? Yeah? Clear? Yes, Madhavan, we can do that. I'll tell you that in some time. Just wait for it. I hope this particular point is clear because it's important. You'll get its importance in some time. Whenever you see an elementary reaction, for elementary reactions, whether you want to calculate rate with the help of law of mass action or you want to calculate rate with the help of rate law, from both the things, you'll be getting the same result. That means X value will always come out to be N1 and Y value will always come out to be N2. Okay? I hope this particular point is clear. Now, what are complex reactions? What are complex reactions? Complex reactions are basically multi-step reactions. Those reactions which are completed in more than one step. Those reactions which are completed in more than one step. Those are what you call as complex reactions. And my dear students, the steps which are involved in the complex reaction, those are always elementary. What that means? Let me give you one example. This is one clear-cut example. This is one reaction. Okay? And my dear students, this reaction has got two steps basically. This reaction has got two steps. I think we have got people from Unacademy team because I texted them right now. Ajay, there is one guy who is continuously spamming the chats. His name, I'll let you know just a second. I think you already blocked him, yeah? Yeah, you have already blocked him. Is that? By the way, guys, Ajay is the one who handles the backend team of our channel. Already done that, yeah? That's great. Thank you. Okay, listen, guys. For example, I've taken a reaction over here, right? This particular reaction, it is not complete in a single step. It is complete in two steps. Try to understand. First of all, the first step is when NO reacts with Br2, it leads to the formation of NOBr2. And after that, the NOBr2, it reacts with NO, leads to the formation of NOBr. And my dear students, if you add these two steps, what do I get? If you add these two steps, NOBr2 gets cancelled out, right? NO makes it 2 times NO plus this is Br2 here. It gives what? It gives 2 times NOBr. Now tell me one thing, whether this particular reaction, whether it is completed in a single step or more than one step. whether this particular reaction is complete in one step or more than one step. It is complete in more than one step. Any such reaction which is completed in more than one step, that's something which you call as complex reaction. That's something which you call as complex reaction. And this complex reaction, it has got how many steps? It has got 2 steps. Do remember every step involved, here is always going to be elementary. Step 1 will be elementary, step 2 will be elementary, and this net reaction is going to be complex in nature. Yeah? So do remember this particular thing as well. This was again one important point. Yeah? Well, my dear students, after discussing this, these are some basic points which we need basically afterwards. Right now, this is all basics. Something which you have to discuss actually. That's something which will be starting like in half an hour. Okay? But for that purpose, we should have the basics very strong. There is something called as molecularity. How do you define the term molecularity? My dear students, there will be a theory which we'll have to discuss in this chapter. That's collision theory basically. There is one simple statement which collision theory states. For the reaction to happen, for the reactants to form products, reacting species must collide first. Reacting species must collide first. For the reaction to occur, for the reactants to form products, as per collision theory, reacting species, they should collide first. Okay? Now, how do we define the molecularity? Molecularity, first of all, it's a complete theoretical concept. Again, it does not have any experimental background. It does not have any experimental background. It is a complete theoretical concept. Now, how it's defined? The number of reacting species, which can be your atoms, which can be ions, which can be molecules. The number of reacting species which collide simultaneously to form the product, it defines the molecularity of the reaction. For example, 2 reacting species are colliding and forming the product. We'll say molecularity of that reaction is 2. 3 reacting species are colliding simultaneously and forming the product. We'll say the molecularity of the reaction is 3, right? So the number of reacting species which collide simultaneously to form the product, that defines the molecularity of the reaction. For example, look at this particular reaction. Can I say 2 reacting species are colliding and forming the product? So I'll say molecularity of this particular reaction is 2. Simple. How many reacting species are colliding here? 2 plus 1. 3 reacting species are colliding and forming the product. Molecularity of this reaction is 3. Right? Over here, 1 molecule of this, 1 molecule of this. So 2 reacting species are colliding and forming the product. Molecularity of this reaction is 2. Right? What will be the molecularity of the first reaction? Molecularity of the first reaction will be 1. Its collision will be considered with the wall of the container. Right? Its collision will be considered with the wall of the container. Perfect. So my dear students, any reaction whose molecularity is 1, you call that particular reaction as unimolecular reaction. Any reaction whose molecularity is 2, you call it as bimolecular reaction. Right? Molecularity 3, trimolecular reaction, etc., or termolecular reaction. Okay? So, what is molecularity? Molecularity is nothing. It is a complete theoretical concept. As per collision theory is concerned, for the reaction to occur, for the reactants to form products, reacting species should collide first. The number of reacting species, which can be your atoms, which can be ions, which can be molecules, which must collide simultaneously to form the product, that defines the molecularity of the reaction. As simple as that. Now, what are the general features of molecularity? What all things we have to define for molecularity? My dear students, point number 1. Molecularity concept. The concept of molecularity. It's only defined for elementary reactions. It is not defined for the complex reactions. So, the concept of molecularity is only defined for elementary reactions. Molecularity of a complex reaction, it does not have any significance. Molecularity is the concept which is defined only for elementary reactions. Now, what are the general features of molecularity? Try to understand. Try to understand. Over here, I'm writing a statement. Molecularity of the reaction can never be zero. It can never be fractional. It can never be negative. How can you understand this? How can you understand this? For example, molecularity of the reaction is zero. What does that mean? That means zero reacting species, zero molecules are colliding. Does not have any significance. Molecularity of the reaction is negative. That means -3 molecules, -5 molecules are colliding. Is that making any significance? No. Molecularity of the reaction is 2.3, fractional. What does that mean? 2.3 molecules are colliding. Is it making any significance? Is it making any sense? No. So molecularity of the reaction, it can never be zero, it can never be fractional, it can never be negative. Okay? It can never be negative. Perfect? It can never be negative. At the same time, reactions with molecularity greater than 3, they are rarely found. Why so? Why so? Those reactions which have got molecularity greater than 3, they are rarely observed, they are rarely found. Why is that? Why is that? My dear students, what is molecularity? The number of reacting species colliding simultaneously to form the product, right? Now for more than 3 reacting species to collide simultaneously, the probability of more than 3 reacting species to collide simultaneously is very less, right? The probability for more than 3 reacting species, for more than 3 atoms, for more than 3 molecules, for more than 3 ions to collide simultaneously is very less. That's why those reactions which have got molecularity greater than 3, they are rarely observed, right? They are not frequently observed. They are rarely observed because the probability of more than 3 molecules to collide simultaneously, it is very less basically. So those reactions which have got molecularity greater than 3, they are rarely observed. Okay? At the same time, this is something which I already told you. Molecularity is defined only for elementary reactions. It is not defined for complex reactions. It's not defined for complex reactions. Okay? I hope this particular statement is absolutely clear to you. Yeah? Now people, one simple statement. Let's assume I've got 2 steps. These are the 2 steps which are given to me. These are, for example, 2 steps which are given to me. If I add these 2 steps, what do I get? NO gets cancelled. NO makes it 2 times NO plus Br2, it gives what? 2 times NOBr. Tell me one thing. Whether this particular reaction, whether it's completed in 1 step? No, it's completed in 2 steps. So should I be calling it elementary or complex? I should be calling it complex. Absolutely, it's a complex reaction. But few minutes back, I told you the steps which are involved to write the complex reaction, these steps are elementary. So this particular step, it is elementary. This particular step is elementary. And molecularity is defined for elementary reactions. So for step number 1, molecularity is defined. For step number 2, molecularity is defined. But for the complex reaction, molecularity is not defined. Now tell me one thing. What is the molecularity of step number 1? I would say 2 particles, 2 reacting species are colliding, right? Similarly, molecularity of step number 2. Step number 2, molecularity is 2. What is the molecularity of the complex reaction? It is not defined at all. Yeah? Molecularity is the concept which is only defined for elementary reactions. Okay? Order of the reaction also we'll discuss in some time. Just wait for it. I'm right now defining molecularity. Is this clear to everyone, people? Quickly. Let me know quickly in the chats. Let me know quickly in the chats. Let me know quickly in the chats. Quickly. Now, I know all of you are waiting for this particular topic, that's order. So let's get to know what exactly is the order of reaction. But before going into the order of the reaction, let's quickly recap things. Molecularity, that's a theoretical concept, right? It's only defined for elementary reactions. Number two, for the reaction to happen, the reacting species should collide first. The number of reacting species which collide simultaneously to form the products, that defines the molecularity, right? Those reactions with molecularity 1, unimolecular, molecularity 2, bimolecular, etc., right? Molecularity of the reaction can never be 0. It can never be negative. It can never be fractional. Those reactions which have got molecularity greater than 3, they are rarely observed. Why is that? because the probability of more than 3 reacting species to collide simultaneously, that's very less. That's the reason why those reactions whose molecularity is greater than 3, why those reactions are rarely found, right? One more thing where you can mess up, For example, you have got a reaction like this. Half of H2 plus half of I2. It gives HI. If I ask you what is the molecularity of this reaction, I'm sure you'll make a mistake here. What is the molecularity of this reaction? Quickly in the chat. Quickly in the chats. Quickly in the chats. Do you think its molecularity is 1? Because half is equal to 1? You're not going to do that. My dear students, if by chance you get this sort of a reaction, so your first point should be, your first focus should be to convert this fraction into a natural number. What I'll be doing, I'll be multiplying this reaction throughout by 2. If I multiply this reaction throughout by 2, it becomes H2 plus I2 gives 2 times HI. Now tell me the molecularity of this particular reaction. I would say molecularity of this particular reaction is 2, right? So you can directly say molecularity of this reaction also has 2. Perfect. Don't say the molecularity of this reaction is 1. It's 2. Okay. So your first point should be, your first focus should be to convert the fraction into natural number. And you will be getting a new reaction here. Whatever is going to be the molecularity of this new reaction, same is going to be the molecularity of this particular reaction, which you were supposed to calculate. So don't make a mistake here also. All right, let's talk about something which is very important. That's order. How do you define the order? What is order basically? My dear students, order is basically defined as the sum of powers. Order is basically defined as the sum of powers. Sum of powers of the concentration terms. Involved in the rate law. What does that mean? Let's have a look. For example, you have got the reaction like this. N1A plus N2B, it gives products. It is a balanced chemical equation, I believe. It's a balanced chemical equation. Let's assume rate constant of this particular reaction is K. Now, my dear students, I am going to write the rate law for this reaction. Rate law for the reaction, R is equal to K, concentration of A raised by X, concentration of B raised by Y. Should I be calling this as a rate law? Absolutely, it's a rate law, right? In the rate law, you are seeing there are 2 concentration terms here, and their powers are X and Y. This X is something which I call as order of the reaction with respect to A, and Y is something which I call as order of the reaction with respect to B. And if I add them up, this X plus Y is something which you call as overall order of the reaction. Overall order of the reaction, right? So what is order? Order is basically a number. Order is basically a number, right? Order is defined as the sum of powers of all the concentration terms involved in the rate law. That defines the order of the reaction. Now you must be thinking, what kind of idea this order gives us? That also will be discussed. What kind of idea this order will give us? What kind of idea this order can give us? Before talking about that, let me tell you, in order to calculate the overall order of the reaction, are we supposed to write the rate law? Absolutely, we are supposed to write the rate law. Is the rate law theoretical or experimental? Rate law is experimental. Therefore, order. Is it theoretically determined or experimentally determined? Order is an experimentally determined quantity. It's an experimentally determined quantity. Okay. Now, people, at the same time, when I talk about order, it can be 0. Order of the reaction can be 0. And any such reaction whose order is 0. Whose order is 0. What does that mean? Any reaction whose order is 0. What does that mean? Order is 0, that means x plus y is 0. That means x plus y is 0. For example, one of the cases, x value is 0, y value is 0. If x is 0, y is 0, that means R will be equal to K. That means for those reactions, rate of reaction will be independent of the concentration of reactants. Right? Order can be 0 also. And for those reactions, rate of reaction will be independent of the concentration of reactants. Okay? So order, it can be 0. Order can be positive as well. Order can be fractional as well. Order can be fractional as well. For example, any reaction whose order is 0, you call that as 0 order reaction. Any reaction whose order is 1, you call that a first order reaction. Any reaction whose order is fractional, you call that as a fractional order reaction. You call that as fractional order reaction. So unlike molecularity, order can be 0, it can be positive, it can be fractional as well. Now people, one more important thing. Let me tell you order with respect to any reactant. Order with respect to any reactant. It can be negative. It can be negative. Order with respect to any reactant, it can be negative. But overall order of the reaction can never be negative. Can never be negative. What does that mean? That means x can be negative, y can be negative, but x plus y, its value will never come out to be negative. Right? Order with respect to any reactant can be negative. X can be negative, y can be negative, but do remember x plus y value, it is never going to be negative. X plus y value, it's never going to be negative. Right? It's never going to be negative. Now, there is one very important thing. There is one very important thing. First of all, have a look on this particular slide. This is order definition. In order to calculate order, what do we need to write? We need to write rate law. Rate law is experimentally determined. That means order, it is also experimentally determined. Order can be 0, it can be positive, it can be fractional. Order can be negative with respect to any of the reactant, but overall order of the reaction can never be negative. This is the important point, guys. For an elementary reaction, order is equal to molecularity. Now, how can you justify it? How can you justify it? How can you justify this particular statement? For the elementary reaction, order is equal to molecularity. What does it mean? Try to understand. For example, you have got the reaction like this. 2 times A plus B, it gives C. It's a balanced chemical equation, for example. And I'm assuming that the reaction is elementary in nature. The reaction is elementary in nature. We know molecularity is defined for elementary reactions. So what will be the molecularity of this reaction? 2 plus 1, 3. Molecularity of this reaction is 3. Okay? Molecularity of this reaction is 3. Do you remember? Law of mass action is truly valid for elementary reactions. So my dear students, if you want to calculate the rate of this particular reaction, I would say the theoretical rate and experimental rate will be the same. The theoretical rate and experimental rate will be the same. Why? Because it's an elementary reaction. I have mentioned already, in case of elementary reactions, x value is equal to n1 and y value is equal to n2. Perfect. What is n1 value? n1 value is 2. What is n2 value? n2 value is 1. Perfect. So x value is equal to 2. Y value is equal to 1. So what is the overall order of the reaction? I would say overall order of the reaction will be x plus y. So 2 plus 1, 3. Now people, what was the molecularity of the reaction? 3. What is the overall order of the reaction? 3. So do remember, whenever you see an elementary reaction, in case of elementary reactions, order has to be equal to its molecularity. Order will be equal to its molecularity, right? You can understand it like this also. In order to calculate order of this reaction, what do I need to write? I need to write the rate law. Rate law is equal to R is equal to K, concentration of A multiplied by concentration of B, raised for X and Y. But in case of elementary reactions, instead of X and Y, you use the powers. So this is 2, this is 1. So overall order of the reaction will come out to be 2 plus 1, which is 3. Perfect. So this is one very important statement, right? For the elementary reactions, order is equal to molecularity. Okay. Now, tell me one thing. Is this particular statement correct or not? What do you think? Is this particular statement correct or not? A zero order reaction must be complex. Can't a zero order reaction be elementary? What do you think? I'm asking you. I'm asking you. Can't a zero order reaction be elementary? Say yes or no, whether this particular statement is right or wrong. I'm waiting for your answers in the chats. What do you think? It's absolutely correct statement, guys. A zero order reaction must be complex. It is absolutely correct. Why? I'm telling you, a zero order reaction can never be elementary. I'm telling you, a zero order reaction can never be elementary. It's always going to be complex. Because if the zero order reaction was elementary, at that point of time, its order and molecularity should have been same. If the zero order reaction was elementary, then its order and molecularity should have been same. Since I'm talking about zero order reaction, that means those reactions whose order is zero. Order no doubt is zero, but can molecularity be zero? Molecularity cannot be zero. Molecularity cannot be zero. Molecularity cannot be zero. Gentle shots, just wait for all these things. I did not discuss everything in detail yet. This is just the basics. Whatever you're asking for zero order reactions, rate does not depend on the concentration. For the first order, they depend. Second order, they depend, right? So just wait for it. Let me complete the basics, then we'll move on. We'll summarize all the things together. Okay, tell me one thing, guys. So is this particular statement absolutely correct? A zero order reaction, it can never be elementary. Because if the zero order reaction is elementary, then its molecularity has to be zero. Molecularity is equal to zero, does not have any significance. Right? All right. Among these two statements, tell me which statement is perfectly correct. Among these two statements, which statement is correct? Among these two statements, which statement is correct? First statement is a unimolecular reaction must be first order. A unimolecular reaction. That means that reaction whose molecularity is 1. A unimolecular reaction must be first order. Is it necessary that any reaction whose molecularity is 1, its order will be also 1? It is a must condition only when the reaction will be elementary in nature. It is the must condition only when the reaction will be elementary in nature, right? So first statement, it's not correct, but second is correct. A unimolecular elementary reaction, its order will be always 1, right? Its order will be always 1. Okay? I hope you got this particular point as well, right? So this was just the idea of order. Now, before solving the questions based on order, before letting you know the significance of the order, let me tell you one more simple thing. A relation between different rate constant. Relation between different rate constant. Try to understand. My dear students, for a particular reaction, we always have got a rate constant. For a particular reaction carried out at particular temperature, every reaction has got a particular value of rate constant. So K reaction represents a rate constant of the reaction. Now I'm defining few more things. I'm defining Ka. Ka is something which you call as rate constant for disappearance of A. Ka is something which you call as a rate constant for disappearance of A. For example, I'm writing Kb. Kb is something which you call as a rate constant for disappearance of B. For example, Kc. Kc is called as a rate constant for appearance of C. And similarly, Kd is called as a rate constant for appearance of D. Now, my dear students, there is a particular result which relates rate constant of reaction and all these individual rate constants. There's a particular result. I'm not going to derive that. I'll be giving you that result directly. Do remember rate constant of the reaction. Sorry. Rate constant of disappearance or appearance of reactant product is always equal to rate constant of reaction multiplied by stoichiometry coefficient of reactant product. This is the particular result which you are going to remember. It has got derivation as well, No need to go into the derivation. Just remember the result, utilize the result. For example, if I write Ka is something which I call as rate constant of disappearance of A. It will be equal to rate constant of reaction multiplied by stoichiometric coefficient of A, that's N1. Similarly, Kb, rate constant of disappearance of B, is equal to rate constant of reaction multiplied by N2. Similarly, Kc, it will be equal to rate constant of reaction multiplied by N3. Similarly, Kd will be equal to rate constant of reaction multiplied by N4, right? So do remember how to write the relation between rate constant of the overall reaction and rate constant of individual rate constant. Yeah? Okay. Now, if you got it, what should be the answer of this particular question as per you? What do you think? What do you think should be the answer of this question? Find the relation between K1, K2 and K3. K1 is the rate constant of disappearance of A. K2 is the rate constant of disappearance of B. K3 is the rate constant of appearance of C. Okay. Now, if I ask you, what is K1? K1 will be rate constant of reaction multiplied with stoichiometric coefficient of A. That's 2. K2 will be equal to rate constant of reaction multiplied with stoichiometric coefficient of B. K3 will be equal to rate constant of reaction multiplied with stoichiometric coefficient of C. Right? Perfect. You got 3 equations. Now, from this particular equation, what is K reaction? Rate constant of reaction. That will be K1 by 2. From the second result, rate constant of reaction will be equal to K2 divided by 3. From this particular expression, rate constant of the reaction is equal to K3. Now, a reaction always has got a particular value of rate constant. Rate constant of reaction, reaction. So from first, second and third, you can say K1 divided by 2 has to be equal to K2 divided by 3, which has to be equal to K3. Okay. Now take the LCM of denominators. LCM of denominators will come out to be 6. So multiply with 6, multiply with 6, multiply with 6. So this is 3 times K1 is equal to 2 times K2, which is equal to 6 times K3. So this is the relation between K1, K2 and K3 which you were supposed to calculate. Is this clear? Is this clear, people? Is this clear? Let me know once in the chats quickly. Everyone. Yeah? Okay. I hope this is clear to everyone. Now guys, one more simple thing. Right now I'm teaching you small things. So that once you get to know these small things, there will be no issue in understanding the actual stuff. Right? Which you might find a bit complicated. Okay, units of rate constant. What are the units of rate constant? For example, you have got the reaction A gives B. This is the reaction, for example. Let's assume that order of the reaction is equal to N. Okay, let's assume that order of the reaction is equal to N. First of all, see, you have got only one reactant here. Can I say, in this particular reaction, whatever is the order with respect to A, whatever will be the order with respect to A, same is going to be the overall order of the reaction. So order with respect to A and overall order of the reaction, both are going to be same because there is only one reactant, right? Let's assume the order of reaction is N. Let's say the rate constant is K. Can you write the rate law? Rate law will be equal to. It is going to be K. The actual rate law is active mass of A raised per what? Active mass of A raised per N. This is the actual rate law, right? This is the actual rate law. Now, for example, this A was in aqueous state. If A is in aqueous state, you can say R is equal to K, concentration of A raised per N. For example, this A was in gaseous state. You can say R is equal to K. Instead of active mass of A, you can write pressure of A raised per N. Right? You can use both the things. Even for example, if it is a gas, if A is the gas, for example, for gases, you can write rate law like this or like this, because for gases, active mass is concentration as well as pressure. For gases, we define pressure as well as concentration. Okay. Now tell me one thing. So what will be K over here? K will be equal to R divided by concentration of A raised per N. What will be K over here? It's going to be R divided by pressure of A raised per N. Right? So units of K. Units of rate here are going to be moles, liter inverse. Moles, liter inverse. For example, time is in seconds, so second inverse. units of rate, moles, liter inverse, second inverse. In the denominator, we have got concentration. Concentration is moles per unit volume. So it's going to be moles, liter inverse, raised per n, right? So I would say the overall unit of K will be equal to moles, liter inverse, raised per 1 minus n. And if time is in seconds, then second inverse. What is n? N defines the order of the reaction. Or if you want to use this particular expression, rate, its units can be atm second inverse. For example, if pressure is in atm, time is in seconds, divided by pressure is in atm, so atm raised per n, right? So it has to be atm raised to the power 1 minus n and second inverse. So these are the general units of rate constant which I would want you guys to remember. General units of rate constant which I want you guys to remember. Yeah? Right, people? Okay. Now try to understand one thing. Let's assume you have got a zero order reaction. For a zero order reaction, n is equal to 0. If n is equal to 0, what will be the units of rate constant? It's going to be moles, liter inverse, second inverse. Or if you want to use this result, if n is equal to 0, it's going to be atm, second inverse, for example. Yeah? My dear students, if you have the first order reaction, if n is equal to 1, first order reaction, what are going to be the units of rate constant? If n is equal to 1, 1 minus 1 is 0, anything raised for 0 is 1. It is directly going to be second inverse. For the time, it can be second inverse, minute inverse, hour inverse, right? If you want to use this particular expression, again it's going to be second inverse only, or minute inverse, or hour inverse, whatever, right? So indirectly, time inverse. Okay? If you have the second order reaction, n is equal to 2, put the value of n as 2, So rate constant units will be moles, liter inverse, raised per 1 minus 2 is minus 1. It is minus 1 and second inverse. Or here you can write atm raised per minus 1. With it, you can write second inverse. So based on the order of reaction, you have to write the units of rate constant. Okay? Do remember this particular scenario as well. Perfect? Perfect, guys? Now, if you ask me, what kind of idea this order gives us? What kind of idea order of the reaction gives us? My dear students, order of the reaction is going to let you know. Order of the reaction is going to let you know how many times the rate of reaction will change. How many times rate of reaction will increase or decrease upon changing the concentration of reactants. How exactly? For example, I'm assuming that it is a zero order reaction. I'm assuming that order of this reaction is 0. For example, you have got one more reaction, C gives D. I'm assuming that order of this particular reaction is 1. Perfect. Can you write rate law for this? Absolutely. R is equal to K, concentration of A raised power 0. Write rate law for this. R is equal to K, concentration of C raised power 1. Right? Anything raised power 0 is 1. So R is coming out to be K. Okay, R is coming out to be K for the first reaction. And R is equal to coming out to be Kc raised power 1. Okay. Now tell me one thing. If you double the concentration of A, what will happen to rate of reaction? Rate of reaction is independent of concentration of A. If you double the concentration of A, nothing will happen to the rate of reaction. But here, if you double the concentration of C, the rate will double. Okay? Here nothing happened, but here something is happening. So, what was the difference? Order of the first reaction was 0, order of the second reaction was 1. And here you are observing that upon doubling the concentration of reactant, nothing is happening to the order. Sorry, nothing is happening to the rate. But upon doubling the concentration of C for this reaction, upon doubling the concentration of this reactant, rate of reaction is doubling. Okay? For example, you have got a reaction, E gives F. Let's assume order of this particular reaction is 2. Can you write rate law? R is equal to K, concentration of E raised power 2. Correct? Now, if you double the concentration of reactant, 2 2s becomes 4. Rate becomes 4 times. For this particular reaction, upon doubling the concentration of reactant, rate becomes 4 times. So order, what kind of idea it's giving you? It's simply giving you the idea how many times the rate of reaction changes upon changing the concentration of reactant. You getting it? Are you getting this? Is it clear? So order is letting me know simply like how many times the rate of reaction changes upon changing the concentrations. Our next session is on Tuesday. Perfect. Manikanda, you can just drag the video a little back. It will be a replay for you. Okay. There is no need to repeat. It's a live session. All right. Let's solve some basic questions based on order. Basic questions, I'm telling you. Look at this particular question. As far as this question is concerned, for a chemical reaction A gives B, it is found that the rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. How do you solve these sort of basic questions? My dear students, you are given with the reaction A gives B. You are given with the reaction A gives B, whose rate constant is K. Let's assume that since there is only one reactant here, so order with respect to A has to be the overall order of the reaction. Let's assume that the overall order of the reaction is equal to N. Let's assume that the overall order of the reaction is equal to N. If you got to know the overall order of the reaction is equal to N, can you write the rate law for the reaction? Rate law for the reaction, R is equal to K, concentration of A raised to the power 2. This is rate law. Correct? Let me call this as equation number 1. Let me call this as equation number 1. Now, as per the question, it is found that the rate doubles. It is found that the rate doubles. Initially, the rate was R. Now, it is becoming 2 times R. It is becoming 2 times R. When is it becoming 2 times R? When is it becoming 2 times R? When the concentration of A is becoming 4 times. Earlier, the concentration was A. Now, it is becoming 4 times A. Let me call this equation number 2. Why am I writing 2 here? It's N, right? Because order of the reaction is N, right? Perfect. So, how many equations I made? I made 2 equations. Yeah. Now, my dear students, it's time to solve these equations. Divide equation 2 by equation 1. When you divide equation 2 by equation 1, R gets cancelled. So, on left side, you have got 2. K gets cancelled. A power n cancelled. On right side, you have got 4 raised power n. What should be the power of n? What should be the value of n such that LHS RHS becomes equal? What should be the value of n such that LHS RHS will be equal? So n value has to be 1 by 2 such that 4 raised power 1 by 2 will come out to be 2. So n value is equal to 1 by 2. And what was this n exactly? N was the overall order of the reaction. Yeah? N was the overall order of the reaction. Okay? That's something which you were supposed to calculate. Is it clear? So you should be able to solve these sort of questions as well. Let me solve one more. Look at this question. Look at the question carefully. Try to solve this. The rate of the reaction becomes half when the volume of the vessel is doubled. Find the order of the reaction. So you are doubling the volume of vessel. We have to see what will happen to the rate of the reaction. Sorry, we have to see what is the order of the reaction. The reaction is given to me. The reaction is given to me. My dear students, this particular reaction, which is given to me, let's assume that its order is equal to N. If its order is equal to N, can't you write its rate law? Its rate law has to be R is equal to K. Concentration of A raised power N. Concentration of A raised power N. This is the rate law, correct? Now, my dear students, what is concentration basically? Concentration is moles per unit volume, right? So I can write the same equation as R is equal to K. Instead of concentration of A, I can write moles of A divided by total volume of the system in liters raised power N. Let me call this as equation number 1. Now, as per the equation, the rate of the reaction becomes half. Initially, the rate was R. Now, it is R by 2. The rate of the reaction becomes half. When the volume of the vessel is doubled. Initially, the volume of the vessel was V. Now, it's 2 times V. Now, it's 2 times V. Let me call this equation number 2. Now, divide the 2 equations. You're done, right? Divide the 2 equations. For example, dividing 1 by 2. Dividing 1 by 2. So, R divided by R by 2. R by 2, RR gets cancelled. On left side, you get 2, right? What is something which you'll be getting on the right side? This and this gets cancelled. NA divided by V raised power N, NA divided by V raised power N gets cancelled. So here, what do we get? Here, what do we get? We get 2 raised power N here, right? We get 2 raised power N here. Perfect. That's the only thing which is left. Now, compare these two. So n value has to be equal to what? N value has to be equal to 1. So what was n? N was the overall order of the reaction, right? I hope this particular equation is also clear to you. Right, people? I hope this particular question is clear. These are two more questions. Look at these questions. We are given with some random rate law, something like this. A reaction is given. Calculate the order of reaction. If the concentration of Br2 is very high, if the concentration of Br2 is very less. My dear students, just remember one thing. For example, if these conditions were not specified, imagine if these conditions were not specified, then your answer will be directly order cannot be predicted. It's a complicated rate law, something, I don't know what's mentioned here. If the conditions are not mentioned in this type of the rate law, this is the rate law which is given, then directly what you will be doing? Can you all see me? Am I audible, visible to you? Yeah? Just say once in the chats. Can you all see me? Am I audible, visible? Quickly, everyone. Everyone in the chats once quickly. Okay. See now. What I'm trying to say, if the conditions are not specified, then your answer will be directly, the order cannot be calculated. But right now the conditions are mentioned, so order can be calculated. The first question is, calculate the order of the reaction if concentration of Br2 is very high. So we are assuming that the concentration of Br2 is very high. Okay. What is the rate law that's given to us? R is equal to K1 multiplied by concentration of H2 multiplied by concentration of Br2 raised power 1 by 2 whole divided by its concentration of Br2 plus K2 multiplied by concentration of HBr. This is the rate law which is given. Now the first condition suggests that the concentration of Br2 is very high. My dear students, if the concentration of Br2 is kept very high, so in the denominator, can't you neglect this term? This particular term can be neglected because the concentration of Br2 is very high. And if the concentration of Br2 is very high, that means in place of concentration of Br2 plus K2 multiplied by concentration of HBr, you can only write concentration of Br2. Correct? Now write the rate law again. Rate law will be equal to R is equal to K1 concentration of H2 multiplied by concentration of Br2 raised power 1 by 2. And in the denominator, we'll be only having Br2 raised power 1, which can be mentioned as K1 as such, concentration of H2 as such, Br2 raised power 1 by 2, and Br2 raised power 1, which has to be equal to Br2 raised power minus 1 by 2. Right? Powers are, bases are same, powers are subtracted in case of division. Okay? Now, my dear students, look at this particular rate law. Look at these concentration terms. Look at their powers. So I'll say order with respect to H2 is 1, order with respect to Br2 is minus 1 by 2. So I would say the overall order of the reaction will be equal to X plus Y. X plus Y. The value overall will come out to be 1 by 2. So 1 by 2 is the order of the reaction whose rate law was given to me and whose concentration of Br2 was kept very high. Okay. The second part I'm sure you can do easily. If the concentration of Br2 is kept very less, and if the concentration of Br2 is kept less, that means instead of Br2 plus K2 HBr, you'll be only writing K2 HBr. Right? So let me show you that part as well. Because you might get confused. To solve the second part. Try to understand the second part, guys. In the second part, he is saying that if the concentration of Br2 is very less, if the concentration of Br2 is very less, for example, if it is very less, that means in place of Br2 plus K2 HBr, what you'll be writing? You'll be writing K2 HBr only, because Br2 is very less. Okay. Now write the rate law again. So rate law is equal to R is equal to K1 concentration of H2 raised power 1, concentration of Br2 raised power 1 by 2, and in the denominator, in place of this whole term, you'll be only writing K2 multiplied by concentration of HBr. Clear? So R is equal to, this is constant, this is constant. Division of two constants will make it a new constant, K dash for example. And this is H2 raised power 1, Br2 raised power 1 by 2, and this will be HBr raised power minus 1. I took HBr in the numerator, right? So this is my perfect correct rate law now. So I'll say order with respect to H2 is 1, order with respect to Br2 is 1 by 2, order with respect to HBr is minus 1. So what about the overall order of the reaction? Overall order of the reaction now will be equal to 1 plus 1 by 2 plus minus 1. The overall order of the reaction again will be 1 by 2 only. Okay? So you should be able to solve these sort of questions also. Sometimes they'll be giving you the complicated rate law form. If the conditions are not mentioned, then right, the order cannot be calculated. Right? If the conditions are specified like this, then you can calculate the order. Is this clear? Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students, if this is clear. Yeah? Perfect. Now, let's get to know how order is calculated experimentally. How do we get the value of X and Y experimentally? There's a trick also, but there is a general procedure as well. So first, I'll go ahead with the general procedure. Then I'll let you know the trick also, with the help of which you can calculate the order easily. Okay? My dear students, look at this particular question. In this particular question, we are given with a reaction. This is the reaction that's given to us. And there are 3 experiments which have been carried out in the lab for this particular reaction. When the concentration of NO is kept this much, when the concentration of H2 is kept this much, at that point of time, rate of reaction was this much. Similarly, the experiment was repeated. Concentration of NO was kept this much, H2 concentration, this rate of reaction was coming out to be this much, right? Similarly, the third experiment. So 3 experiments have been carried out. 3 experiments have been carried out. In the first experiment, this is the rate. Second, this is the rate. Third, this is the rate. We have to check what is the order of the reaction. How do you calculate the order here? Understand. First thing, in order to calculate the order, what do we need to write always? We need to write the rate law. So write the rate law for the given reaction. R is equal to K, concentration of NO raised by X, concentration of H2 raised by Y. This is your rate law first of all. Yeah. Now in this rate law, select the data which is given in the first experiment. In this rate law, fit the data which is given in the first experiment. As per the first experiment, what about the rate? The rate is 3 into 10 raised per how much? 3 into 10 raised per minus 5 moles per liter per second is equal to K. What is the concentration of NO kept in the first experiment? That is 5 into 10 raised per minus 3 raised per X. Concentration of H2, that is 2.5 into 10 raised per minus 3 raised per Y. So this is I call as equation number 1. Equation number 1. Now similarly, you can make the second equation. Fit the second experiment data in this particular equation. Our value will be equal to 9 multiplied by 10 raised per minus 5 is equal to K. Concentration of NO. NO concentration is 15 multiplied by 10 raised per minus 3 raised per X. Concentration of H2 in the second experiment, that's 2.5 into 10 raised per minus 3 raised per Y. You call this as experiment number 2. Equation number 2. What about equation number 3? That will be equal to equation number 3. 36 multiplied by 10 raised per minus 5 is equal to K. It's going to be 15 multiplied by 10 raised per minus 3 raised per X. And it's going to be 10 multiplied by 10 raised per minus 3 raised per Y. Calling this as the third equation. So how many equations I got? I got third equations, right? My dear students, we have to solve these 3 equations and get the value of X and Y. You can easily do that. Let's try to see what to do. For example, if I'm dividing 2 and 1, I'm dividing 2 and 1. Equation 2 divided by equation 1. What do I get? 10 power minus 5, 10 power minus 5. Cancel. 9 by 3 is 3. On LHS, you have got 3. Now, This whole term is cancelled. 10 raised power minus 3, 10 raised power minus 3 cancelled. 15 divided by 5 is 3, so it's going to be 3 raised power x. Now tell me, from this particular equation, can't I say x value has to be 1? X value has to be 1, then only LHS RHS will be equal. So I got the value of x. I got the value of x. Now it is time to get the value of y. It's time to get the value of y. So what exactly I'll be doing? I will be doing one thing. Third equation divided by second equation. 3 divided by 2. So this term cancel. 36 divided by 9. That comes out to be 4 is equal. This term cancel. K cancel. 10 raised power minus 3, 10 raised power minus 3 cancel. 10 divided by 2.5 is 4. So it's 4 raised power y. So 4 is equal to 4 raised power y. So what has to be the value of y? Such that LHS RHS is equal. So y value has to be 1. Right? So x value you got, y value you got. So what should be the overall order of the reaction as per you? It has to be x plus y, 1 plus 1, that comes out to be 2. So overall order of the reaction is equal to 2. Yeah? Perfect. Is that clear, people? Is it clear? Quickly. Quickly, guys, quickly. Perfect. Okay, try to understand one more simpler way of solving the same question. Try to understand one more simpler way of solving the same question. Since you got to the actual procedure, right? If you try to solve the same question without using pen and paper, what do you need to do? See, rate law already you know. R is equal to K, concentration of NO raised power X and concentration of H2 raised power Y. This is the rate law which you already know. Now, my dear students, look at the experiments. If you see, in the first and second experiment, concentration of H2 is kept same. In the first and second experiment, concentration of H2 is kept same, right? Okay. So, what you need to do, imagine as if in this expression there is no H2. Imagine as if there is no H2 in the expression. Now, when you are moving from first to second, what is happening to the concentration of NO? I'll say concentration of NO is increasing 3 times. From first to second, concentration of NO is increasing 3 times. At the same time, look at the rate value. Rate is also increasing 3 times. Yeah? Right? Right, people? So when you look at first and the second experiment, the concentration of H2 is kept same. So imagine as if H2 is not here. Now, NO concentration is being increased 3 times and rate of reaction is also increased 3 times. So imagine H2 is not here. You're increasing the concentration. You're increasing the concentration of NO 3 times. Leave this part aside. You're increasing it 3 times. And eventually, rate is also coming out to be 3 times. Rate is also increasing 3 times. When is it possible? It is possible only when the value of x is 1. Because 3 raised power 1 is 3. If the value of x was 2, then 3 square has to be 9. If the value of x was 2, then on making this 3 times, rate has to be 9 times. But it's observed that on increasing NO concentration 3 times, rate is becoming 3 times. Rate is increasing 3 times. Right? So directly the value of x is 1. Perfect. Now similarly, look at experiment number 2 and experiment number 3. NO concentration is kept same. So imagine NO is not here. Imagine NO is not here. Now, when you move from here to here, the concentration of H2 is increased 4 times. Look at the rate. The rate is also increased 4 times. The concentration of H2 is increased 4 times and the rate is also increased 4 times, which is possible only when the value of y is 1, right? Because if the value of y was 2, then 4 square should have been 16. Then rate should have been increased 16 times. But that's not the case here, right? Perfect. Is that clear? Is it clear, people? Quickly in the chats. Is it clear, guys? Say yes or no in the chats. You got to know how to solve the question like this. We have got a lot of spammers today. Let them come. Let them come. Go ahead, bro. Go ahead. Quickly, people in the chats. Is it clear? Perfect. Let's try to solve one more question like this. Let's try to solve one more question like this. Look at this particular question. General procedure, I hope you already know. Yeah. General procedure, I hope you guys know. Let's solve the question. Right? Let's solve the question with the help of direct result. I mean, the direct shortcut which I told you. First of all, the reaction is given to us. Rate law will be equal to R is equal to K. Concentration of NO raised per X, concentration of Cl2 raised per Y. Correct? Now look at the first and second experiment. NO is kept same. Concentration is kept same. This is increased 3 times. Rate is increased 3 times as well. So on making the concentration 3 times, on increasing the concentration 3 times, the rate is also increasing 3 times, which is only possible if the value of X is 1. So you got the value of X. You got the value of X, that's what. Now get the value of Y. Get the value of Y, guys. Get the value of Y. Now, first of all, look at the 3 experiments again. Now try to see experiment number 1 and 3. Cl2 concentration is kept same. The concentration of NO is made 3 times here. NO concentration is increased 3 times. And rate is becoming 9 times. Concentration of NO is increased 3 times. Concentration of NO, just a second, guys. Sorry. Wait. Cl2, this is NO. X is not 1. I think Y is 1. Right? The concentration of Cl2. Okay, we were increasing the concentration of Cl2. So it's Y value that's 1. It was Y value that was 1. Now look at the second case. NO concentration is increased 3 times, rate is becoming 9 times. NO concentration is increasing 3 times, right? And rate is becoming 9 times, which is only possible when the value of X is 2. Because 3 ka square then only will come out to be 9, right? So X is 2, Y is 1. So overall order of the reaction is 3. That's all. Well, you can use the same procedure, the basic procedure as well. Yeah? Right? Is it clear? Perfect, people? Is it clear? Say yes or no quickly in the chats. Perfect. So I hope from now onwards, easily, you can solve the questions based on experimental determination of rate. Okay? Now, second order reaction and pseudo first order, they are different. They are not same. I think we'll take a break for like 15 minutes. Then after 15 minutes, we'll get back. Okay? So the time right now is 7:41. So session will resume at session resumes at 8:05 p.m. I want everyone to be back because now we are going to start the actual scenario. Till now, whatever I was teaching you, that was complete basics. Now it's going to be the real stuff which I'll be teaching you, right? In which students get a lot of problems. And this is something which I'll be dealing in detail, right? So zero order reactions, integrated equation, and the characteristic features and the types of problems. So be back at 8:05 sharp, guys. Till then, you have some tea. That's what I'm also going to have. See you in a while. Take care. So guys, can you see me again? Am I audible, visible to everyone? Yes. Are you all back? Perfect, guys. Perfect. So let's start then. Right? Let's start with zero order reactions. Just give me a second. All right. So I'm marking the heading over here as zero order reactions. Zero order reactions. This is one important topic, right? So my dear students, how do we first of all define the zero order reaction? Let me mark its definition first. Then I'll make you understand what these zero order reactions exactly are all about. Yeah? Talking about its definition. The reactions in which rate of reaction is independent of the concentration of the reactant. What it means, you'll get the idea in some time. Have a look, people. For example, imagine that you are given with a reaction that is A gives B. Imagine it is one balanced chemical equation. A gives B. I'm assuming that the rate constant of this reaction, for example, is K. And at the same time, I'm assuming that the order of the reaction is 0. Order of the reaction is 0, right? So first of all, before talking about the actual stuff here, let me make you clear with few new terminologies. First, I'm starting at time t is equal to 0. At time t is equal to 0, the reaction has not started yet. There is no product formation yet. Let's assume that initially at time t is equal to 0, the concentration of reactant, for example, that is A naught. So what will be the concentration of product? Concentration of product at time t is equal to 0 will be absolutely 0, right? Now, my dear students, when the reaction will start, what will happen to the concentration of reactant? Concentration of reactant will keep on decreasing and concentration of product will keep on increasing. Let's assume at time t, the concentration of reactant left, that is AT, and the concentration of product formed, that is BT. So first of all, be careful with all these terminologies. What A naught is, what AT is. So let me write it over here. What is A naught? A naught is basically the concentration of reactant at T is equal to 0. What is AT? AT is basically the concentration of reactant left at time t. The concentration of reactant left at time t, right? So initially the concentration of reactant is A naught. At time t, the concentration of reactant left is AT. Now, for example, I want you guys to write the rate law for this particular reaction. Can you write the rate law? You should be able to write. Rate of the reaction as per rate law is equal to rate constant multiplied by concentration of reactant raised power 0, because the order of the reaction is 0. See, anything raised power 0 is 1. So what does that mean? Is the rate dependent on the concentration of reactant? No. Rate is independent of the concentration of reactant. If you increase or decrease the concentration of reactant, nothing will happen to the rate. Any such reaction in which the rate will be independent of the concentration of reactant, you call that particular reaction as the zero order reaction. Okay, point number one. Point number two. My dear students, is there any other way to calculate the rate of reaction? Absolutely, you can use the differential form as well. I'll say rate of the reaction is equal to, with respect to A is the reactant. So start with minus sign. 1 by stoichiometry coefficient. Stoichiometry coefficient is 1. Change in the concentration of A divided by dt. Right? This term will give me the rate of reaction. Even this term will also give me the rate of the reaction. Agreed? Now what I'll be doing? Let me talk about this particular statement now. I'm getting minus d of A divided by dt. Minus d of A divided by dt is equal to K and concentration of A raised power 0. Right? So I can write d of A, change in the concentration of A, is equal to minus K times dt, because concentration of A raised power 0, that's going to be 1. Now, dear students, I'm going to make the integrated rate equation. I'm going to make an equation for zero order reaction, which I call as integrated rate equation. And that particular equation will be valid for all the zero order reactions. And you'll see its application part as well in some time. Just understand. So first of all, I'm going to make an integrated rate equation. So what I'll be doing, I'll be integrating on both the sides. Here I'm integrating with respect to the concentration of A. Right? I'm integrating with respect to the concentration of A. And concentration of A is changing from A0 to AT. So lower limit is A0, upper limit is AT. And here I'm integrating with respect to time, which is from 0 to t. So here lower limit is 0, upper limit is t. You can check also whether the limits are correct or not. My dear students, we know at time t is equal to 0, the concentration of reactant is A0. Right? At time t, the concentration of reactant will be AT. Perfect. Now, try to understand a few more things. My dear students, integral of dx is x. Integral of dy is y. So integral of dA will be A. Integral of dA will be A. And the limits are A0 till AT is equal to minus k will come out. Integral of dt is t. So it will come out to be minus kt. Okay. Now we use the upper limit and lower limit. It has to be AT minus A0 is equal to minus kt. So from this particular expression, you got to know AT is equal to A0 minus kt. This particular equation which I made over here, this particular equation is something which you call as integrated rate equation. This is something which you call as integrated rate equation for zero order reactions. Right? It is something which you call as integrated rate equation. For which kind of reactions? For zero order reactions. Now, my dear students, what these terminologies are? AT is the concentration of reactant left at time t. A0 is the initial concentration of reactant. T is the time in which the concentration of reactant is changing from A0 to AT. Right? Now, where all do we use this particular result? My dear students, you'll be getting a question, for example. You'll be getting a question. You'll be given with a zero order reaction in which you have to check in what time duration the concentration of reactant changes from 8 molar to 3 molar, for example. In what time duration the concentration of reactant changes from 5 molar to 3 molar, for example. How do we calculate that? With the help of this particular result, with the help of this particular expression. You'll see its application part in some time. First, I want all of you to remember this result from now onwards. AT is equal to A0 minus KT. And this particular result I am calling as integrated rate equation for the zero order reactions. Okay? Where can we use the integrated rate equation? I'll let you know in some time. When we do the questions, there you get the idea where do exactly we use it. Okay? So this was the first point which was related to zero order reactions. Point number 1. Point number 2, my dear students. Point number 2 for the zero order reactions. What is that? That's half-life. Half-life, which is represented by either T 50% or T1 by 2. Half-life of the zero order reaction. First of all, how do we define the half-life? My dear students, half-life is defined as the time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction. Or in other words, you can define it like this. The time taken to reduce the concentration of reactant from A0 to A0 by 2. Let's get to know what exactly it means. Let me make you understand what it means, and then we'll be making its expression and its application as well. Imagine that you have got the reaction A gives B. Imagine that it's a zero order reaction. Let's say at time t is equal to 0, the concentration of reactant is 4 molar. Let's assume that at time t is equal to 0, the concentration of reactant is 4 molar. Now, my dear students, when the reaction will start, what will happen to the concentration of reactant? Concentration of reactant will keep on decreasing with time. Can I say there will be a time when the concentration of reactant will reach 2 molar? The time taken to complete 50% of the reaction. The time taken to complete 50% of the reaction. The time taken for the concentration of reactant to be equal to half of its initial value. That time taken is something which we call as half-life. Let's assume that in 10 seconds, the concentration of reactant is changing from 4 molar to 2 molar. That means the half-life of the reaction will be 10 seconds. As simple as that. So in short, the time taken to complete 50% of the reaction. What is meant by 50% completion? 50% completion means 50% of the reactant has got dissociated into products. 50% of the reactant has got converted into products. Right? So if 50% of reactant is converted, I'll be left with 50% of reactant as well. Okay? So I hope you just got the idea of what this half-life exactly is all about. Now people, let's try to make its general result. That is important. Have a look. Imagine you have got the reaction A gives B. Its rate constant is K and it is a zero order reaction, for example. At time t is equal to 0, the concentration of reactant is A0. This will be 0, right? Now, my dear students, imagine that 50% of reactant is complete. If 50% of reactant is complete, that means 50% reactant has got converted into products. If 50% reactant has got converted into products, that means 50% of reactant will be still left in the container, right? So 50% of reactant means A0 by 2. This is the concentration of reactant left in the container. At time, how much? At time, T is equal to T half. Okay? At T is equal to T half, the concentration of reactant left will be A0 by 2. That means 50% of reaction has got completed. 50% reactant has got converted into product. Now, dear students, this is the concentration of reactant left. And the concentration of reactant left is represented by AT. The concentration of reactant left at time t, that is represented by AT. Now try to understand. Over here we got a condition. The condition is at t is equal to t half. At t is equal to t half, the concentration of reactant left, that is A0 by 2. At t is equal to t half, AT will be equal to A0 by 2. Now, my dear students, what is our integrated rate equation for the zero order kinetics? Integrated equation is like this. AT is equal to A0 minus KT. So what I'll be doing, I'll be using this particular condition in this particular expression, right? As per this condition, AT value is nothing, that is A0 divided by 2 is equal. This is A0 minus K. Instead of T, you'll be writing T half, correct? So from this particular equation, you got T half is equal to A0 divided by 2K. So this is the general expression which you guys are going to remember from now onwards to calculate the half-life of a zero order reaction. A general expression to calculate what? To calculate half-life of a zero order reaction. Okay, perfect. So half-life of the reaction, half-life of the zero order reaction, it's equal to A0 divided by 2K. This was the second parameter related to the zero order reactions. Okay. My dear students, the third parameter which is related to zero order reaction, that's what we call as completion time. Completion time, which is represented by T 100%. What is meant by completion time? Completion time is defined as the time taken to complete 100% of the reaction, in short. Okay? Time taken to complete 100% of the reaction. Okay? Try to understand what it means. For example, again you have got a zero order reaction whose rate constant is K and order of reaction is 0. Initially, for example, the concentration of reactant was A0, this is 0. Now, when the reaction will start, the concentration of reactant will keep on decreasing. It will keep on decreasing. My dear students, at time t is equal to T 100%, what will happen? I would say 100% of reactant would have got converted into product. If 100% reactant would have got converted into product, I would say the concentration of reactant left in the container at T is equal to T 100%, that is going to be 0. And concentration of reactant left in the container, that is represented by AT. So over here, I got one more condition. At time T is equal to T 100%, AT value is equal to 0. Now use this particular condition in the integrated rate equation. What is the integrated rate equation? AT is equal to A0 minus KT. Now my dear students, AT value is 0 basically, is equal to A0 minus K. Instead of T, you are going to write T 100%. So from this particular expression, can't we calculate T 100%? So I would say T 100% is nothing, that is A0 divided by K. What is this particular result? It is the result which is going to let you know the time taken to complete 100% of the zero order reaction. This is the time taken to complete 100% of the zero order reaction. Now people, already we calculated T 50% also. Half-life of the reaction. That was equal to A0 divided by 2K. A0 divided by 2K. This was the half-life. So if you look at these two equations, if I divide these two equations, what do I get? I'll be getting T 100% divided by T 50% will come out to be 2. Right? So from this particular expression, you can say T 100% is equal to 2 times T 50%. Now, what does it mean? What does this particular expression mean? It means that a zero order reaction. Is completed. Completed means 100% completed. A zero order reaction is completed in how many half-lives? In 2 half-lives. A zero order reaction is completed in 2 half-lives, right? Perfect. For example, you have got a reaction whose half-life is 10 minutes. I'm asking you, how much time does it take to complete 100% of the reaction? Directly 2 times half-life. So 2 into 10, that comes out to be 20 minutes. So it will take 20 minutes for the reaction to get 100% completed, right? So this is one more statement which you need to know. A zero order reaction, it's 100% completed in how many half-lives? In 2 half-lives. This was the second point. Sorry, this was the third point. Now talking about the fourth point. Fourth point will be degree of dissociation. Degree of dissociation, which is represented by alpha for a zero order reaction. I hope you exactly remember how do we calculate degree of dissociation. Do you remember that? Alpha, degree of dissociation, is equal to number of moles of reactants dissociated divided by initial moles of reactants taken. Correct? Number of moles of reactants dissociated divided by initial moles of reactants taken. Now guys, try to understand. For example, you have got a zero order reaction like this. A gives B, whose rate constant is K, and order of reaction is 0. It's a zero order reaction. Imagine that at time t is equal to 0, the concentration or the moles of reactant are A0. Moles of reactant or concentration of reactant. At time t is equal to 0, for example, that's A0. So this has to be 0. Correct? At time t, At time t, the concentration, the moles of reactant left. The concentration of reactant left or the moles of reactant left, that is 80. Right? That's 80. Initially, the moles of reactant were A0. At time t, the moles of reactant left are 80. Now, I want to calculate alpha value, degree of dissociation for this particular zero order reaction. Number of moles of reactants dissociated. Number of moles of reactants that got converted into products. What is that going to be? Initially, I start with A0 moles. I'm left with 80 moles of reactant. So how many moles of reactant got converted? Initially, I took A0. Now I'm left with 80. So 80 A0 minus 80. These are the moles of reactant. This is the concentration of reactant. These are the moles of reactant. This is the concentration of reactant, which got converted into products, which got dissociated, divided by initial moles of reactants. Initial moles of reactants were nothing. That was A0. Correct? Now, my dear students, get the value of alpha. Alpha has to be equal to A0 minus. What is 80 for a zero order reaction? For a zero order reaction, 80 is nothing. That's A0 minus KT. Divided by what? Divided by A0. So A0 gets cancelled. So alpha value has to be equal to KT divided by A0. This is how you calculate degree of dissociation for a zero order reaction which has got the stoichiometry 1:1. Right? So you're going to remember this particular parameter as well. This is the fourth parameter related to zero order reactions. That is degree of dissociation. Right? That is degree of dissociation. Alpha is equal to KT divided by A0. K is the rate constant, T is the time, A0 is the initial concentration. Perfect. This was the fourth parameter. Talking about the fifth parameter for the zero order reactions. What is that? That is units of rate constant. Units of rate constant for a zero order reaction. My dear students, generally the units of rate constant are written as moles, liter inverse, raised power 1 minus n, and time, for example, is in seconds, second inverse. Or you can write it like this. For example, pressure is in atm, so atm raised power 1 minus n. Let's assume time is in seconds, second inverse, right? Now you are given the zero order reaction, that means n value is equal to 0. If n is equal to 0, that means I'm talking about what? I'm talking about the zero order reaction. If n is equal to 0, the value of rate constant, the unit of rate constant has to be n value 0. So it's going to be moles, liter inverse, second inverse, or choose this one, n is 0, so it's going to be atm second inverse. Perfect. So these are the units of what? These are the units of rate constant for a zero order reaction. Okay? For a zero order reaction. Now, dear students, the sixth point. The sixth point for a zero order reaction. Do remember it. I'm going to make a table over here. I'm just going to make a table over here. Over here, I'm writing time. Over here, I'm writing time. And here, I'm writing concentration of reactant. Concentration of reactant. Now, try to understand what exactly I'm going to say. Let's assume at time t1, the concentration of reactant was A1. At time t2, the concentration of reactant is A2. At time t3, the concentration of reactant is A3. At time t4, the concentration of reactant left, that was A4, right? Concentration of reactant initially is A1. Concentration of reactant left at time t2, that's A2. Concentration of reactant left at time t3. Concentration of reactant left at time t4, correct? Now, my dear students, I'm going to talk about the zero order reaction. Let's say the reaction is like this, A gives B, whose table I have given you. A gives B, whose table I have given you. For the same time interval, what does it mean? For the same time interval. What does that mean? That means T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. So basically, I'm considering the time intervals to be same. The time interval from here to here is equal to, from here to here is equal to, from here to here. So I'm considering the same time interval. If in the same time interval, A2 minus E1 will be equal to A3 minus A2, which will be equal to A4 minus A3. So basically, I'm trying to say, if in the same time interval, the concentration of the reactants will have the same common difference. Will have the same common difference. Do remember at that point of the time, the nature of the reaction, the order of the reaction is going to be 0. Do remember at that point of the time, the order of the reaction is going to be 0. Okay? If in the same time interval, the concentration of reactants or pressure of reactants, for example, or in general, you can say amounts of reactants, if they have got the same common difference, if A2 minus A1 is equal to A3 minus A2 is equal to A3 minus A4 minus A3, then do remember the nature of the reaction, the order of the reaction is going to be 0. It is particular condition valid for a 0 order reaction. Okay? It's a particular condition valid for a 0 order reaction. So you can directly say, after looking at the table, you can say the order of the reaction is absolutely going to be how much? It's going to be 0. Okay? Perfect. Right, guys? Now try to understand one more thing. This was the 6th parameter which you have to remember related to the 0 order reactions. 7th parameter which I want you guys to remember related to the 0 order reaction. What is that? Have a look. For example, you have got the reaction like this, A gives B. You have got the reaction like this, A gives B, whose rate constant is K, and the order of the reaction is 0. It is a 0 order reaction. Let's assume at time t is equal to 0, the concentration of reactant is A0. At time t1, the concentration of reactant is AT1. At time t2, the concentration of reactant is AT2. The concentration of reactant is AT2. Right? My dear students, if I ask you, how much time does it take? If I ask you how much time does it take for the concentration of reactant to reduce from AT1 to AT2? I'm asking you how much time does it take for the concentration of reactant to reduce from AT1 to AT2. That means what am I asking you? I'm asking you this time interval from here to here. I'm asking you this time interval from here to here. Which time interval I'm asking you? I'm asking you the time interval T2 minus T1. This is the time interval I'm asking you. How much time does it take for the reactant concentration to reduce from AT1 to AT2? So which time interval I'm asking you? I'm asking you this time interval. T2 minus T1 time interval. Right? Or let's try to write it like this. Just a second. Let's try to write it like this. Have a look. What is my integrated equation? That is AT is equal to A0 minus KT. AT is equal to A0 minus KT. This is my first condition. The first condition says at time T1, the concentration of reactant left is AT1. Now use the first condition here. So instead of AT, I'll be writing AT1 is equal to A0 minus K. Instead of T, you are going to write T1. Now use the second condition. Use the second condition in the same expression. It's going to be AT2 is equal to A0 minus K, K times T2. Correct? My dear students, this is, let's call this as equation 1, let's call this as equation 2. If I take the difference of the two, I'm going to write the final result. Let's take the difference of the two, subtract them and get the final result. Final result is going to be AT2 is equal to AT1 minus K times T2 minus T1. When do we use this particular expression? When do we use this particular expression? My dear students, in case of 0 order reactions, if they ask you how much time does it take for the concentration of reactant to reduce from AT1 to AT2, how much time does it take for the concentration of reactant to reduce from AT1 to AT2? That means they are asking you this time interval, T2 minus T1 time interval. T2 minus T1 time interval. This is the expression which you guys are going to use. This is the expression which you guys are going to use. Right? Remember this particular expression as well. I'll show its application in some time. Just wait for it. Just wait for the things. So this was the 7th parameter related to what? Related to 0 order. Let's exactly first of all have a look what all parameters we discussed about the 0 order. About the 0 order, we started with the integrated equation, right? Second, we discussed the half-life. Third, we discussed completion time. Next, we discussed degree of dissociation. Next, we discussed units of rate constant. Next, we discussed about this shortcut table method. Next, we discussed how much time does it take for the concentration of reactant to change from AT1 to AT2. This one more expression, okay? Now, the 8th parameter related to 0 order. What is that? That is graphs related to 0 order reaction. Now, you must be thinking, what are the graphs which are related to 0 order reactions? let's try to make all the graphs which are related to zero order reaction, which can be asked. Okay, try to understand. The first graph which I'm going to make, that's going to be rate of reaction versus concentration of reactant. This is the first graph which we'll make. The second graph which we are going to make, that's going to be concentration of reactant left versus time taken, AT versus T. The third graph which I'm going to make, that's going to be half-life, A half versus A naught, initial concentration. The next graph which we are going to make, that's going to be A 100% versus A naught. Okay. The next graph which we'll make, that has to be between what? Alpha, degree of dissociation versus A naught. Okay, these are few graphs which we are going to make over here. Try to understand. The first graph is rate versus concentration of reactant. In case of zero order reactions, we know R is equal to K, concentration of A raised power 0 as per rate law. So R is equal to K. So is the rate dependent on the dependent on the concentration of reactant? Rate is not dependent on the concentration of reactant. So what has to be the nature of the curve? On changing the concentration of reactant, nothing happens to the rate. So it is independent, right? This particular graph, it is only valid for zero order reactions. Okay, point number one. Point number two. Point number two. AT versus T. You already know the equation. AT is equal to A naught minus KT, correct? Now AT you are plotting along y-axis. Time you are plotting along x-axis. So this will be your M. The sign here is minus, and this term will be C. So y is equal to minus mx plus c. Y is equal to minus mx plus c. The nature of the curve has to be like this. Okay, it's a straight line. If I ask you what about the slope of this particular curve? Slope of this particular curve basically is minus k. If you ask me what is the intercept, what about the intercept? Intercept is c, which is basically A naught. Right? So this is the graph which is particularly valid for zero order reactions. Okay. Now people at the same time, look at this particular graph. T half versus A naught. What is the result between T half and A naught for the zero order? You know T half is equal to A naught divided by 2k, or you can say 1 by 2k multiplied by what? Multiplied by A naught. This is the half-life expression. Now T half you are plotting along y-axis. A naught you are plotting along x-axis. So this whole term has to be your M. So y is equal to mx. Y is equal to mx means straight line passing through origin. If you ask me what about the slope of this particular curve? Slope is basically M, and M value is nothing. It is 1 upon 2k. Correct? 1 upon 2k. Right, people? Now at the same time, T 100% versus A naught. It will be again a straight line, but its slope is going to be what? Its slope is not going to be 1 upon 2k. It's going to be 1 upon k this time. Because you know T 100% is equal to A naught by k. T 100% is equal to A naught by k, right? Right, people? Perfect. Okay, look at the next one. Look at the next one. Alpha versus A naught. Few minutes back only we derived alpha. Alpha was equal to A naught divided by KT, I guess. Was this the expression? No, it was KT by A naught. Right? Alpha was KT divided, yes, KT divided by A naught. So I'm asking you to make a graph between alpha and A naught. Alpha and A naught, they're inversely proportional, and whenever you have to make a curve between two variables which are inversely proportional to each other, the nature of the curve has to be rectangular hyperbola. So this is the nature of the curve. So these are the different graphs which can be asked related to what? Related to zero order reactions. I hope this is clear. Let me know quickly in the chats if all these graphs are clear. These are the different types of graphs which can be asked in case of zero order reactions. Quickly, let me know in the chats if all the things are absolutely clear to you. Right, people? Now, how do we and where do we use the expressions which I gave you in case of zero order reactions? Before that, there is the 9th parameter which I want you guys to remember. Take the screenshot of this. Take the screenshot of this. Examples of the zero order reaction. It can be the memory-based question. It can be the memory-based question. Photochemical reaction between H2Cl2. It is the direct example of zero order. Decomposition of HI over gold surface. Zero order. Decomposition of NH3 over molybdenum. It's again zero order. So these are the examples of the zero order reactions. Do remember them. Do remember them directly. Do remember them directly. So what is the special feature about these reactions? These are the zero order reactions. That means if you change the concentration of reactants, nothing is going to happen to the rate of these reactions. Nothing is going to happen to the rate of these reactions. So take the screenshot of this particular slide. This is important. Okay. Now, let's try to see exactly the equations which I gave you, the concepts which I told you related to zero order. How do we use them and where do we use them exactly? Look at the first one. Look at the first one, guys. The first question. I'll show you how to solve the questions by general approach. There are shortcuts as well, which I'll tell you later on. But right now, I'll teach you first of all how to solve the questions with the help of general approach. For a zero order reaction, A gives B. So we are given with a zero order reaction, that's A gives B. For a zero order reaction, A gives B. It was observed that at the end of an hour, 75% of A has reacted. What time? 10% A will be unreacted. Understand? It's mentioned that at time t is equal to 0. At time t is equal to 0, the initial concentration of reactant is taken as A naught. This has to be 0, absolutely. Right? This has to be 0. Okay, guys, this has to be 0. Now, it is mentioned that it was observed at the end of an hour. So, at the end of an hour, 75% of A has reacted. Now, people, if 75% of reactant has reacted, does that mean 25% of reactant will be still left in the container? Absolutely. 25% of reactant. 25% of A naught will be equal to 25 by 100 into A naught, that will be A naught by 4. So this is the concentration of reactant left in the container at T is equal to 1 hour. It is mentioned in the question. At the end of an hour, 75% reactant has reacted. If 75% of the reactant has reacted, that means 25% of the reactant is still left in the container. Right? 25% of the reactant, that means 25% of A naught, which is going to be 25 by 100 into A naught. Do remember, AT is always the concentration of reactant left. AT always represents the concentration of reactant left. Now, what are we supposed to calculate? At what time A will be 10% unreacted? So, at what time A will be 10% unreacted? Unreacted concentration of A we have to calculate at time t. Sorry. We have to calculate at what time? At what time A will be 10% unreacted? 10% unreacted means 10% of the reactant has to be left. 10% of reactant means 10 by 100 into A naught, which has to be A naught by 10. Now, this is the value of AT. So, see how many conditions we have. Try to understand how many conditions we got. We got 2 conditions. The first condition says, at T is equal to 1 hour, the concentration of reactant left is A naught by 4. The second condition, at what time the concentration of reactant left will be A naught by 10. At what time the concentration of reactant left will be A naught by 10. These are the 2 conditions. My dear students, remember, from the given conditions, from the first condition, I will be always getting the value of rate constant. From the first condition, I'll be getting the value of rate constant. From the second condition, I'll be getting the value of time. Right? And how exactly you're going to solve it from here. Okay. What is the integrated rate equation for the zero order kinetics? For the zero order kinetics, you know, AT is equal to A naught minus KT. This is your integrated rate equation. Correct? Now use the first condition in this integrated rate equation. AT value is nothing, that is A naught by 4. As per first condition, is equal to A naught minus K. T value is equal to 1 hour. Right? So I would say K will be equal to 3 divided by 4 A naught. K will be equal to 3 by 4 A naught. What are the units of K? Well, time is given in what? Time is given in hours, right? Time is given in hours. So K units has to be moles, liter inverse, R inverse. Okay, so you got the rate constant. I told you from the first condition, we'll be getting the rate constant. Now second condition. Put the second condition in the integrated rate equation. As per second condition, AT is nothing, that is A naught divided by 10 is equal to A naught minus K value already we got, that is 3 divided by 4 A naught multiplied by T we have to calculate. So A naught cancel. So you can calculate T from here. T value will come out to be 1.2 hours. So this is something which I was supposed to calculate. At what time A will be 10% unreacted? Or you can say at what time 90% of the reaction is completed. So you got to know after 1.2 hours, you can say 10% of reactant will be left in the container. Or you can say at 1.2 hours, you will find out that 90% of the reaction has got completed. Is this clear? Is this clear, guys? This was the first question which you did. Very simple question this was. Moving on to one more. I'm not using any shortcut right now. No shortcut. I'm using the general procedure of solving the equations. A zero order reaction, you're given, for example, with a zero order reaction, A gives B, whose rate constant is, for example, K, and the order of the reaction is mentioned in the question, that's 0. Now, firstly, at time t is equal to 0, the initial concentration of reactant is A naught. This is 0, correct? Now, my dear students, it's mentioned that a zero order reaction is 20% completed in 10 minutes. A zero order reaction is 20% completed in 10 minutes. Now, what does it mean? It means that 20% of reactant has got converted into product. If 20% reactant has got converted into product, can I say 80% of reactant will be still left in the container? 80% of the reactant will be still left in the container at 10 minutes. 80% of reactant means 80 divided by 100 into A naught, right? Which comes out to be 0.8 A naught. So this is the concentration of reactant which is left in the container at 10 minutes. Okay. Now what are we supposed to calculate? At what time it will be 10% completed? Sorry, at what time it will be 80% completed? At what time the reaction will be 80% completed? 80% completed means 80% of reactant has got converted into product. That means 20% of reactant is left. So at time t, 20% of reactant will be left in the container. So 20% of A naught, 20 by 100 into A naught, which comes out to be 0.2 A naught. So this is the concentration of reactant left at time t. So how many conditions I got? Tell me. This is the first condition and this is the second condition. What am I supposed to calculate? I'm supposed to calculate t. At what time the concentration of reactant left will be 0.2 A naught. Now, my dear students, as I told you already, from the first condition, I'll be always getting the value of rate constant. From the second condition, I'll be getting the value of time, right? Now, what exactly we'll be doing? We will be using the integrated rate equation. What is the integrated rate equation for the zero order kinetics? You know it. AT is equal to A naught minus KT. AT is equal to A naught minus KT. Now, tell me one thing. From the first condition, AT value is how much? In the first condition, AT value is 0.8 A naught is equal to A naught minus K. T value in the first condition is 10 minutes. So from here, you can get the value of K. K will be 0.2 A naught divided by 10. What are going to be the units of K? It's going to be moles, liter inverse, time is in minutes. So it's going to be minute inverse, right? So K value you got with the help of the first condition. Now use the second condition in the integrated rate equation. Use the second condition. Second condition says AT is equal to 0.2 A naught is equal to A naught I'm writing as such minus K value is 0.2 A naught divided by 10 multiplied by T we have to calculate. So A naught cancel. You got one equation and from here T value will come out to be 40 minutes. So what is this T exactly? This T is the time. This T is the time which tells you that 80% of the reaction is getting completed in 40 minutes, right? You got to know 80% of the reaction is getting completed in 40 minutes. T is the time at which 80% of the reaction has got completed. T is the time at which 20% of the reactant is still left in the container as such. I hope you can easily solve these sort of questions from now onwards, right? Let's try to see a few more questions based on the zero order kinetics. My dear students, look at this particular question. Look at this particular question. We are given the table. It's a table basically, right? And the reaction that's given to us, that's A gives B. This is the reaction that's given to me. We are given with a table. When the concentration of reactant is 1 molar at time t is equal to 0, this at this, this at this. What are we supposed to calculate? Calculate the rate constant. Calculate the rate constant. Try to understand what exactly I'm going to say. We are supposed to calculate the rate constant of this zero order reaction. K value you have to calculate. How do we get the value of K? What do you think? Dear students, try to understand. At time t is equal to 0, the concentration of reactant is 1 molar. And time t is equal to 0, the concentration of reactant we represent with A naught. So A naught value is 1 molar. It is given to me as per the equation. Right? It's given to me as per the equation. Now, the concentration of reactant left is 0 molar. When? At 120 seconds. Now you understand. When the concentration of reactant left will be 0 molar. Concentration of reactant left is equal to 0 molar. What does that mean? That means 100% reaction has got completed. Right? When 100% reaction gets completed, at that point itself, you can say the concentration of reactant left is 0, right? So can I say this is the time at which the concentration of reactant left is 0? So should I be calling this time as the completion time? Absolutely, it's going to be the completion time, right? So completion time, T 100%, is given to me as per the equation. That's 120 seconds. Correct? We are almost done. Do you remember the expression which I told you by means of which we can calculate T 100%? T 100% for a zero order reaction, that's A naught by K. So A naught by K is nothing, it is 120 seconds. So K value has to be equal to A naught divided by 120. A naught is 1 molar divided by 120. Units are supposed to be moles, liter inverse, second inverse. This is the rate constant which you were supposed to calculate. That's all. Yes? You should be able to solve these sort of questions as well. Yeah? You should be able to solve these sort of questions as well. All right. Look at this particular question. Can you give it a try? Can you give it a try quickly? T half for the zero order reaction is 1 hour. Okay, T half is 1 hour. Perfect. When the initial concentration of reactant was 2 molar. When the initial concentration of reactant was 2 molar, T half is equal to how much? T half is 1 hour. How much time does it take for the concentration to reduce from 0.5 molar to 0.25 molar? My dear students, I gave you one equation a few minutes back. And what was that equation? Try to understand. See, you are given the reaction A gives B, whose rate constant is K. It is a zero order reaction. It is absolutely a zero order reaction as per the equation. Now, initially at time t is equal to 0, the concentration of reactant which I represent with A naught, that's given to me as, when the initial concentration was 2 molar, that's given to me as 2 molar, right? How much time does it take for the concentration to reduce from 0.5 molar to 0.25 molar? Let's assume at time t1, the concentration of reactant left was 0.5 molar. And let's assume at time t2, the concentration of reactant left was, imagine 0.25 molar, right? As per the equation, what do we have to check? We need to check how much time does it take for the concentration of reactant to reduce from 0.5 molar to 0.25 molar. So what time interval do I need to calculate? I have to calculate this time interval, t2 minus t1. Have I told you how to calculate this time interval? I gave you one direct result, if you remember, for the zero order reactions. You know, AT2 is equal to AT1 minus K times T2 minus T0. This is the result which we derived a few minutes back only. So AT2 is given to me as the equation 0.25. AT1 is nothing, that's 0.5 minus K into T2 minus T1. Now, K value is not given to us. K value is not given to us. How do we get the value of K? My dear students, as per the equation, half-life for the zero order reaction is given as 1 hour. Half-life for the zero order reaction is given to me as 1 hour. And you know, half-life for the zero order reaction, that's nothing, that's A naught divided by 2K. So basically A naught divided by 2K is 1, right? So from here, K will be equal to A naught by 2, right? A naught is 2, and 2 by 2, that comes out to be 1. So K has to be 1 mole liter inverse. Time is given in hours. It's R inverse, right? So this is the value of rate constant. Now we got the rate constant as well. So the final expression, I mean, K value you got, K value is 1. So T2 minus T1. T2 minus T1 from here comes out to be how much? 0.2 hours, 0.25 hours. So what it means exactly? It means it will take 0.25 hours to reduce the concentration of reactant from 0.5 molar to 0.25 molar. I hope this is clear, right? I hope this is clear. Perfect. Now guys, try to understand one more thing. Look at this particular equation. Here you can do a mistake. Here you can do a mistake. Why is that? Whatever expressions I gave you related to zero order reactions, those expressions were valid for the reaction A gives B, in which the stoichiometry was 1:1. Whatever expressions I gave you till now, those are valid for the zero order reactions in which the stoichiometric coefficient of reactant was 1. But here in this reaction, stoichiometric coefficient of reactant is 2. Stoichiometric coefficient of reactant is 2. What I'll be doing here? Whenever the stoichiometric coefficient of reactant is not 1, It is anything apart from 1. At that point of time, there is something very simple which you need to do. What is that? Just try to understand. Just a second. Say, 2 times A gives P. This is basically the reaction that's given to me, right? Well, half-life of the reaction is given to me as 120 seconds. Initial concentration of reactant was given to me as 2 molar. What do we need to calculate? We need to calculate rate constant of the reaction. Rate constant of the reaction. My dear students, stoichiometry of the reactant is not 1, it's 2, right? So, what I'll be doing? T half is equal to 120 seconds. What was the formula to calculate T half for zero order? It used to be A naught divided by 2K. But this was the formula when the stoichiometric coefficient of reactant was 1. And the stoichiometric coefficient of reactant is not 1. So instead of rate constant of reaction, you'll be writing rate constant of disappearance of A. You will be writing rate constant of disappearance of A. So the formula changes here. It's not A naught by 2K reaction. It's A naught by 2Ka, right? Because the stoichiometry here is 2. Okay? So this value is equal to 120, right? Now A naught value is 2. A naught value is 2. 2 got cancelled. So Ka value got equaled 1 upon 120, and its units are going to be moles, liter inverse, second inverse. But as per the question, am I supposed to calculate the rate constant of disappearance of A? No, I'm not supposed to calculate the rate constant of disappearance of A. What do I need to calculate? I need to calculate rate constant of the reaction. Do you remember I told you a few minutes back only? Rate constant of disappearance of A. It will be equal to rate constant of the reaction multiplied by stoichiometric coefficient of A. Right? So it's going to be Ka divided by stoichiometric coefficient of A, that is 2. It has to be equal to rate constant of the reaction. So I must say rate constant of the reaction is equal to Ka by 2. So Ka by 2 comes out to be Ka divided by 2. The value will be 1 upon 240 moles, liter inverse, second inverse. This is the rate constant of the reaction. I hope you can easily solve it from now onwards, right? So got to know where to use this particular concept? When the stoichiometry of the reactant is anything apart from 1. Yeah? Perfect, guys? All clear? No, Madhavan, that's not the half-life. Half-life is initial concentration A naught to A naught by 2. Okay? 0.5 was not the initial concentration. That was the concentration in the middle somewhere. Right? Anish, how does that matter? How does that matter? I'm changing the stoichiometry, right? I'm changing the stoichiometry. When you change the stoichiometry, basically, integrate rate constant, integrate rate equation, that automatically changes. Correct? That will change. Okay, guys. So this was all about your zero order reactions. Now first order reactions, their characteristic features, Arrhenius equation and collision theory. That will be done in the next session, right? So is everything clear till here? Is everything clear till here? Let me know in the chats. Whatever I taught you today, is every single thing clear? Sure? So exactly assume that whatever I've told you today, whatever I've taught you today, starting from law of mass section, then we talked about the rate law, we talked about types of reactions, elementary complex reactions, we talked about molecularity, we talked about order, right? We did few questions based on experimental determination of order. We did few questions on general order, right? Then we started with the zero order reactions. We talked about certain important features which can be asked from the zero order reaction, starting with integrated rate equation, half-life, completion time, degree of dissociation, units of rate constant, all the graphs which are involved here, right? Examples and the few questions which can be asked from the zero order kinetics as well. Okay, so I hope all the things are absolutely clear. So in the next session, which is going to be lecture number 3 of chemical kinetics, what all things we are going to cover? We'll be talking about the first order reactions. Number 1, we'll be talking about the parallel first order reactions. We'll be talking about the gaseous first order reactions. Okay, we'll be talking about the Arrhenius equation and collision theory. So these are the topics which we shall be covering in the next session. So next session will be approximately some 4 to 5 hour session, because that has to be the last session, and it will happen on Tuesday. It will happen on Tuesday at 6 p.m. on your Unacademy NEET English channel. Okay. Perfect. Rahul, this is the complete English channel, right? There are a lot of teachers who take care of the Hindi speaking students. So I think I'm the only one who teaches in English this particular chemistry. So one has to teach in English as well, yeah? Or else Hindi mein padha sakta hu main. Okay, guys. And after this chapter, we shall be starting with either electrochemistry or, yeah, electrochemistry only we shall be starting. Perfect. So till now, which all chapters we completed? Do you remember? We completed mole concept. We completed redox reactions as well. Mole, redox. We completed states of matter, solid state, thermodynamics, chemical equilibrium, ionic equilibrium, and this is chemical kinetics going on. Chemical bonding we completed. So this is the 9th chapter which we are completing, guys. 9th chapter which we are completing. And at the same time, your HSP sir, he completed your GOC, isomerism, right? Hydrocarbons he completed. And apart from that, he completed your haloalkanes, haloarenes, and right now he's taking care of your amines. So basically in chemistry, we are done with 13 to 14 chapters. Now there are not many chapters left. Okay, same goes for your physics, same goes for your biology as well, right? So we'll try to complete syllabus as soon as possible so that we can go for the revisions, we can go for the crash courses, etc., right? And let me tell you, in the last week of this particular month, I'm not going to take class on YouTube. I'll be taking special classes in which I'll be teaching you inorganic chemistry, basically, starting with periodic properties. I'll let you know exactly when I'll be taking that session. Okay, I'll be giving you its link as well. So if you've not joined the Telegram yet, I would want you guys to join the Telegram as well so that you remain updated about all the sessions which I take here, right? Perfect. So my dear students, let me know in the chat quickly if all of you can hear me, if I'm perfectly audible, visible to everyone. Quickly, let me know in the chats. Quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Welcome back, guys. Welcome back. Welcome back. Welcome back. So, dear students, as you all must be knowing, till now we are done with 2 sessions of the chapter Chemical Kinetics, right? And today it's going to be the last session. It is going to be the last session of the chapter. And basically, we are going to complete this particular chapter in the today's session. Yeah? Perfect. So, are you guys done with the first 2 sessions of kinetics? Have you watched them? Have you watched the first 2 sessions of the kinetics chapter? Say yes or no in the chats. Say yes or no in the chats quickly. Are you done with the first 2 sessions? And related to All India Test Series, which we have launched, right? Its syllabus, I'll be letting you know today, right? In the Telegram group. I'll be letting you know the syllabus for the upcoming tests for the All India Test Series. In the Telegram group, I'll be mentioning that. Sir, Hindi mein session kab hoga? Hindi mein session nahi hoga. This is the English channel, right? If you want to get trained in Hindi or English, there are other channels of Unacademy too. Okay, you can consult them. Perfect. So without wasting a lot of time, let's get going and let's get started with the today's session. But before that, The ones who have not subscribed to the channel yet, I would want every one of you to subscribe to the channel right now, so that you remain updated about all the sessions which we take live on this particular Unacademy NEET English channel, right? So do like the session, do share the video with everyone, let everyone get benefited out of the sessions. And my dear students, at the same time, if you have not subscribed to the channel yet, please and please do subscribe to the channel as well, right? So that you'll remain updated about the sessions, about the chapters which we keep on completing on YouTube, that too absolutely free of cost. Yeah? Perfect, guys. So, if you remember, in the last session, we completed till zero order reactions. So, in this particular session, I'm going to start with the first order reaction. Okay? What are first order reactions and what all characteristics we have to remember about first order reactions, what all different types of questions can be asked from first order, all those things I'm going to discuss one by one in detail, right? Perfect, guys? Yes, absolutely. Next chapter is going to be your GOC. So IUPAC nomenclature, I'm taking day after tomorrow. It's going to be a one-shot video. The thumbnail, I believe it's already out. You would have seen that too. Perfect, guys. So let's get going. Let's get started. All right. Just give me a second. Just give me a second. Just give me a second, guys. All right, so let's talk about the first order reaction. What first order reactions are all about and how do we get the integrated rate equation for the first order reaction. That's important. My dear students, look at the definition. First order reaction, it is that particular reaction in which the rate of the reaction varies linearly with the concentration of reactant. Now, you must be thinking what is meant by that. For example, I'm taking a balanced chemical equation A gives B. Let's assume this is a balanced chemical equation whose rate constant, for example, is K. And at the same time, I'm assuming that the order of the reaction is 1, right? This is something which I'm assuming. Order of the reaction is 1. Now, my dear students, if I write the rate law for this particular reaction, how do I write it? I'll be writing rate of the reaction is equal to, it's going to be rate constant multiplied by concentration of A raised to the power order, that's 1. Okay. Now, my dear students, look at this particular expression. Look at this particular rate law. If you double the concentration of A, the rate of the reaction automatically doubles. If you triple the concentration of A, the rate of reaction automatically triples. If you make the concentration of A 4 times, the rate of this particular reaction will become 4 times. Any such reaction in which rate of the reaction varies linearly, with the concentration of reactant, we call that particular reaction as the first order reaction. Any such reaction in which rate of reaction varies linearly with the concentration of reactant, we call that particular reaction as the first order reaction, right? Very, very simple and basic. Perfect. If you double the concentration of A, the rate will double. If you triple the concentration of A, the rate will triple. If you make it 4 times, the rate will become 4 times. So rate is varying linearly with the concentration of reactant. Any such reaction in which rate varies linearly with the concentration of reactant, what do you call that reaction as? You call that particular reaction as the first order reaction, right? Now, my dear students, what exactly we are going to get? The way we derived the integrated rate equation for the zero order reactions, in the similar way, I'm going to derive an expression, which is what you call as integrated rate equation, which will be perfectly valid only for the first order reaction. And from that particular expression, you can solve almost all the questions. Let's try to derive that expression. That's important, right? Try to understand what I'm going to say. My dear students, the reaction is A gives B. It's a balanced chemical equation. That's something which I'm assuming. Now, at time t is equal to 0, let's assume the initial concentration of reactant is A0. This has to be 0. Now, you know, as the reaction proceeds, the concentration of reactant, it decreases with time. Let's assume at time t, the concentration of reactant left, that is 80. Let's assume that the concentration of reactant left in the container at time t, that is, for example, 80. And similarly, For example, the concentration of product formed at time t that I'm representing with Bt. So you have to be clear with all these terminologies first of all. So what is A naught? A naught is nothing. It is the initial concentration. It is the initial concentration of reactant. It is the initial concentration of reactant at time t is equal to 0, right? What is AT? AT is basically the concentration of reactant. It is the concentration of reactant left at time t. Similarly, what is BT? BT is the concentration of product. BT is the concentration of product formed at time t. Formed at time t. And what is K? K is the rate constant of the reaction. K is the rate constant of the reaction. And what about the order of the reaction? Order of the reaction which I'm taking over here, that's 1. Okay. Now try to understand. First thing, I'll be writing the rate law for this particular reaction. How do I write the rate law? Rate law for the reaction. Rate is equal to rate constant multiplied by concentration of A raised power 1. This is how you write rate law for this particular reaction because its order is 1. Now, my dear students, is there any other way to calculate the rate of reaction? Absolutely. You can calculate the rate of reaction with the help of differential form as well. You can calculate rate of reaction with respect to a reactant. It is just you have to start with minus sign, right? 1 divided by stoichiometry coefficient is 1. Okay, then it's going to be change in the concentration of A divided by dt. Perfect. Right. Now, my dear students, from this particular result, from this particular expression, I'm going to get one very, very, very important expression. And what is that important expression going to be? For that, I would need a new slide over here. Understand. What did I get? I got something like this. K multiplied by concentration of A raised power 1 is equal to minus times d of A divided by dt. This is something which I got till now. Perfect. Right? Now, dear students, try to understand few more things. I can write it like this as well. I can write it dA divided by dt. dA divided by dt is equal to minus times K, or let me write it like this, just a second. I can write it like this, minus, or leave minus aside, I can write dA divided by concentration of A. dA divided by concentration of A is equal to minus K multiplied by dt, right? I'm just separating the variables, nothing else. See, what did I do? I took this A in the denominator, took this dt over here, and it's going to be minus times. So dA divided by dt is equal to minus K dt. Perfect. Now, what exactly I'm going to do? I have to get the integrate rate equation. Dear students, I'll be integrating on both the sides. Over here, I'm integrating with respect to the concentration of A. And concentration of A, as you see, it is changing from A naught to AT. Concentration of A is changing from A naught to AT. And right here, I'm integrating with respect to time. And look at the time, from 0 to t, right? So the limits are going to be from 0 to t. Now, if you want to check whether the limits you have given, those are correct or not, look at this particular thing. At time t is equal to 0, the concentration of reactant was A naught. At time t, the concentration of reactant was AT. Perfect. Now, you must be knowing integral of dA divided by A. Integral of dA divided by A. What is it going to be? Integral of dx by x. That's going to be ln of x. Integral of dy divided by y. That's going to be ln of y. In the similar way, integral of dA divided by A. It's just going to be ln of A. It's going to be ln of concentration of A. Under the limits A naught to AT. And on right side, minus will come out, K will come out. Integral of dt is t, upper limit, lower limit, so it's going to be minus kt in short, right? Now, guys, give the upper limit, give the lower limit. It's going to be ln of AT minus ln of A naught is equal to minus kt, or you can write it like this. You can write it ln of AT is equal to ln of A naught minus kt. Well, this is the first way of writing the integrated rate equation for the first order reactions. This is the first way of writing the integrated rate equation for the first order reaction. In zero order reaction, it used to be AT is equal to A naught minus KT. And here in the first order reaction, it's going to be ln of AT is equal to ln of A naught minus KT. Correct? This is the first expression. Well, You can write the integrated rate equation in different formats as well. This is one of the format. This is one of the format in which you are writing the integrated rate equation. What about the other formats? Have a look. My dear students, how do you convert a ln into log? Instead of ln of 80, I'll be writing 2.303. It's going to be log of 80. This is how you convert a ln into log. As simple as that. Similarly, instead of ln of a0, I'll be writing 2.303. It's going to be log of a0. And with it, you have got minus kt as well. Yeah. Now do one thing. Divide throughout by 2.303. In this particular equation, if you divide throughout by 2.303, what do I get? I'll be getting something like this. Log of 80 is equal. It's going to be log of a0 minus k divided by 2.303 multiplied by t. This is one more way to write the integrated rate equation for the first order kinetics. One more way of writing the integrated rate equation. Log of 80 is equal to log of a0 minus k divided by 2.303 multiplied by t. So how many forms of integrated rate equation we got till now? This was the first form. This is the second form. Correct? First form, second form. I believe it's clear till here, right? I believe it's clear till here. Is it? Is it, guys? Is it clear to everyone quickly? Quickly in the chats. Yeah? Did you get to know how did we get these two equations? These are very, very, very important. There are some more ways to write the integrated rate equation for the first order reactions. Let's exactly have a look what those ways exactly are. And all the forms of integrated rate equation of the first order kinetics, they are very, very, very important. So you have to remember them one by one. First, ln of 80 is equal to ln of a0 minus kt. Second, log of 80 is equal to log of a0 minus k divided by 2.303 multiplied by t. Now let's have a look on few more expressions of the first order kinetics. Have a look, guys. Understand properly what exactly I'm going to say. If you look at this particular equation, the one which I'm representing with star, right? What exactly I'm going to do? I'm going to multiply this equation by minus. I'm going to multiply this particular equation by minus. Multiplying this equation by sign minus. It will come out to be ln of a0 minus ln of 80. It will come out to be equal to kt. It will come out to be equal to kt, right? Now, dear students, ln of m minus ln of n comes out to be ln of m divided by n, right? And this is equal to k times t. Perfect. Now you can write it like this. You can write k is equal to 1 divided by t ln of a0 divided by 80. This is one more expression, right? This is one more way of writing the integrated rate equation for the first order kinetics. So this is the third expression of writing the same thing. This is integrated rate equation. Even this is. These are the different formats of integrated rate equation. Nothing else. Okay. At the same time, this was the third expression. This was the third one. Now, my dear students, you can write the same equation like this as well. K is equal to. This form is in terms of ln. Now convert it in logarithmic form. So K is equal to. It's going to be 2.303 divided by t. Now it's going to be log of a0 divided by 80. This is the most important form of the integrated rate equation, which I'll be using in majority of the questions, and I'll be calling this expression as the fourth expression. So this is the fourth expression of writing the integrated rate equation, right? Is that it? No, that's not it. There is one more way. There is one more way, guys. Try to understand. Try to understand what exactly I'm going to do. If you look at this particular result, the star one, if you look at this particular result, the star one, ln of m minus ln of n, it's going to come as ln of m divided by n. So it's going to be ln of 80 divided by a0 is equal to minus kt, right? The base here is how much? The base here is e. The base here is e. So my dear students, how do I write it? How do you convert a ln into exponential form? How do you convert logarithmic form into exponential form? For example, you have got something like this. Ln of x to the base y is equal to z. Ln of x. For example, you have got something like this. Just a second. Ln of x to the base a, for example, is equal to z. How do I convert it into the exponential form? I'll be simply writing x is equal to e raised power z. I'll be writing x is equal to e raised power z. This is how you convert ln into exponential form. Correct? Similarly, you have got a similar type of equation like this. Ln of something to the base a is equal to minus kt. Can't I write Can't I write AT divided by A naught will be equal to e raised power minus KT? Absolutely, it will be e raised power minus KT. Now, why did I do it? Because I wanted to get one more equation, and the equation is something like this. Try to get it properly. The equation is something like this. I'll be writing AT is equal to A naught e raised power minus KT. This is one more expression. This is one more way of writing the integrated rate equation for the first order kinetics. So these are in total some 5 different forms by means of which you can write the integrated rate equation. Perfect. So is this clear till here, whatever I taught you? My dear students, you have to remember them. They should be on your tongue at every time. They should be always at the tip of your tongue. First one, in terms of ln of AT is equal to ln of A naught minus KT. Second one, log of AT is equal to log of A naught minus K upon 2.303 into T, right? Similarly, third one, K is equal to 1 by T ln of A naught by AT. Next one, K is equal to 2.303 divided by T log of A naught divided by AT. Next one, AT is equal to A naught e raised power minus KT. These are the different forms of the same equation. I hope I'm clear till here, yeah? Is it clear? Is it clear, people? Quickly. Right? I hope all these things are absolutely clear to you, right? So these are the equations which I want every one of you to remember, and all these equations are valid for the first order reactions. Where do we use them? How do we use them? That's a separate debate which I'll be letting you know in some time. But before talking about those things, till now, whatever equations I have given you, how do we make different types of graphs, right, for the first order reaction? Try to understand what exactly I'm going to say. Graphs which are based on first order reaction. Graphs are related to first order reaction. There are a lot of graphs, but right now I'll be showing some 4 to 5 graphs. The other graphs will be discussed too, but after some time. Okay? My dear students, the first graph which I'm plotting, that's going to be between rate of reaction versus concentration of reactant for the first order reaction. You should be able to make this particular graph on your own. You know, as far as the rate law is concerned for the first order reaction, R is equal to K, it's going to be concentration of A raised power 1. Now it's very simple. Rate of the reaction you are plotting along y-axis. Concentration of reactant you are plotting along x-axis. So this is your M. Y is equal to mx. Is it going to be a straight line passing through origin? Absolutely, it's a straight line passing through origin, right? If you ask me, what about the slope of this particular curve? Slope is basically M, which is K over here. Slope is represented by M, right? Slope is represented by M, and M is K in this particular case. So this is the first graph, which is perfectly valid for the first order reactions. Number 1. Number 2. For example, I am plotting one more graph. The graph has to be between ln of AT versus T. Ln of AT versus T. What is the equation? We know ln of AT is equal to ln of A naught minus KT. So this is the equation, correct? Ln of AT you are plotting along y-axis. So instead of ln of AT I'm writing y. Time you are plotting along x-axis. So instead of T I'm writing x. So this is your M. The sign here is minus, and this whole term is going to be your C. And over here you've got equal sign, and this has to be plus. So y is equal to minus mx plus c. Y is equal to minus mx plus c. What is the nature of the curve? Minus mx plus c, the curve will be like this, right? What about the slope of this particular curve? Slope of this particular curve directly is equal to minus k. And if you ask me about the intercept, the distance from the origin to the point from where the curve starts, intercept, which is denoted by c, that's actually equal to ln of A naught. So this is one more graph, which is perfectly valid for what? It is again valid for the first order reactions, right? Now, my dear students, for example, you are plotting one more graph. The graph is between log of AT versus T. Log of AT versus T. One equation I gave you a few minutes back. That was the log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This was the equation which I gave you a few minutes back. Now try to understand. Log of AT you're plotting along y-axis is equal to this time you're plotting along x-axis. So this is your x. So this whole term has to be your minus m. This whole term is equal to minus m. And this is basically c. The sign over here is positive. So it's again y is equal to minus mx plus c. So minus mx plus c graph is like this. So what about the slope of this particular curve? Slope of this particular curve, as you can see over here, it is minus k upon 2.303. What about the intercept? Intercept is basically represented by c, and c value is nothing, that is log of a naught. So this is one more graph which can be asked in the question, right? This is one more graph which can be asked in the questions. And I'll show you the questions after some time, but there are a lot of other things which needs to be discussed too. Okay, let's try to complete everything step by step. Now we will at the same time. For example, you have to make a graph. The graph is between AT versus T. The graph is between AT versus T, right? Few minutes back only I gave you one equation. I told you AT is nothing, that is A naught e raised power minus KT. AT is equal to A naught e raised power minus KT, right? Now, as you can see over here on this curve, AT you are plotting along which axis? AT you are plotting along y-axis, right? This is going to be y is equal to A naught, that's a constant, for example, k, e raised power minus e raised power minus kt. T you are plotting along x-axis, so it's going to be e raised power minus x format. Y is equal to k e raised power minus x format. Do you remember what will be the nature of the curve? Do you remember what will be the nature of the curve? Y is equal to e raised power minus x type. Y is equal to e raised power minus x. Is it going to be the exponential decrease form? Absolutely, it will be the exponential decrease form. It will be exponentially decreasing. Exponentially decreasing, right? And my dear students, this graph, it is not going to touch the x-axis. It is not going to touch the time axis. Why is that? There's a reason, which I'll tell you in some time, right? This is one more graph, which you have to remember for the first order reaction. AT versus T. It's exponentially decreasing curve, right? But do remember this particular graph, it's not going to touch the time axis over here. What is the logic behind that? Why it's not going to touch? There's a reason, which you'll get in some time, right? So these are the four graphs which I wanted to discuss with you, right, before doing the other things. Ln AT versus T, log AT versus T, then you have got rate versus concentration, you have got concentration versus time. So these are few graphs which you need to remember, okay? And directly questions will be asked from these graphs. Directly questions will be asked from these graphs. How exactly? Again, you'll see that in some time. Now try to understand few more important features of the first order reactions. So till now, I only talked about the integrated rate equation, right? Integrated rate equation I taught. Second, my dear students, the second parameter, that is the half-life. Half-life. Do you remember how did we define the half-life? The time taken to complete 50% of the reaction. The time taken to complete 50% of the reaction. Or you can define it, the time in which the concentration of reactant reduces to half. The time duration in which the concentration of reactant reduces to half, right? Or you can simply say the time duration in which the concentration of reactant reduces from A naught to A naught by 2, right? Let's try to understand what this half-life, how this half-life is calculated for the first order reactions. Try to understand. My dear students, we have got the reaction. A gives B, whose rate constant is K. Imagine that at time t is equal to 0, the initial concentration of reactant is A naught. Now what is going to happen with time? When the reaction proceeds, the concentration of reactant will keep on decreasing with time, right? The concentration of reactant will keep on decreasing with time. My dear students, at time t is equal to t half, at time t is equal to t half, when 50% of the reaction would have got completed, when 50% of the reactant would have got converted into product, can you let me know what will be the concentration of reactant left in the container? The concentration of reactant left in the container is simply going to be A naught by 2. Because 50% of the reactant has got converted into product. So this is the concentration of reactant left at time t. And the concentration of reactant left at time t, that is represented by what? That is represented by AT. So simply I got one condition over here. This is one condition which I got. At time t is equal to t half, AT value is equal to A naught divided by 2, right? Now dear students, if I use the integrated rate equation, do you remember this particular equation I told you a few minutes back? T is equal to 1 divided by K, ln of A naught divided by AT. This was one of the forms of integrated rate equation. My dear students, if I put this particular condition in this equation, if I put these conditions in the equation, what I'll get? So instead of T over here, I'll be writing T half. Instead of T, I'm writing T half is equal to 1 divided by K. It's going to be ln of A naught divided by AT value over here is equal to A naught divided by 2. AT value is equal to A naught by 2. So A naught gets cancelled. So you got to know T half is equal to ln of 2 divided by K. And ln 2 value you already know, that is 0.693 divided by K. So this is one expression which you need to remember, by means of which you can calculate the half-life of the first order reaction. So half-life for the first order reaction is ln of 2 by K, or you can say 0.693 divided by K. Whereas if you compare it with the zero order used to be A naught divided by 2K. T half is equal to A naught divided by 2K for zero order reactions. But here, as you can see, T half is equal to ln of 2 by K, or you can say 0.693 divided by K. Perfect. Now, my dear students, if you look at this expression, in this expression, do you see the A naught term? Do you see the initial concentration of reactant? No. So I would categorically say half-life of the zero order reaction. Half-life of the zero order reaction. Sorry, half-life of the first order reaction is independent. It is independent of the initial concentration of reactants. It is independent of the initial concentration of reactant, right? But it's valid perfectly for what? It's valid perfectly for first order reaction. Yeah? Right, people? Now, if I ask you to plot a graph, between T half-life of the reaction versus initial concentration of reactant, what will be the nature of the curve? Since I told you T half, it is independent of initial concentration of reactant. It is independent of any concentration term. So on changing the concentration of reactant, nothing happens to the half-life. It remains the same. It's constant. If you increase or decrease the concentration of reactant, nothing is going to happen to the half-life of the first order reaction. So this curve is valid for the first order reactions. Whereas if you remember your zero order reactions, T half used to be equal to A naught by 2K. And if you remember, when I plotted a graph between T half versus A naught for a zero order reaction, it used to be like this, whose slope used to be equal to 1 divided by 2K. This was for zero order reaction, but this is for first order reaction. You know it, right? Simple. So this was the half-life. Half-life expression I want you guys to remember from now onwards. T half is equal to ln 2 by K. It's equal to 0.693 divided by K. So this was the second parameter which I wanted you guys to remember. The third parameter. The third parameter for the first order reaction. What is that? That's completion time. What used to be the completion time in zero order reaction? It used to be A naught by K. How do we get the completion time in the first order reaction? This is important. Have a look exactly what I'm going to say. This is important. My dear students, you have got the reaction again A gives B, whose rate constant is K. Order of the reaction is 1. It's understood it's a first order reaction. Now at time t is equal to 0, assume that the initial concentration of reactant is A naught. So this has to be 0, right? Now with time, what is going to happen? With time, I must say, the concentration of reactant will keep on decreasing. With time, the concentration of reactant will keep on decreasing. If I say at time t is equal to t 100%, at time t is equal to t 100%, what is t 100%? The time taken to complete 100% of the reaction. The time taken to complete 100% of the reaction. The time duration in which 100% of the reactant would have got converted into product, right? The time duration in which the 100% of reactant would have got converted into product. So my dear students, at t is equal to t 100%. If 100% of reaction gets completed by chance, right? That means 100% of reactant would have got converted into product. So can I say the concentration of reactant left at that time will be 0, and the concentration of reactant left at any time is represented by AT. So I would say at time t is equal to t 100%, AT value should be equal to 0. The concentration of reactant left in the container should be 0, because I'm assuming that 100% of reactant has got converted. Yeah? I got one condition here. Condition is at time t is equal to t 100%, AT value is equal to 0. What does it mean? My dear students, use the integrated equation. T is equal to 1 divided by K. It is the ln of A naught divided by AT. right? If I put this particular condition in this expression, instead of t, I'll be writing t 100% is equal to 1 divided by k. It is the ln of a naught divided by, what is at? At value is 0. At value is 0. Division by 0 is infinite. So can I say this whole term will approach towards infinity? This whole term is approaching towards infinity. What does it mean? It means that a first order reaction takes infinite time to get completed. A first order reaction to get 100% completed will take infinite time, right? A first order reaction, it takes infinite time to get 100% completed. What does that mean exactly? That means a first order reaction, it never undergoes 100% completion. A first order reaction, it never undergoes 100% completion. Do you remember a few minutes back only I made one graph? The graph was like this. AT versus T. This was the graph. And the nature of the graph was like this. It was like this, right? This point represents time t is equal to 0. At time t is equal to 0, the concentration of reactant is A0. Now with time, the concentration of reactant is decreasing. I told you that this curve is not going to cut the time axis. Why? Because if this curve cuts the time axis, at that point, the concentration of reactant would become 0. That means the reaction has got 100% completed. But a first order reaction never undergoes 100% completion. So this particular graph, it is not going to cut the time axis. If it cuts the time axis, that tells you that the concentration of reactant has reduced to 0, right? Which is not possible. That means 100% reaction has got completed, which is not possible in case of the first order kinetics, right? So do remember, a first order reaction, it never undergoes 100% completion. This is one more important point which I wanted to share with you, right? Is it clear till here, people? Quickly. Is it clear till here? Quickly? Was this the fourth point? No, it was the third point. Now, let's talk about the fourth point related to the first order reactions. What is that? That is degree of dissociation. How do we get the degree of dissociation for the first order reactions? If you remember, in case of zero order reactions, we also calculated the degree of dissociation. It used to be equal to Kt divided by A0, right? Now let's get to know in the first order reactions how to get the alpha value. Let's get to know how do we get the alpha value. See guys, the reaction again which I'm taking, that's A gives B, whose rate constant is K. It's the first order reaction, right? At time t is equal to 0, the initial concentration, or you can say initial moles of reactants, that's A0, for example. Initial concentration or initial moles of reactant, that's A0. At time t, the concentration of reactant left or the moles of reactant left at time t, that's equal to AT. Correct? What do we need to get? I need to get the value of alpha. How do you get the value of alpha? What is alpha? Alpha is number of moles of reactant dissociated into product divided by initial moles of reactant, right? Alpha is equal to ND divided by NI. Number of moles of reactants dissociated into products divided by initial moles of reactants. Now, my dear students, if I ask you, how many moles of reactants have got dissociated into products? Initially, I started with A0 moles. I am left with 80 moles. So how many moles of reactants have got converted? It is A0 minus 80. So these are the moles of reactants basically which have got dissociated into products, right? Divided by, what is Ni? Ni represents initial moles of reactants. Initial moles of reactants are simply A0, right? Perfect. So my dear students, alpha is equal. It has to be A0 minus. What is 80? 2 minutes back only I told you the value of 80, which is A0 e raised power minus Kt, right? Divided by A0. My dear students, if I take A0 common in the numerator and denominator, A0 gets cancelled. I'll be getting the value exactly 1 minus e raised power minus kt. So this is the expression. This is the expression to calculate the degree of dissociation for the first order reaction, right? This is how you calculate the degree of dissociation for the first order reaction. Alpha is equal to 1 minus e raised power minus kt. And this particular result is valid for the first order reaction. If I ask you, what was the expression for zero order reactions? For the zero order reactions, alpha was equal to kt divided by a naught, if you remember, right? Now, my dear students, there is one thing which I want you guys to have a look on. In case of zero order reactions, alpha was dependent on the initial concentration of reactant. Here, alpha is independent of the initial concentration of reactant. So, do remember, take a note of this particular statement, that the degree of dissociation alpha is dependent or independent? Is independent. It is independent on the initial concentration of reactant, right? But it's valid only for the first order reactions. But in case of zero order reactions, it is absolutely dependent, right? Perfect. Now, again, one more thing. If I want you guys to plot a graph, between alpha versus a naught, in case of zero order reaction, it was rectangular hyperbola. But here, what will be the nature of the curve? I told you in case of first order reactions, if you increase or decrease the concentration of reactant, nothing happens to the value of alpha. The value of alpha will remain the same. This particular result, it's valid for, this particular graph is valid for the first order reaction. I hope this is clear to everyone, right? So this is how you get the degree of dissociation for the first order reaction. Is that clear? Let me know once in the chats quickly. Let me know once in the chats quickly. See, degree of dissociation of a zero order reaction, that depends on a naught. Whereas degree of dissociation for the first order reaction, it is independent. That does not depend on the a naught. Okay? Yes, Prajwal, you can go ahead with the doubt. What is the doubt? What is the doubt? So till now we are done with the 4 characteristic features of the first order reaction. The 5th characteristic feature which I'm writing on my own. What is that? The 5th characteristic feature I'm going to let you know. It is basically the time taken to complete X% of a first order reaction. The time taken to complete X% of the first order reaction. How much time does it take to complete a certain percentage of a first order reaction? For example, Prajwal, just wait for it. I'm going to derive that expression as well, right? I'm going to derive that expression as well. This is something which you were talking about, right? Is this the topic which you are waiting for? Time taken to complete X% of the first order reaction. That means time taken to complete, for example, 10% of first order, 20%, 30%, 50%, 60%. How do we calculate it? Try to understand. Or you can say time taken to complete a certain fraction of reaction. Yeah? Try to understand. My dear students, you have got the reaction A gives B, whose rate constant is, for example, K. And this reaction, it follows the first order kinetics. Initially, at time t is equal to 0, let's assume that the initial concentration of reactant is A naught. This is 0. This is something which I'm assuming. Now, my dear students, let's assume that X% of the reaction has got completed. The time taken to complete X% of the reaction, I'm representing that with Tx%. Time taken to complete X% of the reaction is equal to Tx%. Now, what does it mean that X% of the reaction has got completed? What does it mean? That means X% of the reactant has got converted into product. That means X% of reactant has got converted into product. So at time t is equal to Tx%, can you let me know the concentration of reactant left in the container? See, initially I started with A naught. This was my initial concentration. Now, X% of the reactant is getting converted. X% of the reactant is getting converted into product. So I'll be left with A naught minus X% of A naught. A naught minus X% of A naught. This is the concentration of reactant left at time t, which I'm representing with AT. Right? Now, let's get its exact value. So, A naught minus, this is going to be x divided by 100 multiplied by A naught. Or you can say, you can take A naught as common. You can take A naught as common. It's going to be 100 minus x divided by 100. This is equal to 80. This is equal to 80. So, at time t is equal to tx%, at time t is equal to tx%, this is the concentration of reactant left in the container. This is the concentration of reactant left in the container. Now do one thing, use the integrate rate equation. That is T is equal to, let's use this expression, 2.303 divided by K. It is the log of A naught divided by AT, correct? So I would say, if I use this particular condition, this is my condition, this is my condition. If I use this condition in this expression, then instead of T, I'll be writing Tx%. So time taken to complete x% of the reaction is equal to 2.303 divided by K. It's going to be log of A naught divided by, what is AT? AT is nothing, that's A naught multiplied by 100 minus x divided by 100, right? So A naught gets cancelled out. So time taken to complete x% of the reaction, it is always equal to 2.303 divided by K, and it's going to be log of 100 divided by 100 minus x. This is the formula. This is the expression which you guys are going to remember to calculate the time taken to complete x% of the first order reaction. Yeah? Right, people? Is it clear? So, my dear students, when do we use this particular expression? For example, you have to calculate the time taken to complete 10% of the first order reaction. You will just put the value of x as 10. You will just put the value of x as 10. Time taken to complete 20% of the first order reaction. Put the value of x as 20. Right? 30% of the reaction. Put the value of x as 30. You'll be getting the time taken to complete x% of the reaction. Yeah? Right, people? Perfect. Now, there is one expression here. There is one important thing which you need to understand here. In this expression, do you see the concentration of reactant anywhere? Do you see A naught anywhere? In this particular expression, do you see A naught term anywhere? Just tell me that. Just tell me that. You do not see A naught term here in this expression. What does it mean? It means that time taken to complete x% of the reaction, time taken to complete x% of the first order reaction, it is independent of the initial concentration of reactant. I'm going to write this particular expression here, or maybe I've already written it. Time taken to complete a certain fraction of first order reaction, or you can say indirectly, time taken to complete x% of the first order reaction. That is independent of the initial concentration of reactant. That is independent of the initial concentration of reactant. My dear students, this particular expression, this particular result, it has got significance as well. It has got significance as well. Try to understand its significance. For example, you have got the reaction like this, A gives B. See what this statement exactly means. You have got the reaction A gives B. Right? You have got the reaction A gives B. Let's say it's a first order reaction, first of all. Absolutely. It is a first order reaction. Now, guys, let's assume the initial concentration of the reactant here is, for example, 5 molar. The initial concentration of reactant is 5 molar. Here, I'm keeping the initial concentration of reactant as 10 molar. I'm keeping the initial concentration of reactant as 10 molar. Now, my dear students, for example, when the initial concentration of reactant is 5 molar, let's assume at that point of time, 10% of the reaction, 10% of the reaction is completed, for example, in 20 minutes. 10% of the reaction is, for example, completed in 20 minutes. Since time taken to complete a certain percentage of reaction, that's independent of initial concentration. No doubt you have kept the initial concentration of reactant as 10 molar here. But again, to complete 10% of this reaction, it will again take 20 minutes only. I hope you got this particular state. So time taken to complete a certain percentage of first order reaction, that is independent of initial concentration of reactant. No doubt you have kept the initial concentration different here, but time taken to complete a certain percentage of the reaction will be same in both the scenarios, no matter what the initial concentrations are, right? Right, people? Is it clear to everyone? Quickly. Is it clear to everyone? Do you know why did I give you this particular concept? Because there was a question asked long back in your JEE examination. and it's a proper NEET standard question. If you got the exact idea of what I said, you're not supposed to use any pen and paper in this question. You can solve it directly. Otherwise, it will take you like 5 to 6 minutes to do the calculations, etc., etc. Look at the question, tell me the answer. Look at the question and tell me the answer. Read the question carefully. The question is the catalytic decomposition of a reactant over gold. It is a first order reaction. So for example, you have got the reaction like this, A gives B. Let me not write the exact reaction, leave that aside. Let's say the reaction is A gives B, and it's following the first order kinetics. At the initial concentration of 200 molar, it was 73% decomposed in 100 minutes. So 73% of the reaction was getting completed in 100 minutes. 73% of the reaction is getting completed in 100 minutes, right? Now, my dear students, the question is, how much will it decompose in 100 minutes if the initial concentration was 600 molar? Now, imagine in the same reaction, you are taking the initial concentration as 600 molar. Imagine in the same reaction, you are keeping the initial concentration as 600 molar. Now, he's asking you, in 100 minutes of time, how much reaction would have got completed? Same 73% of the reaction would have got completed. So the answer is 73%. Because I told you a few minutes back, taken to complete X% of the first order reaction. It's absolutely independent of the initial concentration of reactant. Whatever initial concentration you want to keep it. Nothing will happen with the time taken to complete a certain percentage of the first order reaction. Yeah? Is it clear to everyone? So my dear students, this was our fifth parameter for the first order reactions, right? Fifth parameter. Now we have got few more expressions which I would want you guys to remember directly. I'm not going to derive the expressions. I want you guys to remember the expressions and try to use them in the questions. See. Now our sixth parameter for the first order reactions. What is that? Time taken to complete. 75% of the first order reaction. How do you get the time taken to complete 75% of the first order reaction? Do remember, there are few expressions which I want you guys to remember directly. No need of derivation, etc., etc., right? So the first expression is time taken to complete 75%. Time taken to complete 75% of the first order reaction. It is 2 times the half-life. It is equal to 2 times the half-life. Time taken to complete 87.5% of the first order reaction. It is 3 times the half-life. And time taken to complete 99.9% of the first order reaction. It is 10 times the half-life. And all these three expressions, these are valid only for the first order reaction. Do you remember them? With the help of these particular results, you can solve the questions in lesser time. Right? The first one. Time taken to complete 75% of the first order reaction. That's 2 times half-life. 87.5% of the reaction. That's 3 times half-life. 99.9% of the reaction. That is 10 times half-life. Even you can derive these expressions as well. Right? The expression which I gave you a few minutes back. Time taken to complete X%. You just have to put the value of X as 75. Then you have to put the value of X as 87.5. Then you have to take the value of X as 99.9. Eventually, you'll get the result. Right? But nothing to do with the derivation. Just remember these results. So this was our sixth parameter related to the first order reactions. Now, let's have a look. Where do we use this? Let's have a look. Where do we use all these results? Few questions will do. Then there are few more parameters related to the first order reaction. It's not done yet. Right? There are few more parameters. But before talking about that, let's try to solve some basic questions. The question is, a first order reaction is 75% completed in 100 minutes. So you have got a first order reaction. And it's mentioned that the first order reaction is 75% completed. In how much time? A first order reaction is 75% completed in 100 minutes. He's asking you, calculate the time taken to complete 87.5% of the reaction. This is something which we are supposed to calculate. Isn't it very simple? See guys, time taken to complete 75% of the first order reaction. That's 100 minutes. And you know, this particular thing, it is equal to 2 times the half-life. So 2 times T half is nothing, that's 100, correct? So from here, you can calculate half-life, which comes out to be 50 minutes. So you got the half-life of the reaction first of all. Why do I need the half-life? Because I'm supposed to calculate the time taken to complete 87.5% of the reaction. You know, it is always equal to 3 times half-life for the first order kinetics. Since half-life you already calculated, that's 50 minutes. The value overall comes out to be 150 minutes. So I'll say 87.5% of the first order reaction will get completed in 150 minutes. I hope this is clear to everyone. I hope this is super clear to everyone, right? Right, people? Let's do a few more questions. Then we'll move on to a few more topics. Then we'll move on to basically a few more characteristics of the first order, right? Look at this particular question. The question says for an elementary reaction, X gives Y plus Z. Half-life is equal to 10 minutes. In what period of time would the concentration of X be reduced to 10% of the original value? Right? Are you understanding this particular question? See, as per the question is concerned, we are given the reaction X gives Y plus Z. It is not mentioned in the question whether the reaction is zero order, whether it's first order. It's not mentioned. But there is one statement that's mentioned. The reaction is elementary in nature. If you remember, I have told you, in case of the elementary reactions, molecularity is always equal to order. Right? Do you remember? In the last session only I have told you. In case of the elementary reactions, order is equal to molecularity. What is the molecularity of this reaction? Molecularity of this reaction is 1. That means the overall order of this particular reaction, it has to be 1 as well. So it's a first order reaction. It is a first order reaction. Yeah? Right? Nikhil, syllabus I'll be giving in the Telegram group. Right? Tonight. Telegram group. Okay. The reaction which is given to us, its half-life is equal to 10 minutes. Its half-life is equal to 10 minutes. Now, you know, half-life is nothing. It is 0.693 divided by K. That is basically 10 minutes as per the question. So, K has to be equal to 0.0693. And its units are going to be simply minute inverse. Right? So, this is the rate constant. I first of all calculated the rate constant with the help of half-life. Now, what are we supposed to calculate? In what period of time would the concentration of X be reduced to 10% of its original value? Right? So indirectly, he's asking you how much time will it take for the reaction to get 90% completed. Do you agree with this? Indirectly, he's asking you how much time would it take for the reaction to get 90% completed. Because when the 90% of the reaction will get completed, that means 90% of the reactant will get converted into product. At that point of time only, 10% reactant will be left in the container. 10% reactant left in the container means 90% reaction completed, right? So he's asking you the time taken to complete 90% of the reaction. So time taken to complete 90% of the reaction will be equal to 2.303 divided by T. It's going to be log of, you can write 100 divided by 100 minus X. 100 minus X, and X is 90. So this is 10, 100 divided by 10 is 10. So you can say time taken to complete 90% of the reaction is equal to, sorry, this is K here. This is K here. So it's going to be 2.303 divided by K. K value already we have calculated 0.0693 and it's log of 10 and log of 10 is 1. So you just need to do a bit of calculation and you'll be getting the time taken to complete 90% of the reaction. Yeah? Is it clear? It's simple, guys, right? So the answer at the end of the question will be 33 minutes. So it will take approximately, not approximately, it will take exactly 33 minutes to complete 90% of the first order reaction. Yeah? Sir, who will teach atomic structure and periodic classification? I will teach atomic structure and periodic classification. No need to worry. Okay? Even I'll teach few chapters of organic as well. Okay, because physical almost we are done with, right? Physical almost we are done. Yeah? Even chemical bonding is also done. Inorganic one chapter is also done. Perfect. So this was the first question, which I gave it to you. All right. Look at this particular expression. Look at this particular expression, my dear students. Look at this particular question. The question is, an organic compound undergoes a first order decomposition. Time taken for its decomposition to 1/8 and 1/10 of its initial concentration are T1/8 and T1/10 respectively. In this particular value. Okay. Have a look at this particular question. See. For example, the reaction is nothing, it is A gives B, whose rate constant is K, and the reaction follows the first order kinetic. Now, dear students, at time t is equal to 0, the initial concentration of reactant is A naught. This has to be 0. Perfect. Now, I'm defining two times. The first time is at t is equal to T1 by 8. This is the time at which the concentration of the reactant reaches to 1/8 of its initial value. So it's going to be A naught by 8. So at time t is equal to T1 by 8, the concentration of reactant left is equal to A naught divided by 8. Right? Similarly, at time t is equal to T1/10, the concentration of the reactant reaches to 1/10 of its initial value. So the concentration of reactant left is going to be A naught by 10. So this is the concentration of reactant left at time t is equal to T1/10. Right? So basically, what did I get? I got two conditions. At time t is equal to T1/8, this is the concentration of reactant left in the container. And similarly, at time t is equal to T1/10, this is the concentration of reactant left in the container. Oh, how many conditions do I have? I've got two conditions. I got two conditions basically. Yeah? I got two conditions basically. Now, my dear students, I'll be using these conditions in the integrate rate equation. Let's see what do we get. Let's see what do we get. If you remember, already I have given you one expression. T is equal to 0.303 divided by K. It's going to be log of A naught divided by AT. Do you remember this particular expression? Do you remember this particular expression? It is valid for the first order reactions. Now, in this expression, my dear students, I'm going to introduce these two conditions. Introducing first condition in this expression, instead of T, you'll be writing T1/8 is equal to 2.303 divided by K. It is log of A naught divided by. What is AT value here? AT value is A naught by 8. Perfect. So can I say A naught and naught cancel? 8 comes up. 8 can be written as 2 raised power 3. 8 can be written as 2 raised power 3 here. 2 raised power 3. It can be also mentioned as log of m raised power n, n log m. So 3 comes to the front, then it's going to be log 2. So 3 comes to the front, then it's going to be log 2. 3 comes to the front, log 2. Log 2 is nothing, that is 0.3. Correct? So this one equation which I got. Now, if I introduce second condition in the given equation, so instead of T, I'll be writing T1/10. T1/10 is equal to 2.303 divided by K. It's going to be log of A naught divided by, what is AT? AT is A naught by 10. AT is A naught by 10. A naught don't cancel, 10 comes up. Log of 10 is 1, right? Log of 10 is 1. So this term is completely gone. So I got T1/8, I got T1/10. What exactly I'm supposed to calculate? I'm supposed to get the value of T1 by 8 divided by T1 by 10 multiplied by 10. This value I need to get. Tell me what is the value of T1 by 8? T1 by 8 is 2.303 divided by K. This will be 0.9, right? Whole divided by. What is the value of T1/10? It is 2.303 divided by K. Multiplied by what? Multiplied by 10. So this term is gone. 0.9 multiplied by 10, value comes out being 9. So 9 is going to be the answer of this question. Yeah? Is this clear to everyone? Is this absolutely clear to everyone? Quickly. Quickly, guys. One more question which we have on the screen. Let's give it a try. My dear students, as per this particular question, for a first order reaction, choose the correct value of half-life. Okay. We are supposed to get the half-life. We are supposed to get the half-life. The graph is given to me. Log of AT versus T. Log of AT versus T. This particular graph, the straight line with a negative slope, it is valid for which reaction? Zero order or first order? It is valid for first order, right? So, okay, it's mentioned in the question only. The reaction is first order, whose graph is given. The reaction is first order, whose graph is given. What do I need to calculate? I need to get the half-life. What is half-life all about? What is half-life all about? Half-life of the first order reaction is nothing, that is 0.693 divided by K. So basically, in order to get the half-life of the reaction, what do I need? I need the rate constant. Where do I get the rate constant? From this particular graph. I'm given the graph log T versus T. And you know, log T versus T, its slope, few minutes back only I've told you. Its slope will be equal to minus K upon 2.303. Right? What is slope? Slope is tan of theta. What is theta? Theta is the angle which this straight line mixed with the positive x-axis in the anti-clockwise direction. So this is the theta, right? So slope is tan of theta. Tan of what? Tan of theta, tan of 135, which is minus k upon 2.303. Now, my dear students, tan of 135, how much is that? That's minus 1. So minus 1 is equal to minus k upon 2.303. Or I can say k is equal to 2.303. Since time is given in minutes, so k units are going to be simply minute inverse, right? So k you got. Why did I get this k? Because I had to calculate half-life, right? So I would say half-life of this reaction is equal to 0.693 upon k, which is 2.303, right? Perfect. And it's minute inverse in the denominator. So I would say t half will come out to be how much? It will come out to be 0.3 minutes, right? So half-life of this particular reaction whose graph was given to us, it is simply equal to 0.3 minutes. I hope this is clear. I hope it's again clear to everyone. Yeah? Is it clear, people? Quickly. Is it clear to everyone? Let me know in the chats. Let me know in the chats. How many parameters, how many characteristics are we done with? We were, I think, done with 6 parameters, 6 characteristics of first order. Let's have a look on the 7th one. Let's have a look on the 7th one. Seventh one. The 7th parameter is calculation of the concentration. Calculation of the concentration of a reactant. Calculation of the concentration of reactant left after n half-lives. Well, there is one expression which I'm going to give you directly. Let's not derive that because that's going to be a wastage of time, nothing else. So I'll be giving you the expression, my dear students, and I'll show you how to utilize that expression. Yeah? Try to understand what exactly I'm going to talk about. Concentration of reactant left after n half-lives. Imagine that you have got a reaction A gives B. Imagine that you have got a reaction A gives B. I'm assuming it's following the first order kinetics. It is basically a first order reaction. It is basically a first order reaction, right? For example, just to make you understand. For example, half-life of the reaction is 10 minutes. Let's say half-life of this particular reaction. Let's assume that's 10 minutes. Okay? Let's assume that's 10 minutes. If I write T is equal to 20 minutes. If I write T is equal to 20 minutes. Can you let me know if half-life of this reaction is 10 minutes? Can you tell me how many half-lives this T is equal to 20 minutes will represent? See, half-life is equal to 10 minutes. So 20 minutes will represent how many half-lives? This 20 minutes, it will represent how many half-lives? It will represent 2 half-lives. Right? Simple. If I write T is equal to 30 minutes, so 30 minutes will represent how many half-lives? 30 minutes will represent simply 3 half-lives. Right? If I write T is equal to 100 minutes, 100 minutes will represent 10 half-lives. So first of all, how do we calculate the total number of half-lives? Total number of half-lives which I'm representing with n. Total number of half-lives I'm representing with n. It is always equal to total time T divided by T half. It will always give you the number of half-lives. It will always give you the number of what? It will always give you the number of half-lives, right? Okay. Now, I'm asking you to calculate the concentration of reactant left after n half-lives. How do we get it? I'm just going to give the expression. No need of derivation. AT is the concentration of reactant left after n half-lives is equal to A naught divided by 2 raised power n, where A naught is the initial concentration, right? And n stands for the number of half-lives. So this is one more expression which we'll frequently use in the equation. But this particular expression, where do we use it? This particular expression is used to calculate the concentration of reactant left after n half-lives. Perfect. It has got the derivation as well, but again I'm telling you, no need of derivation. Remember the result? do the questions from this particular result. That's it. Let's try to see certain questions first. Then you'll get to know where do we use this particular expression. This is the question. The question is, rate constant for the first order reaction is 1.386 minute inverse, right? So the units are minute inverse. That means the reaction must be first order. Okay. Calculate the concentration of reactant left after 8 minutes. Calculate the concentration of reactant left after 8 minutes. So T value is equal to 8 minutes. We have to calculate the concentration of reactant left after 8 minutes. Okay. Now, first of all, as per the question, rate constant of the reaction, that's 1.386 minute inverse. My dear students, if rate constant of the reaction is equal to 1.386 minute inverse, can you let me know what will be the half-life of the reaction? Half-life will be equal to 0.693 divided by K, and K is nothing, that is 1.386. So the value is equal to 0.5, right? Minutes. So this is the half-life. This is the half-life. Why do I need the half-life? Because I have to calculate the concentration of reactant left after 8 minutes. So let me exactly see how many half-lives these 8 minutes are. How many half-lives these 8 minutes are. So number of half-lives is total time divided by T half. Total time is 8 minutes. T half is 0.5. The value comes out to be 16. So basically, as per the question, I'm supposed to calculate the concentration of reactant left after how many half-lives? After 16 half-lives. And already you know the concentration of reactant left after n half-lives. That's equal to A naught divided by 2 raised power n. So the answer of this particular equation is going to be A naught divided by 2 raised power 16. So this is the concentration of reactant left after 8 minutes, or you can say this is the concentration of reactant left after how many half-lives? After 16 half-lives, right? Is that clear, people? Let me know in the chats quickly. Quickly, people. Is it clear? Okay, by the way, before solving the other questions, let me tell you one important thing. From 25th August till 31st August, there will be no session on YouTube. There will be no session on YouTube from 25th to 31st. So what we'll be doing in that week? No session. Be it chemistry, be it biology, be it physics, right? There'll be no session on YouTube from 25th August to 31st August. In this particular week, all the classes will happen on Unacademy platform. And these classes which are going to happen in Unacademy platform, these are what we call as special classes. Well, you must be thinking whether these classes are free or not. Absolutely, these classes are free, absolutely free for all. You just have to download. Your Unacademy app in the mobile or laptop, wherever you're seeing it, right? Download the Unacademy app. I'll be sharing the link of all the special classes which I'll be taking, right? I'll be sharing it in my personal Telegram group, right? And I'm sure all of you are already added in that, okay? Well, I have planned some 3 to 4 sessions, 3 to 4 special classes in this particular week, right? And whatever chapters we have completed till now on YouTube, like we have completed almost all the physical chemistry, right? From every chapter, I'll be doing some 100 top-notch questions, basically. We'll start with the mole concept, top 100 questions of mole concept, so that it'll be the revision and problem practice too. Similarly, the other chapters too, right? My first session on this Unacademy platform, right? In the special classes, it will be on 26th. 26th August, I'll be taking the first special class, right? Similarly, 29th August, I'll be taking one more special class. Similarly, 31st August, I'll be taking one more special class. These are the 3 special classes which I've planned, right? So I'll be doing some 100 questions in every session from the chapters which we have already covered. So that will be a problem practice as well as you'll remember the chapter properly. Is that cool? And tomorrow I'm going to take one special session at 10 p.m. on this channel in which I'm going to let you know the other things, the surprises which are going to be for all the NEET 2024 students as well. Yeah. Okay. But you have to join these sessions, my dear students, right? I'll share the link of the sessions in the Telegram. I hope you all are in my Telegram group, right? It is t.me/WASSIMSIRCHEM. Okay. Perfect. Surprise, you'll get to know tomorrow, not now. Surprise will be tomorrow. This particular week is going to be the problem practice week from the chapters which we have already covered on YouTube. Okay? Perfect. Look at this particular question. The question asks us, what amount of reactant for the first order reaction will be left after 3.5 minutes? We have to see the amount of reactant, the concentration of reactant left after 3.5 minutes. After 3.5 minutes. The graph is given to us. Ln 80 versus T graph. It is given to us. Why is it needed? Let's have a look. See guys. First of all, since I need to calculate the concentration of reactant left, 80. 2 minutes back only I told you 80 is nothing. That's A naught divided by 2 raised per n. A naught divided by 2 raised per n. What is n? N stands for number of half-lives, which is total time divided by T half. And what is total time? Total time is given to us as 3.5 minutes. So 3.5 divided by T half. Right? What is T half all about? T half is nothing. That is the ln of 2 divided by K. Perfect. Ln of 2 divided by K. So basically, I need to calculate the concentration of reactant left after 3.5 minutes. So first of all, I'll see exactly how many half-lives these 3.5 minutes are. Are these 2 half-lives, 3 half-lives, 4 half-lives? Accordingly, I'll use this particular result, right? And in order to get the number of half-lives, I should know the half-life of the reaction. In order to get the half-life, I should know the rate constant of the reaction. And rate constant of the reaction, I'll get to know from this curve. Ln 80 versus T. Do you remember what is the slope of this particular curve? Slope of this particular curve, ln 80 versus T curve. This is something which we have discussed already, right? It's minus K, correct? So my dear students, slope is what? Tan of theta. And which is theta? Which is theta here? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. This is theta. Now, if this is 45, this is 90, this is 45, so this has to be 135. So tan of 135 is minus 1. So minus 1 is equal to minus K. So K value is equal to 1 and it's going to be minute inverse. So we got the value of K. We got the value of K. K value is equal to minus 1, right? Sorry, K value is equal to 1. Ln of 2, we have to take as 0.7, 0.7 divided by 1. So this is the half-life. If this is the half-life, then this has to be 3.5 divided by 0.7. So number of half-lives came out to be 5. So indirectly, we have to calculate the concentration of reactant left after 5 half-lives, which is just going to be A naught divided by 2 raised power 5 molar. This is the concentration of reactant left after 5 half-lives, after 3.5 minutes. That's something which I was supposed to calculate, right? Let me know in the chats if all these things make sense to you, if they are clear to everyone. Quickly, people. Perfect, guys. Perfect. Okay. There is our one more Telegram channel. Just a second, guys. My wire is getting stuck. Okay. This is t.me/Unacademy NEET English. Unacademy NEET English. This is our official Telegram group, right? You can join this as well. I'll be sharing the link of this special class in this Telegram group as well, right? And one more is there. Again, I'm telling you, t.me/WSSIM right? That's mine. Any of the two you can join and get benefited. Okay, so I hope till here every single thing seems clear, right? Now guys, there is one more type of the question. There is one more type of the characteristic feature which you have to remember. That is going to be the 9th characteristic feature. Is it 9th or 8th? I believe it's 9th, right? 9th or 8th, whatever it is. So one more characteristic feature, one more type of the question which can be asked basically from the first order reactions. When the concentration of reactants at two different times are given, what it means exactly? Try to understand. I'm again not going to derive the result. I'll be giving you the result and I'll show you how to utilize that result. You are given with a first order reaction A gives B, for example, whose rate constant is how much? Whose rate constant is K. It's a first order reaction. Assume that. Now, for example, at time t is equal to 0, the initial concentration of reactant is A0. Let's say at time t1, the concentration of reactant left is 81. And let's assume when the concentration of reactant left is 81, at that point of the time, the rate of the reaction, that's R1, for example. Similarly, at time t2, the concentration of reactant left, that is 82, and let's assume that the rate of the reaction at this particular point is R2. It is R2. Be careful with these terminologies. At time t1, the concentration of reactant left is 81, and the rate of the reaction is R1. At time t2, the concentration of reactant left is 82, and the rate of reaction is R2. Right? I am, for example, asking you, how much time will it take? How much time will it take for the concentration of reactant to reduce from 81 to 82? That means I'm asking you this particular time interval, which is T2 minus T1. I'm asking you this particular time interval, which is T2 minus T1. Right? I hope you got it, what I said. I hope you got what I said. I'm asking you to calculate the time taken in which the concentration of reactant changes from 81 to 82. That means this particular time interval I'm asking you, T2 minus T1. How do we get this particular time interval? There is one result which I'm going to give you directly. You'll be remembering that from now onwards for all the first order reactions. The expression is K is equal to 2.303 divided by, it is T2 minus T1. Then we have log of 81 divided by 82. This one expression, or you can write it like this as well. 2.303 divided by T2 minus T1, it's going to be log of rate of reaction at time T1 divided by rate of reaction at time T2. So this is the expression which I want all of you to remember, my dear students. Yeah? No classes on YouTube from 21st August to 31st August. They already know it. I have told them there will be no classes. All the class will happen on the platform in the form of special classes, right? Okay, guys. Now let's exactly see how this particular expression is used in the questions. What kind of questions will be asked? See, for example, this is one simple question which I'm giving you, right? The rate of the first order reaction is 0.04 moles per liter per second at 10 minutes and 0.03 moles per liter per second at 20 minutes after initiation. Find the half-life of the reaction. The question is like this. The reaction is like this. A gives B, whose rate constant is, for example, K, and it's following the first order kinetics. Let's assume that at time t is equal to 0, the concentration of reactant is A0. Let's assume that at time t1, the concentration of reactant is, just a second. Let's assume that at time t1, which is equal to 10 minutes. At time t1, which is equal to 10 minutes, the concentration of reactant left, that is 81, and at the same time, the rate of the reaction, which I'm representing with R1, that's given to me as 0.04 moles liter inverse second inverse. There's something which is given to me. Similarly, at 20 minutes, it's mentioned that at 20 minutes, let's assume that concentration of reactant left is 82 and rate of the reaction at this particular point of time, it is given to me as 0.03 moles liter inverse second inverse. What are we supposed to calculate? We are supposed to calculate half-life of the reaction. How do we calculate half-life of the first order reaction? It is 0.693 divided by K. So basically we have to get the value of K. And how do you get the value of K here? 2 minutes back only I told you K is equal to 2.303 divided by T2 minus T1. It is the log of R1 divided by R2. I gave you this expression, right? Perfect. Two rates of reactions at two different times are given to us. So of course I'll be using this expression, right, to get the value of K. So K has to be equal to, it will be 2.303 divided by T2 minus T1 will be 10. Then it's going to be log of R1 by R2. R1 by R2, which comes out to be 4 by 3. So log of 4 by 3 is basically log of 4 minus log of 3. Log of 4 already you know that's 0.6. Log of 3 you know that's 0.47. Put it here, get the value of rate constant. Once you get the right value of rate constant, put it here and get the half-life. This is the general procedure, right? General procedure of solving this question. No need to think a lot about this, right? One more question. In what time will the molar ratio of ethylene to cyclobutane be 1? In what time will the molar ratio of ethylene to cyclobutane be 1? What it means exactly? Have a look. First of all, the reaction is C4H8 gives 2 times C2H4. He's asking you, in what time will the molar ratio of ethylene to cyclobutane be 1? See, let's assume that at time t is equal to 0. Let's assume that at time t is equal to 0. The moles of reactants are, for example, A. A represents the initial moles of reactant. This is, for example, 0, right? Now, for example, at time t, let's assume that out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles of reactant. Now use the stoichiometry. 1 mole of reactant gives 2 moles of product. So X moles are giving me 2X moles of product, right? So I assume the time t. At time t, the concentration of reactant left is A minus X. The concentration of product formed is 2X. Concentration or moles? Both are, I'm considering same over here, right? What do we have to calculate? At what time will the molar ratio of reactant to that of product? At what time will the molar ratio of product to that of reactant is equal to 1? So I'm assuming this is the time at which the ratio of the moles of product to that of reactant, that is equal to 1. So I'm assuming this is the time t at which 2x divided by A minus X is equal to 1, right? So from this particular result, I can say 2x is equal to A minus X, right? Or you can say X is equal to A divided by 3. X is equal to A by 3. Perfect. What do I need to calculate? I need to calculate this time. at which the ratio of the moles of products and reactants is equal to 1. Now what I'll be doing? Just use the integrate equation. We know T is equal to 2.303 divided by K. It is the log of A naught divided by AT. This is the integrated equation. Now, my dear students, T we have to calculate. T is this time which we have to calculate, right? It's equal to 2.303 divided by K value. What is K value? Given to me as per the equation, 2 into 10 raised power minus 4 log of A naught means initial moles here, which is A. AT means the moles of reactants left at time t, which is A minus X. So A minus A by 3, which comes out to be 2A by 3. So A cancelled, 3 comes up. It is log of 3 by 2, which makes it log of 3 minus log of 2. Log of 3 minus log of 2, right? So this term approximately cancels out. 10 raised power minus 4 comes up, becomes 10 raised power 4. Log of 3 is 0.47. Log of 2 is 0.3. The value here comes out to be how much? It comes out to be 1700 seconds. So my dear students, it will take 1700 seconds for the ratio of moles of product to that of reactant to be 1, right? This is something which I was supposed to calculate. I hope you got to know how to deal with this question, right? I hope you got to know how to deal with this particular question. This was one more good question, which I would say, right, that was given to us. Okay, one more question is there, but this will be the homework question. You'll do it on your own. There is one trick here in this question, guys. There is one trick here, right? Do not just go with the flow. There's a trick here in the question. There's a trick here in the question. You might have to use the equation P1 by P2 is equal to N1 by N2 as well, which we have studied in gaseous state. That is one more equation which you have to use in this question. Give it a try. I want you guys to use your brain at least, because if I solve all the questions, it won't make a sense first of all. Yeah. So you have to use the brain as well. So you have to give it a try after the end of the session. If you are unable to solve it, do let me know on my Telegram. I'll show you exactly how to deal with this question. Perfect. So this was your first order reactions. Now our next topic is going to be gaseous first order reactions. But before that, one more characteristic feature which I would want you to know so that you can solve the questions in lesser time. See, that is the ninth feature of the first order reaction. Ninth characteristic feature of the first order reaction. Try to understand. For example, I'm given with a reaction A gives B. Let's say I'm given with a reaction A gives B. Okay. Now, my dear students, try to understand what I'm going to say. This is the table which I'm getting, right? This is the table, for example. Here I'm mentioning time. Here I'm mentioning concentration of reactant. Concentration of reactant or pressure of reactant, for example. Now, my dear students, at time T1, let's assume the concentration of reactant was A1. At time T2, let's assume the concentration of reactant was A2. At time T3, let's assume the concentration of reactant is A3. At time T4, let's assume the concentration of reactant is A4, right? For example, in the same time interval. What does that mean? What does same time interval mean? Same time interval means that T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3, right? That means I'm talking about this time interval. Time interval everywhere is same. The time interval from T1 to T2 is same as that of T2 to T3 is same as that of T3 to T4. If, my dear students, in the same time interval, if in the same time interval, A2 divided by A1 value comes out to be same as that of A3 divided by A2, which comes out to be same as that of A4 divided by A3. What does it mean? It means that these concentrations at different times, they have got same common ratio. They have got same common ratio. What does that mean? That means the concentrations of reactants, they are forming, geometric progression. Whenever you see this kind of a scenario, in the same time interval, if the common ratio of the concentrations comes out to be same, that means if in the same time interval, the concentrations of reactants, they are forming the geometric progression. Remember, at that point of the time, the reaction which you have, it will be automatically following the first order kinetics. It is going to be a first order reaction. Where in case of zero order, they used to form arithmetic progression. Here they are not from the arithmetic progression. They are forming the geometric progression, right? Right, people? Is it clear to everyone? Is it clear to everyone? Okay, guys. So let's take a break till here. Let's take a break. And the time right now is 7:35. Let's take a half an hour break so that we'll have a proper rest and then we'll come back. Okay. So session resumes at perfect. Because I don't want myself to be tired, nor I want you to be tired. Right? Let's have some tea or something. Perfect. So you guys carry on till then. I'm giving you half an hour break. That's huge. First of all, I'll see you all at 8:05 with a new topic that's going to be kinetics of the first order gaseous phase reactions. Till then, you take care, right? Okay, see you at 8:05. But I want everyone to be back, guys, okay? Be back, be back. It's going to be fun. Is everyone back? Is everyone back? Is everyone back? Guys, can you all hear me? Am I again perfectly audible, visible to everyone? Let me know in the chats quickly. Quickly, people, quickly in the chats if all of you can hear me again. Quickly, let me know in the chats again if all of you can hear me. Yes, Meghna, yes. Perfect, guys. So, till now we are done with the first order reactions, right? The general first order reactions, their integrated rate constants, half-life, completion time, degree of dissociation, and the other parameters too. Now, my dear students, it's time for the kinetics of a gaseous first order reactions, right? This is again one important topic, and it's simple at the same time, right? So again, we'll be starting from the basics only so that you can understand this particular topic in detail with a proper understanding, okay? So first of all, imagine that you have got a reaction A gas, it gives B gas plus C gas. Let's assume this is a reaction. Imagine that it's a balanced chemical equation in which the stoichiometry coefficients are 1, 1, and 1, right? First of all, is the state of all the reactants and products same? Absolutely. The state of all the reactants and products is same. So this particular reaction, in which the state of all the reactants products is kept same, you call this particular reaction as the homogeneous reaction, right? And at the same time, the state of all the reactants products is gas in particular. So I'll be calling this particular reaction as homogeneous gaseous phase reaction. So it is the example of homogeneous gaseous phase reaction. My dear students, I'm assuming the order of this particular reaction as 1. I'm assuming the order of this particular reaction 1. If the order of this particular reaction is 1, then only I'll be calling this particular reaction as homogeneous first order gaseous phase reaction. So I'm assuming this particular reaction is the homogeneous first order gaseous phase reaction, right? Now try to understand what exactly I'm going to say. Something very important. My dear students, first of all, this particular reaction, it will be taking place in some container which is closed. For example, I've got a container which is closed on all the sides, and in that particular container, this reaction has to take place, correct? I am assuming this particular reaction taking place at constant volume and temperature. I'm assuming this particular reaction taking place at constant volume and temperature. Now, my dear students, if you use the ideal gas equation says PV is equal to nRT. I'm keeping volume and temperature constant. R is already constant, so I can say pressure is directly proportional to moles. What does that mean? That means if moles decrease, pressure will decrease. If moles increase, pressure will increase, right? And my dear students, if moles decreases, pressure will be decreasing. That means the proportion in which the moles will decrease, in the same proportion, pressure will also decrease. The proportion in which moles will increase, in the same proportion, pressure will also increase. What does that mean? Try to understand what exactly I'm going to say. My dear students, let's assume at time t is equal to 0. At time t is equal to 0, there will be only reactant present in the container, right? Because at time t is equal to 0, I'm assuming the reaction has not started yet. If the reaction has not started, there'll be no product formation. That means in the container, there'll be only a reactant, right? So at time t is equal to 0, we'll be only having gas A in the container, right? There'll be only one gas in the container at time t is equal to 0. That is gas A, right? So whatever will be the pressure of the container at time t is equal to 0, that pressure will be entirely due to A. Let's call that as P naught. P naught is the pressure at time t is equal to 0, which is particularly due to A. Since B and C is not formed yet, so pressure due to B and C, that is absolutely 0, right? Now, my dear students, what will happen when the reaction starts? When the reaction starts, the number of moles of reactant will keep on decreasing. Its number of moles of A will keep on decreasing. That means pressure due to A will also keep on decreasing, right? Since if moles of A decreases, pressure due to A, that also decreases. And the proportion in which moles of A will decrease, in the same proportion, pressure of A will also decrease. Now, my dear students, the treatment which we used to do with the moles, the same treatment we are going to do with the pressure as well. So let me assume at time t, the pressure due to A, it is going to be P naught minus X, because the pressure due to A has reduced by how much amount? By X amount, right? Now, imagine as if this is not pressure. Imagine it's moles. Now, 1 mole of A gives 1 mole of B. So X moles of A will give me X moles of B. Similarly, 1 mole of A gives 1 mole of C. X moles of A gives X moles of C. But is this X actually moles? No, it's pressure. So this P naught minus X, this is the pressure due to A. This is the pressure due to B. This is the pressure due to C. Right? Try to understand. At time t is equal to 0, there was only one gas in the container. At time t, there are 3 gases in the container. Right? There are some moles of A which will be there in the container. Some moles of B and C which would have got formed. So if I ask you whether at time t, is there only one gas or we have got a mixture of gas at time t? I would say at time t, we have got a mixture of gas. At time t, we have got a mixture of gas, right? My dear students, if I ask you, just a second, what just happened? Okay. So if I ask you, what will be the total pressure of the mixture at time t, which I'm representing with PT? PT represents the total pressure of the mixture at time t. Since at time t, there are 3 gases in the container. Gas A, there are some moles of gas B which have got formed, some moles of gas C. So there are 3 gases in the container. So the total pressure of the mixture at time t, that is absolutely going to be P naught minus X plus this X plus this X. Right? So I must say this X and X got cancelled. So I would say PT is equal to P naught plus X. Right? From this particular expression, can I get the X value? X value is equal to PT minus P naught. So first of all, I got the value of X. Right? Now people understand. Since it is the first order reaction, it is the first order gaseous phase reaction, right? Order of the reaction is 1. We know it. Order of the reaction is 1. A first order reaction never undergoes 100% completion. It takes infinite time to undergo 100% completion. So my dear students, at time t is equal to infinity, I would say 100% of the reaction would have got completed. So 100% of the reactant would have got converted into product, right? So will there be any reactant left in the container at t is equal to infinite? No, there is no reactant left in the container at t is equal to T infinity. So pressure due to reactant at t is equal to infinity will be 0. Now all the reactant has got converted into product at t is equal to infinity. So if I say 1 mole of A gives 1 mole of B, so from P naught, you will be getting P naught. Similarly, 1 mole gives 1 mole, from P naught, you will be getting P naught. Perfect. Now if I ask you, what is the total pressure of the mixture at infinity? Total pressure of the mixture at T is equal to infinite. It's going to be 0 plus P naught, which makes it 2 times P naught, right? So from this particular expression, you can say P naught is nothing. It is just P infinite divided by 2. So what is this P naught? Basically, I got the value of P naught exactly from here, right? I got the value of P naught from here, which came out to be P infinite by 2. Now you must be thinking, why did I do it? Why did I get the value of X? Why did I get the value of P naught? You have to remember this procedure, guys, first of all. You have to remember this procedure. Perfect. After writing all this stuff, now I'm going to do one thing. First, I'm going to write the rate constant. I'm going to write the rate constant in terms of, I'm going to write the rate constant in terms of PT and P naught. Let's try to write the rate constant expression in terms of PT and P naught. How do you write the expression for rate constant for the first order reaction? You know it. You know K is equal to 2.303 divided by T. It used to be log of A naught divided by AT, right? It used to be log of A naught divided by AT. But for this particular reaction, for this homogeneous gaseous phase reaction, if you want to write the rate constant, in terms of P naught and PT, how you are going to write it? You will be writing K is equal to 2.303 divided by T. It is log of, what is A naught? A naught is initial concentration of reactant. But here, I won't be using the term initial concentration. I'll be using the initial pressure of reactant. And initial pressure of reactant is P naught. So instead of A naught, I wrote P naught. What was this AT? AT used to be the concentration of reactant left at time T. The concentration of reactant left at time T. But here, AT won't be the concentration of reactant left at time T. It is going to be the pressure of reactant left at time T, right? Which is P naught minus X. So this is P naught minus X, right? So K value here will come out to be 2.303 divided by T. It's going to be log of P naught divided by P naught minus X. X value already we have calculated, that is PT minus P naught. So this is PT minus P naught. So my dear students, I got one important expression. Well, you are not supposed to remember this expression, but you should know exactly how to make this expression. That is important because question is directly asked. You will have to make this particular expression. So it will come out to be 2 times P naught minus PT here, right? So this is the expression of rate constant for the first order gaseous phase reaction in terms of what? In terms of P naught and PT. Again, I'm telling you, you're not supposed to remember this expression. You should be able to make this expression, right? Because if you change the stoichiometry, then absolutely on changing the stoichiometry, the expression will change. Now guys, one more question is asked. What is that? That is the rate constant in terms of rate constant value in terms of PT and P infinite. Rate constant in terms of PT and P infinite. Now you can easily check it out. Since already I have told you P naught is equal to P infinite by 2. Already I have told you P naught is equal to P infinite by 2. So wherever in this expression you are seeing P naught, just replace the value of P naught by P infinite by 2. So what do I get? I'll be getting K is equal to 0.303 divided by T. It is the log of. Instead of P naught, you'll be writing P infinite divided by 2. Whole divided by. It is 2 times. Instead of P naught, again P infinite by 2 minus PT. So K automatically will come out to be 2.303 divided by T. It is the log of. See, this 2 gets cancelled. So P infinite divided by 2 times P infinite minus PT. So this is the expression of rate constant in terms of PT and P infinite. These questions are directly asked you in the examination. And all these expressions are basically valid for this particular reaction, which is A gas gives B gas plus C gas. I hope you exactly got to know the procedure of getting the rate constant, right? Now I'll be giving you one more example, and with that example, I'm damn sure it will be absolutely clear to you. Let me know in the chats if all the things are clear. Let me know in the chats if all the things are clear, whatever I've told you. Quickly, people, everyone. Everyone. Guys, am I audible, visible to you properly? Okay, yes, perfect. All right, let me give you one more example. So basically, this was your expression which we got. What was P naught? P naught was the initial total pressure. PT is the total pressure at time T. P infinite is total pressure at the completion of the reaction. Okay, let me see one more example so that you'll understand it properly. See guys, you are given with a reaction. You have to get the rate constant in terms of P naught PT. That's the first question. The second question is get the rate constant in terms of PT and P infinite. Sorry, the second question is PT and P infinite. Right? These are the two questions basically. Now you should be able to form the rate constant expression. Right? And I'm sure you can easily do that. See what exactly you'll be doing. Let me write the reaction again. So 2 times A gas, it gives 3 times B gas plus 4 times C gas. It is the homogeneous gaseous phase reaction which will be carried out in some container which is closed on all the sides. At time t is equal to 0, there will be only a reactant in the container. So there is only one gas in the container at time t is equal to 0. So whatever is the pressure of the system at time t is equal to 0, that is due to A, which I'm representing with P naught. So pressure due to B and pressure due to C at time t is equal to 0, that's 0, right? Because the reaction has not started yet. Product formation has not been done yet, right? So there is only one gas in the container at time t is equal to 0, that is A. So whatever is the total pressure at time t is equal to 0, that is due to A, which is equal to P naught, right? Now, how we are going to treat the pressure? We are going to treat the pressure in the similar way as we used to treat the moles, right? Now, my dear students, at time t, pressure due to A has to be P naught minus X, right? Now, we use the stoichiometry. 2 moles are giving us 3 moles. 1 mole gives 3 by 2 moles of B. So, X moles are going to give us 3 by 2 multiplied by X moles of B. So, my dear students, this 3 by 2x, what is it actually? Actually, it is the pressure due to B at time t. Similarly, what is the pressure due to C at time t? Use the stoichiometry. 2 moles gives 4 moles. So 1 mole gives 2 moles. X are going to give me 2x moles. So what is this 2x basically? 2x is the pressure due to C at time t. Now, if I ask you one thing, at time t, how many gases will be there in the container? There will be 3 gases in the container. There are some moles of A which are left in the container, some moles of B which have got formed, some moles of C which have got formed. So at time t, you will find 3 gases in the container, right? So at time t, you are finding basically a mixture of gas. If I ask you total pressure of the mixture of gas at time t, total pressure of the gaseous mixture at time t, how much it's going to be? It's going to be P naught minus X plus 3 by 2x plus 2x, right? Perfect. If you take P naught on the other side, it's going to be PT minus P naught is equal to. Now take 2 as LCM. So this will be minus 2x plus 3x plus 4x, right? So you'll be getting PT minus P naught is equal to. This will be x plus 4x, which makes it 5x. So 5x divided by 2. From this particular expression, you can get the value of x. X value will be equal to 2 divided by 5 times PT minus P naught. This is our first step always to get the value of x, right? So what did we get? We got the value of x from here. We got the value of x from here, right? Now, my dear students, if I continue, if I write t is equal to infinity, right? First order reaction, it takes infinite time to complete. So t is equal to infinity. Pressure due to A will be 0. Now we use the stoichiometry. 2 moles are giving 3 moles. 1 mole gives 3 by 2 moles. From P naught, you get 3 by 2 P naught. This is the pressure due to B at t is equal to infinity. 2 moles gives 4 moles. 1 mole gives 2 moles. So P naught is going to give us 2 times P naught. This is the pressure due to C at infinity. So if I ask you, what about the total pressure of the system at infinity? Total pressure at infinite time will be equal to. Total pressure at infinite time will be equal to P divided by 2 P naught plus 2 times P naught, right? So P infinite is just going to be 3 P naught plus 4 P naught makes it 7 P naught divided by 2. From this particular expression, you can get the value of P naught, which is going to be 2 times P infinite divided by 7. So you got P naught in terms of P infinite as well. So all the things are done. Now we just have to write the expression of rate constant. First in terms of P naught PT and second in terms of what? PT P infinite. So my dear students, first of all, I'll be writing the rate constant. Rate constant in terms of what? Rate constant in terms of P naught and PT. Rate constant in terms of P naught and PT. How do I get this rate constant expression? It is simple. K is equal to 2.303 divided by T log of. It used to be A naught by AT. What was A naught? Initial concentration of reactant. But here I won't be using initial concentration of reactant. I'll be using I'll be using initial pressure of reactant, that is P naught, right? So it's initial pressure of reactant divided by. It used to be AT in the denominator. Concentration of reactant at left T. Concentration of reactant left at time T. But here I'll be using pressure of reactant left at time T, which is P naught minus 6. Already we have got the X value, if you remember. So it is 2.303 divided by T. It is a log of P naught divided by P naught minus X value. I believe I've already calculated 2 by 5 PT minus P naught. So this is 2 divided by 5 PT minus P naught. Correct? Well, you can further solve it a bit, cross multiple this a bit and get the exact value of K. Well, the value of K which you will get from here, it is 2.303 divided by T. Then it's going to be log of, this will be P naught divided by. It is 5 P naught minus 2 times PT plus 2 times P naught, and in the numerator you'll write 5. After doing the calculation, that's all. Right? So final expression of K has to be 2.303 divided by T. It is going to be log of 5 times P naught divided by 7 times P naught minus 2 times PT. Perfect. This is something which you were supposed to calculate. Expression of rate constant in terms of PT and P naught. So you got the expression of rate constant in terms of PT and P naught. I hope this is clear. Atomic structure will be done also. Just wait. After this chapter, maybe I'll start atomic structure. All right. What is the second part of the question? Second part of the question is calculate the rate constant in terms of PT and P infinite, right? Calculate the rate constant in terms of PT and P infinite. So what exactly you will be doing in this question? Already we have got the relation between P naught and PT. You know, P naught is equal to 2 by 7 P infinite. P naught is equal to 2 divided by 7 P infinite. So what you have to do just is, in this expression, wherever you see P naught, instead of P naught, you have to write 2 by 7 P infinite. You'll be getting one more expression of K. That will be in terms of what? That will be in terms of PT and P infinite. That's it. So P naught value, you have to substitute here. You'll be getting the exact value of K in terms of PT and P infinite. I hope this is clear to everyone. Can you let me know quickly in the chats? Can you let me know quickly in the chats if this is clear to everyone? Quickly, people. Quickly, everyone. Yes? I hope you can solve these sort of questions. Let me know quickly in the chats if all of you can solve these sort of questions. Perfect. Let me give you one more question. You're given the reaction. Assuming ideal gas behavior, calculate the order of the reaction. There is some table that's given to me. A table is given to me. From this particular table, we have to see the order of the reaction first. Few minutes back only I told you a way to check the order of the reaction from the table, right? First of all, I want you guys to see, is the time interval same? 0 to 100. That means the time interval here is 100 minutes, right? Then from 100 to 200, again the time interval is 100 minutes, right? So the time interval is same, right? So the time interval is same. If the time interval is same, now check whether the pressure of reactant is X, right? Whether the pressure of reactant, whether it forms GP or AP. Say, if I divide 400 by 800, the value comes out to be 1 by 2. Then if I divide 200 by 400, the value again comes out to be 1 by 2. So is the common difference same or common ratio same? In the same time interval, is the common ratio of the pressure of reactant same or common difference? It is the common ratio which is same. And in the same time interval, if the common ratio of the concentration of reactants or the pressure of reactants, if it is same, we say these pressures, they form the geometric progression, and geometric progression is formed in case of what? In case of zero order or first order. It is formed in case of first order reactions. So first question is done, order of reaction is 1. So we got to know that the reaction is of first order. This is the first order reaction, right? Now we have to calculate T half and T 75%. T half and T 75%. But before that, let's try to calculate the rate constant first. Let's try to calculate the rate constant. How do we get the rate constant? See, at time t is equal to 0, pressure due to reactant, we know, right? At time t1, pressure due to reactant is 400. At time t2, pressure due to reactant is 200. Perfect. Now, my dear students, you can choose any time interval. Let's assume I'm choosing this time interval. I'm choosing this time interval, 0 to 100 minutes. So this I'll be calling as A0. This I'll be calling as AT. As simple as that. Or you can call it as initial pressure. This is the pressure of reactant at time t. Right? Nothing I'm doing. Nothing extra I'm doing. Use the expression. K is equal to 2.303 divided by T. Time interval is 100 seconds, which I'm choosing. Log of. No matter if you are given with the pressure of reactant or concentration of reactant, you'll use the same thing. You'll use the same procedure, right? So it was supposed to be A0, initial concentration of reactant, but here I'll be using initial pressure of reactant, which is 800 divided by it used to be 80. Concentration of reactant left at time t, but here I'll be using the pressure of reactant left at time t. Perfect. This is time t is equal to 0. This is time t, right? So this has to be 400 because I've chosen this time interval over here. I've chosen this time interval. I hope you're getting it. So K value from here, I'll be getting 2.303 divided by 100. It's going to be log of 2. And log of 2, you know, that's 0.3. So multiplied it with 0.3. Perfect. So you'll be getting K. Well, if I ask you whether this is the rate constant of the reaction or not, the units are minute inverse. Whether it is the rate constant of reaction or not, if I ask you, what do you think? Is it the rate constant of reaction? My dear students, see, the stoichiometry here is 2. The stoichiometry here is 2. If the stoichiometry is not 1, if the stoichiometry of reactant is not 1, then I should be calling this as rate constant of disappearance of X. I hope you remember in the last session I've told you. I'll be calling this as rate constant of disappearance of X. Now, you know, rate constant of disappearance of X has to be equal to rate constant of reaction multiplied by stoichiometric coefficient of X. So from here, you'll be getting rate constant of reaction as Kx divided by stoichiometric coefficient. So it is 0.606 divided by 100, right? And divided by stoichiometric coefficient of X. That is 2. So it has to be 200. Now it's going to be minute inverse. Now this is the rate constant of the reaction. This is now the rate constant of the reaction. Yeah. Now you got the rate constant of the reaction. So rate constant of the reaction you calculate it. Well, after getting the rate constant of the reaction, calculate T half. How do you calculate T half? T half is equal to 0.693 divided by K reaction. K reaction already you have calculated, right? Put it here, get the T half. Calculate T 75%. T 75% is 2 times the T half. 2 times the T half. T half you have calculated from here. So you can calculate T 75% too, right? Total pressure when Px is equal to 700. This should be your homework. You should be able to solve this one as well. Total pressure of the system when Px is equal to 700. It's again simple. It's again simple, guys. Is it clear? Is it clear to everyone? Say yes or no in the chats quickly. Okay, let me show you the total pressure also. Total pressure when Px is equal to 700. See, you're given the reaction 2x gas, it gives 3y gas plus 2z gas. Initially at time t is equal to 0. Pressure due to x is 800. So this is 0, this is 0. Now, let's say at time t, pressure due to x is 700. Pressure due to x is 700. So how much is reduced? 100 is reduced. So x value is 700. X value is 100. Now see, 2 moles are giving 3 moles. 1 mole gives 3 by 2. So 100 is going to give us 3 by 2 multiplied by 100. Right? Simple procedure. 2 moles are giving 2 moles. 1 mole gives 1. So 100 gives us 100. Perfect. So this is 250. 50 into 3 is 150. So I would say total pressure of the system at time t will be equal to 700, which is pressure due to x, plus pressure due to y, that is 150, and pressure due to z, that's 100. So this is 850 plus 100, that comes out to be 950 mm of Hg. So this is the total pressure of the mixture at time t, right? When the pressure of the reactant left is 700. This was 800, left is 700. So how much has got converted? 800 minus 700, that's 100. So 100 mm of Hg has got converted. Or you can treat them as moles. Imagine this is 800 moles initially. Now how much is left? 700 moles. That means 100 moles have got converted. Now 2 moles gives 3 moles, 1 mole gives 3 by 2, 100 will give 3 by 2 into 100. You are going to treat pressure in the similar way as moles. No doubt you treated them like moles, but this is actually pressure. No doubt you treated it as moles, but this is actually pressure. So let me know once in the chat if this is clear. Let me know quickly, people. Will you be able to solve these sort of questions if they are asked? Will you be able to solve these sort of questions? Let me know once in the chat quickly. If these sort of questions are asked. Quickly, guys. Quickly. Yeah. I hope you got to know how to deal with these questions. Now there is one more topic. That is kinetics of a first order parallel reaction. So first of all, what is a parallel reaction? What is the first order parallel reaction? What all expressions we have to remember, and how do we deal with these parallel first order reactions? Let's get to know. Try to understand. My dear students, the reaction in which a reactant is involved in more than one first order reaction. In which a reactant is involved in more than one first order reaction. What is meant by that? For example, you have got a reaction like this. A gives B, whose rate constant is K1. Let's assume this particular reaction is a first order reaction. Let's assume it's a first order reaction. At the same time, this A is getting converted into C, rate constant K2. I'm assuming, for example, this reaction also is the first order. So how many reactions actually these are? These are 2 reactions. This one is the first order reaction. Even this one is the first order reaction. And one reactant, it is common in both the reactions. One reactant is involved in more than one reaction. One common reactant that's involved in more than one reaction. Whenever you see such kind of the reaction, in which one particular reactant is involved in more than one first order reaction, you call this particular reaction as the parallel first order reaction. You call this as the parallel first order reaction. So what is the parallel first order reaction? In which a reactant is involved in more than one first order reactions like this. For example, A gives B, this is one first order reaction, and A gives C, one more first order reaction. Correct? Let's assume the rate constant of this is K1, this is K2. A gives B, it is first order. A gives C, it's also first order. Perfect. Now guys, there are few things which you need to remember first of all. I'm not going to derive, I'll be giving the expressions and I'll show you how to solve the questions with those expressions. My first expression here is going to be to calculate the average rate constant of the reaction. Average rate constant of this parallel first order reaction. Let me tell you, average rate constant of the parallel first order reaction is the sum of individual rate constant. It is the sum of individual rate constant. Average rate constant of this parallel first order reaction. It is the sum of individual rate constants. Point number 1, right? Point number 1. Point number 2, my dear students. If you ask me what is the integrated rate equation for this parallel first order reaction, it is same. What was the integrated rate equation for the general first order reaction? K is equal to 2.303 divided by T log of A naught divided by 80, right? But here instead of K, I won't be writing K. I'll be writing K1 plus K2. So K1 plus K2 is equal to 2.303 divided by T. It's going to be log of A naught divided by 80. This is going to be what? This is going to be called as the integrated rate equation. This is the integrated rate equation for the parallel first order reaction like this. A gives B, A gives C. Okay. Just in place of K, I wrote K1 plus K2. Now, for example, if there was one more reaction, A gives D, whose rate constant was K3, then I was supposed to write K1 plus K2 plus K3. Okay. If you remember one more equation I had given you in the first order, AT is equal to A naught, e raised power minus KT. So instead of K, I'll be just writing K1 plus K2 multiplied by T, right? These are few equations which you are going to remember directly. No need for their derivation, right? Now guys, is that it? That's not it. That's not it. Let me tell you a few more things. Try to understand. At time t is equal to 0, let me assume. At time t is equal to 0, let me assume. Let me assume at time t is equal to 0, the moles of reactants, for example, are A naught. Let's say A naught represents the moles of reactant at time t is equal to 0. Right? Right? let's say A naught, it represents the moles of reactant at time t is equal to 0. Or you can say this is the concentration of reactant at time t is equal to 0. Because I'm assuming moles and concentration is same here. Right? I'm assuming moles and concentration is same here. So I'm assuming A naught represents the moles of reactant at time t is equal to 0. Or you can say A naught represents the concentration of reactant at time t is equal to 0. Correct? Now, my dear students, since the moles of reactant at time t is equal to 0 is A naught, moles of product at time t is equal to 0. That will be 0 also because the reaction has not started yet. Now, my dear students, what will happen with time? With time, the moles of reactants will keep on decreasing. With time, the moles of reactant will keep on decreasing. Let's say at time t, the moles of reactant left are 80. 80 represents the moles of reactant left at time t. And let me assume a term here, x. Let me define a term x here. Let's say x represents the number of moles or concentration of what? Of reactant. Of reactant, which got converted into products. Which gets converted into products. Which gets converted into products. Right? I'm assuming X are the moles of reactants which are getting converted into products. Now imagine how many moles you had? A naught. How many are we left with? 80. So A naught minus 80. A naught minus 80. A naught minus 80. Can I say A naught minus 80 gives me those moles of reactants which got converted into product? That's something which I call as X. So what is X? X is moles of reactant which got converted into product. Initially I start with A naught. I'm left with 80. So A naught minus 80. It gives me those moles of reactants which got converted into product. Right? Now, my dear students, there are few things which you need to know. What is that? See, at time t, there are some moles of reactant left. If I ask you what is product here in this reaction, I would say product in the reaction is B plus C. If you ask me what is product in the reaction, product in the reaction is B plus C. B plus C combinedly, I'm calling as product. B plus C combinedly, I'm calling as product. There are a lot of things which can be asked. There can be asked, calculate the moles of B which are formed at time t. Calculate the moles of B which are present in the container at time t. They can ask you, calculate the moles of C which are formed in the container at time t. How do we calculate moles of reactant left in the container at time t? How do we calculate moles of B which are formed at time t? How do I calculate moles of C which are formed? How do we do that? I'll be directly giving you one trick for their calculation. Try to understand what exactly I'm going to tell you. See guys, trick number one. Trick number one. For example, you have got the reaction like this. A gives B and at the same time A gives C. Its rate constant is K1, its rate constant is K2, right? At time t is equal to 0, the initial moles of reactants are A naught, right? At time t, the moles of reactants left are AT. Perfect. I'm defining a term X. What is X? X represents the number of moles. The number of moles or concentration of what? Of reactant. Of reactant. Converted into products. Converted into products. At time t. At time t. Try to understand. My dear students, if I ask you what are my products, if I ask you about the products, product at time t, product at time t, our product is going to be C and D. C and D combinedly I'm calling as product. C and D combinedly I'm calling as product. The first question that is asked, what is the percentage of B in the product? In the product. Calculate the percentage of B in the product. The product is B plus C basically, right? I'm asking you the percentage of B in the product. The percentage of B in the product. The product is C, the product, sorry, not B. Wait, C plus D. This is B plus C here, okay? Just, this is B plus C, right? B plus C combinedly I'm calling as product. The first question is asked, calculate the percentage of B in the product. Percentage of B in the product is simply written as K1 divided by K1 plus K2 multiplied by 100. This will be the first question which will be asked. Number one. Number two, percentage of C in the products. Percentage of C in the products. Percentage of C in the products. It is just going to be equal to K2 divided by K1 plus K2 multiplied by 100. This will give you the percentage of C in the product, right? Now they can ask you, what about the moles of B which have got formed at time t? What about the moles of B which have got formed at time t? Now, how you are going to write it? Moles of B formed at time t. It is going to be equal. First, you will start with K1 divided by K1 plus K2. Now, 1 mole of A gives 1 mole of B. Therefore, X moles of A would have got X moles of B. So this particular term is going to give us the moles of B formed at time t. Similarly, what about the moles of C formed at time t? Moles of C formed at time t. Start with K2. You'll be writing K2 divided by K1 plus K2. Now, 1 mole of A gives 1 mole of C. Therefore, X moles of A are going to give us X moles of C. So I got the moles of C formed at time t as well. Now, my dear students, if you divide the two, moles of B formed at time t divided by moles of C formed at time t. So X cancelled, K1, K2 cancelled. So I'll be left with only K1 divided by K2, right? These are few expressions which you should be able to make on your own. Right? Few expressions, important ones. Why are they important? Because I'll show you the questions after few minutes, then you'll get to know about their importance. Right? Perfect. Now, guys, if, for example, by chance, they play with the stoichiometry, let's say they give you a question like this. N1A, it gives N2B, and at the same time, N1A gives N3C. Let's say they are giving it a question like this. The rate constant of the first reaction is K1, rate constant of this reaction is K2. Right? Again, I'm assuming certain things. At time t is equal to 0. The moles of reactant is A0. At time t, the moles of reactant left are AT. Right? These can be moles, they can be concentration, they can be called as concentration, they can be called as pressure. The choice is all yours. Right? Try to understand what exactly I'm going to do. I'm defining a term X. What is X? X you already know. What is X? X are basically the moles of reactant. X you can call either as moles or concentration or pressure. I'm right now calling it as moles. Moles of reactant getting converted into products. Moles of reactant getting converted into what? Into products. At what time? At time t. Now try to understand. The first question which will be asked. Calculate the percentage of, or leave the percentage aside. Tell me one thing. Moles of B which have got formed at time t. Moles of B or concentration of B formed at time t. You'll start with K1. Divided by K1 plus K2. Now, N1 moles are giving me N2 moles. N1 is giving me N2. So 1 mole gives me N2 divided by N1. So X moles of A are going to give me N2 divided by N1 multiplied by X. Right? Stoichiometry, that's it. Similarly, moles of C which have got formed at time t. Start with K2. So K2 divided by K1 plus K2. Now use the stoichiometry. N1 moles are giving N3 moles. So 1 mole gives N3 divided by N1. So X moles are going to give us N3 divided by N1 multiplied by X. Right? Okay. Now at the same time, if you divide them up, moles of B at time t divided by moles of C at time t, what I'll be getting? I'll be getting N2 times K1 divided by N3 times K2. Perfect. If they ask you, what is the percentage of B in the products? Calculate the percentage of B in the products. How you are going to do it? Percentage of B in the products. What is there in front of B? N2K1. So you'll write N2K1 divided by N2K1 plus N3K2 multiplied by 100. Right? This will give you the percentage of B in the products. If they ask you about the percentage of C in the products, at time t, for example. See, in front of C, what do you have? N3K2. So you'll write N3K2 divided by what? Divided by N2K1 plus N3K2 multiplied by what? Multiplied by 100. This will give you This will give you the percentage of C in the products, right? Perfect. So my dear students, these sort of questions can be asked, right? Well, I did not derive them. I'm just giving you the tricks to solve the questions. That's all. Let's try to see exactly what kind of questions can be asked out of these parallel first order reactions. Understand and see how we are going to deal with the questions. Try to understand, guys. Just a second. This is the first question. This is the first question. It is the simplest among all because the stoichiometry is 1:1:1. K1, K2 is also given to us. Calculate the percentage distribution of B and C in the products. My dear students, since the stoichiometry is 1:1:1, what about the percentage of B in the products? Percentage of B in the products. Since the stoichiometry is 1:1. When the stoichiometry is 1:1:1, when the stoichiometry is 1:1:1, 1:1:1, how do we get the percentage of B in the products? K1 divided by K1 plus K2 directly, right? So it is going to give B. It is going to be K1 divided by K1 plus K2 multiplied by 100. Correct? Now K1 value 0.693, right? K1 plus K2 0.693 plus 0.1386 multiplied by what? Multiplied by 100. Now 0.693 I'm writing as such. In the denominator, if I take 0.693 common, it's going to be 1 plus 2 multiplied by 100. So this term got cancelled. It is 1 divided by 3 into 100. The value comes out to be how much? The value comes out to be 33%, right? Right? 33%. So percentage of B in the products is coming out to be how much? It is coming out to be 33%. Yeah? Right, people? You got the percentage of B in the products. In the products, there won't be only B. There'll be C also, right? If they ask you about the percentage of C, which they have asked, percentage of C in the products. What about the percentage of C in the products? It's going to be 100 minus 33, which comes out to be 66%. This is the percentage of C in the products. Percentage of B, percentage of C in the products. Right? Is this clear to everyone? This is one type of the question. This is one type of the question. Right, people? Let's see the other types of question as well. Just a second. For example, look at this question. Look at this particular question. You should be able to solve this question. You see the question first, and then I'll see some other questions. Quickly. Can you give it a try? See guys, on starting with 2 moles of A, calculate the total moles after 75% completion. See, as per the question, the reaction is like this. A gives 2 times B, and at the same time, A gives 2 times C as well. Rate constant of this reaction is K1, rate constant of this reaction is K2. On starting with 2 moles of A, so initially at time t is equal to 0, how many moles of reactant we have? We are given with 2 moles of reactant. We are given with 2 moles of reactant, correct? 2 moles of reactant we have. So at time t is equal to 0, the moles of B and C formed, that will be absolutely 0, right? Because the reaction has not started yet. Now guys, calculate the total moles after 75% completion. What is meant by 75% completion? That means 75% of A has got converted. What is 75% of A? What is 75% of 2? 75 divided by 100 into 2. How much is that? 1.5 moles. So out of 2 moles of A, I would say 1.5 moles have got converted into products. So I'll be left with 2 minus 1.5. 2 minus 1.5 is 0.5. So these are the moles of A left in the container after 75% completion. If I ask you, what about X value? What is X? Moles of reactant which get converted into product. So I had 2 moles. Now 75% of 2 is getting converted into product, right? So that means 1.5 moles have got converted into product. So x value is equal to 1.5. So you got the value of x first of all, right? Now, at time t is equal to T75, the moles of reactant left in the container are 0.5. Now, there will be few moles of B and C also, which would have got formed at T75%. Absolutely. Now, calculate the moles of B at time t, which have got formed. Calculate the moles of B at 75% completion. See, how exactly? You know it. Start with K1 divided by K1 plus K2. Now use the stoichiometry. 1 mole of A gives 2 moles of B. If 1 mole of A gives 2 moles of B, that means x moles of A are going to give us 2x moles of B, right? Similarly, moles of C at time t. Moles of C at time t, it is going to be equal, start with K2. So it's K2 divided by K1 plus K2. K2 divided by K1 plus K2. Now, 1 mole gives 2 moles. So from x moles, you are going to get 2x. Perfect. Right, people? Now put the values and get the answer. See, K1 by K2 is 1 by 2. So this is 1 divided by 1 plus 2 multiplied by 2x. 2 into x is 2 into 1.5 is 3. So this is 3 divided by 3, which comes out to be 1. Right? Similarly, K2 value, this will be 2 divided by 1 plus 2. 2 into x is 3. So 3 2s are 6. 6 divided by 2 is 6 divided by 3 is, for example, 2. Right? So my dear students, if I ask you, when 75% reaction is completed, which all components are there in the container? There are some moles of A left in the container, some moles of B have got formed, and some moles of C have got formed. So how many total moles are there in the container when 75% of the reaction has got completed? Moles of reactant left, that's 0.5. Moles of B which have got formed, that's 1. Moles of C which have got formed, that's 2. So the final value comes out to be 3.5. I would say 3.5 moles will be there in the container in total when 75% of reaction would have got completed. Let me know in the chats if this is again clear to you. Is it clear? Is it clear, people, quickly? Yeah? Wonderful. All right, can you give this question a try? Can you solve this question? Initially, only A was taken at 8 atm. See guys, whatever treatment you do with moles, same treatment you do with concentration as well. Same treatment you do with pressure as well. Right? Same treatment, no change at all. Right? Assume moles is equal to concentration is equal to pressure. Same treatment everywhere. Look at this question. We are given the reaction A gives B, A gives C, and at the same time A gives D. K1, K2, K3 are given to us. K1, K2, K3 are given to us. Initially, only A was taken at 8 atm. So at time t is equal to 0. At time t is equal to 0. At time t is equal to 0, the pressure due to A, which I'm representing again with A naught, it's 8 atm. It is pressure due to A. So pressure due to C and D, pressure due to B, C and D, that will be 0 because the reaction has not started yet. Now, my dear students, the partial pressure of B after 100 seconds. The partial pressure of B after 100 seconds. So, first of all, you know when the reaction will start, the moles of A will keep on decreasing. The moles of B, C and D will start to increase, right? So, at 100 seconds, there will be some moles of A in the container. Moles of B, C and D will be there in the container. So, basically, at 100 seconds, there will be 4 gases in the container. Gas A, some moles of gas A left, some moles of gas B formed, gas C formed, gas D formed. So there are 4 gases in the container. So there will be a gaseous mixture present in the container at 100 seconds. Right? There will be a gaseous mixture present in the container at 100 seconds. Now you have to calculate. Let's assume that gaseous mixture will have some total pressure. The contribution made by gas B towards the total pressure of the gaseous mixture. The contribution of gas B towards the total pressure of the gaseous mixture is something which I call as partial pressure of B. And that partial pressure of B you have to calculate. And how exactly you'll be solving this. The partial pressure of B after 100 seconds. My dear students, first of all, K1, K2, K3 is given. Let's say I'm calculating average rate constant. What will be the average rate constant? This plus this plus this. If I take 10 raised power minus 3 common, right, it'll be 2 plus 3 is 5. 5 plus 1.93 is 6.93. So average rate constant came out to be 6.93. Average rate constant is coming out to be 6.93 into 10 raised power minus 3. Right? This is the average rate constant. If it is the average rate constant, can you calculate the average half-life? Average half-life is going to be 0.693 divided by K average. Simple. K average already you know. If you put the K average here, you got the answer as 100 seconds. Right? What is this 100 seconds? 100 seconds basically is the half-life of the reaction. 100 seconds is the half-life of the reaction. So basically what we identified that we have to calculate the partial pressure of B after 50% completion. We have to calculate partial pressure of B after 50% completion. It's a live lecture going on. It's not the recorded one. Okay. We have to calculate the partial pressure of B at half-life. So this 100 seconds is half-life. That means T 100 seconds means that 50% of reaction has got completed. When 50% of reaction got completed, that means 50% of reactant got converted into products. So tell me one thing. What will be the pressure of reactant left at T 50%? 8 by 2 is 4. So pressure of reactant left is 4 atm. Right? Because we are dealing with half-life right now. Correct, people? Correct? If I ask you what is the value of X? What is the value of X? X value used to be moles of reactant that got converted into product. But instead of moles, I'll be using pressure. So initially I had 8, now I'm left with 4. Therefore 4 atm has got converted. So X is 4 atm here. X is 4 atm. Now my dear students, try to understand. If I ask you what is the partial pressure of B at time T, that means T 50%, it's going to be equal to, first you'll write K1 divided by K1 plus K2 plus K3. This is the first step. Now, 1 mole of A gives 1 mole of B. Therefore, from X, you get X multiplied by X. Right? This is something which we need to calculate basically. So, partial pressure of B at time T is equal to 100 seconds is equal to K1 divided by K1 plus K2. K1 divided by K1 plus K2. Right? See, K1 value you have. K1 you have, K2 you have, K3 you have. Perfect? Right? Or let me just calculate it for you. K1 is nothing, that is 2 into 10 raised power minus 3 divided by it is going to be 6.93 into 10 raised power minus 3. The sum of them multiplied by X value is 4. So 10 power minus 3, 10 power minus 3 cancel. So it's going to be 8 divided by 6.93, which will be approximately 1.1 atm. So partial pressure of B, the contribution of B towards the total pressure of the mixture at 100 seconds will be exactly how much? It's going to be 1.1 atm. I hope this is clear to everyone. Yeah? Perfect, guys? I hope you can solve these sort of questions as well. Okay? One question I'm giving as the homework in this, or before giving you the homework question, one small topic is there which you need to know. Calculation of average half-life for the first order reaction. Calculate the average half-life for the first order reaction. See guys, for the first order parallel reaction basically, okay? Let's say you've got a parallel reaction like this, A gives B, A gives C, right? Its rate constant is K1, its rate constant is K2. Now first of all, average rate constant of this parallel reaction is going to be simply K1 plus K2. Perfect. It's going to be K1 plus K2. Now, my dear students, average half-life. Average rate constant. Can I write it as 0.693 divided by T half average? I can write it like this. Okay. What is K1? K1 can be written as 0.693 divided by partial half-life of the first reaction plus K2 can be written as 0.693 divided by partial half-life of the second reaction. So 0.693, 0.693 everywhere cancel. So you got to know 1 by average half-life will be equal to 1 divided by partial half-life of the first reaction plus 1 divided by partial half-life of the second reaction as well. Okay. So this is one more expression from which question can be asked. Right? This one more expression from which question can be asked. Okay. Right? From this particular expression, you can calculate the average half-life. Or my dear students, there can be one more expression. See, one more expression to calculate average half-life. The reaction, for example, is A gives B and A gives C. Rate constant of this reaction K1, this is K2. Now you know K average. That is nothing, that is K1 plus K2. Correct? Instead of K average, I can write 0.693 divided by average half-life, which is equal to K1 plus K2. So from this particular expression, you can also calculate average half-life. Average half-life of such reaction will be equal to 0.693 divided by K1 plus K2. Right? This is the average half-life of the reaction in terms of individual rate constant. So I'm writing it. This is basically the average half-life in terms of what? This is in terms of individual rate constants. Individual rate constants. And what was this one? What was this one? This is the average rate constant. Sorry, this is the average half-life in terms of partial half-lives. This is the average rate constant average half-life in terms of partial half-lives. Is this clear? Is this clear to everyone? You have to remove these two expressions as well, right? One question I'll be giving you as the homework. But before that, this is the expression which we have seen. Even this is the expression which we have seen. There was one question which I have kept as the homework for you, right? This was the question. Give it a try and you guys are going to let me know the answer of this question in the comment section afterwards. Okay, this is the question. This is your homework question. Average half-life is given. Percentage distribution of B in the products is given. Then the partial half-life of A. Simple question. It can be a bit lengthy, right? It can be a bit lengthy. Calculation must be involved here, right? But it's simple only. Yes, it's simple only. Calculation might be a bit tough, but it's doable. I mean, you should be able to do it after learning all the concepts which I told you. Okay. Okay, guys, is everything clear till here? See, average half-life is given. So you can calculate average rate constant from there, right? 0.693 divided by K. 0.693 divided by T half average, right? Then K average will be equal to K1 plus K2. Percentage of B in the products is given. That means 2 times K1 divided by 2 K1 plus 3 K2. 2 K1 divided by 2 K1 plus 3 K2 into 100 is given to us as 50. It's a simple question, guys, right? Order I have discussed in the second part of the kinetics chapter. Will you be able to do this question? Say yes or no in the chats once. Then only I'll move ahead quickly. I want everyone to say it quickly. Will you be able to solve this question? Okay, so we are done with the parallel first order reactions. Now, let me tell you one more important thing. From which question is asked frequently? From which question is asked frequently? That is order of the reaction. Order of the reaction from half-life. How do I calculate order of the reaction from the half-life? How do I calculate the order of reaction from the half-life? Okay. Try to understand what exactly I'm going to say. My dear students, for example, you have got a zero order reaction. For a zero order reaction, what is the expression to calculate half-life? A naught divided by 2k, right? For the first order reaction, half-life will be equal to 0.693 divided by k, right? For zero order reaction, for the first order reaction, correct? Now, can I say for the zero order reaction, half-life is directly proportional to initial concentration? For this first order reaction, half-life is independent of the concentration of reaction. For example, you have got nth order reaction. The reaction whose order is n. Can I simply say T half will be directly proportional to A raised power 1 minus n, where A is the initial concentration. For example, right? Check. If n value is, for example, 1, that means the reaction is first order. So 1 minus 1, 0. Anything raised power 0 is 1. So T half is independent. Absolutely correct. If n is 0, zero order. If n is 0, 1 minus 0 is 1. So T half is directly proportional to initial concentration. Absolutely. So this particular result is valid. It is valid, right? So from this particular expression, can't I write T half is equal to, it's a constant k, right? A raised power 1 minus n. Correct? Why am I giving you all this? There's a logic behind that. Just a second. People. Now, first of all, what I'll be doing from here, I'll just do one thing. I'll multiply this equation with log. It becomes log of T half will be equal to log of k plus 1 minus n log of A. This is the equation which I got. So basically what did I do? I multiplied this equation with log. It became log of m into n, which is log of m plus log of n. Then it becomes n log m, right? This is the equation which I got. So first thing, for example, I'm making a graph. Let's say I have to make a graph. The graph is between log of T half versus log of initial concentration. Log of T half versus log of initial concentration. So this is y, this is x, this is m, this is c. Y is equal to mx plus c. It's going to be a straight line like this. What about the slope of this particular graph? Slope means m, which is 1 minus n, right? And what about the intercept of this particular curve? It is just going to be log of k. So my dear students, if by chance a graph like this will be given to us, log T half versus log initial concentration of reactant, slope of this particular curve is equal to 1 minus n. From there, if slope is given, let's say slope is given to us as 3. So yeah, slope is given us as 2 or whatever. So basically 1 minus n value is given. From there you can get the n value. You can get the order. Right? Yes, A is the initial moles or initial concentration of reactant. So from this particular graph, if the slope is given to us as per the equation, then easily n value, you can calculate the order of the reaction. Correct? Now, my dear students, if you look at this particular expression, where do you use this particular expression? T half is directly proportional to initial moles or initial concentration raised power 1 minus. Now, imagine you have got a reaction like this. A gives B. I have no idea what is the order of the reaction. Order of reaction is n, for example. It is n. Okay. For example, when the initial moles or initial concentration of reactant is A1, at that point, let's say half-life of the reaction is T half 1. When the initial moles or initial concentration of reactant is kept A2, at that time, let's assume half-life of the reaction is T half 2. Okay. Now we know T half is directly proportional to initial concentration of reactant raised power 1 minus n. So can I say T half of 1 divided by T half of 2 has to be equal to A1 divided by A2 whole raised power what? Whole raised power 1 minus n. So from this particular expression, you can also get a question. And frequently you have been getting the question in JEE Mains from this particular expression. Yeah? Right? Like you'll be given with 2 half-lives, 2 initial concentrations, you'll have to get the value of n. That's all. Will you be able to solve this? Quickly. Will you be able to solve this question? I just want to know in the chats. Will you be able to solve this question? Right, people? I cannot see your chats. Just a second. Just a second. All right. So I think you should be able to do this sort of equation on your own, right? If the initial concentrations are given, A1, A2 is given, T half 1, T half 2 is given. So I believe you can use this particular result and get the value of the order of the reaction, whatever is asked, right? And most of the times, the question which will be given to you, it will be given in the format of table. It will be given in the format of table like this. I'm just showing you. It will be given, I'm showing you the format of the question. It will be given like this. For example, T half and concentration of reactant, right? If the initial concentration of reactant is A1, at that time, half-life of the reaction will be given to us. Similarly, initial concentration of reactant when kept A2, half-life of the reaction will be given to us at that time also, right? So A1, A2 will be given, T half 1, T half 2 will be given. You have to put in this expression, compare and get the value of, solve, get the value of N. Perfect. So do remove this particular thing as well. From this particular expression, questions are asked. Now, guys, there is one more topic. What is that? You must have heard about it. That is Arrhenius equation. Have you heard about Arrhenius equation? Have you heard about Arrhenius equation? Arrhenius equation. Arrhenius equation which tells you exactly what happens to rate constant of the reaction on changing the temperature. What happens to rate constant of the reaction on changing the temperature. Okay? See, guys. First of all, for example, I have got the reaction A gives B. Let's say this is the reaction A gives B. Okay? Its order is, for example, N. Its order is, for example, N. Now, for example, I'm writing rate law for this reaction. Rate is equal to rate constant, concentration of A raised power N. Now, my dear students, first of all, if concentration of reactant is kept to 1 molar, at that point of time, rate of the reaction is rate constant. So, first of all, more the rate constant of the reaction, hence more is going to be the rate of the reaction. Now, if you remember, rate constant depends on the temperature. Rate constant of a particular reaction, it depends on the temperature. And how it depends on the temperature? That is something which Arrhenius equation is going to let us know. I'm directly going to give you the expression. Rate constant of the reaction, it is directly proportional to E raised to the power minus EA divided by RT. It is directly proportional to E raised power minus EA divided by RT. If you remove the proportionality sign, it becomes a constant A, E raised power minus EA divided by RT. This is one of the forms of the Arrhenius equation. Now, guys, in this particular expression, what this K is, what this EA is, what this R is, what this T is, you should first of all know their meaning. What is K? K already you know, that is the rate constant of the reaction. What is A? A is called as pre-exponential factor. You call it either as pre-exponential factor or you call it as the frequency factor. You call it as frequency factor, right? Now, EA is something which you call as activation energy. My dear students, A and EA combinedly, they are called as Arrhenius parameter. Now, you tell me one thing. You have got a reaction which is carried out at temperature T. You have got a reaction A gives B. Assume that the reaction is carried out at temperature T. Its rate constant is K. Now, for example, if you increase the temperature of the reaction, tell me what will happen to the value of EA divided by RT? This value. If you increase the temperature, that means denominator you are increasing, this whole term will decrease. If this term is decreasing, that means minus times EA by RT. This whole term now will be increased. If this whole term is increasing, what does that mean? That means E raised power minus EA divided by RT. This whole term will be also increased. If this term is increasing, this whole term is increasing, which eventually says that K is increasing. So basically what is happening? We are increasing the temperature of the reaction, and on increasing the temperature, what is happening to the rate constant? Rate constant of the reaction is increasing. That's your Arrhenius equation. So Arrhenius equation says that on increasing the temperature, what happens to the rate constant of the reaction? Rate constant of the reaction increases. And do remember, in case of reversible reactions, upon increasing the temperature, rate constant of forward as well as rate constant of backward, both the things will increase. In case of reversible reaction, upon increasing the temperature, rate constant of forward as well as rate constant of backward reaction, both the things will increase. Point number one. Point number two, we got to know Arrhenius equation. K is equal to AE raised power minus EA by RT. Correct? Okay. K is equal to AE raised power minus EA by RT. So basically you got to know on increasing the temperature, rate constant of the reaction increases. And if rate constant increases, that means rate of reaction automatically increases. Right? Rate of reaction automatically increases. Now, my dear students, there are few more things. There are few more things which I want to discuss with you. For example, you have got a reversible reaction. You have got a reaction like this. A, for example, in equilibrium with B. Rate constant of the forward reaction, for example, that's Kf. Rate constant of the backward reaction, that's Kb. Okay. We got to know on increasing the temperature, rate constant of reaction increases, be it forward, be it backward. If you increase the temperature, rate constant of forward as well as rate constant of backward reaction, both the things increase. Okay. Now there is something which I want to share with you. My dear students, I'm going to write one equation. The equation is like this. Van 't Hoff equation you would have somewhere seen. Log of K2 divided by K1 is equal to delta H divided by 2.303 R. This is 1 divided by T1, or let me write it like this. This is T2 minus T1 divided by T1, T2. Well, I have taught this equation in the Le-Chatelier principle as well, if you remember, right? This particular equation. Why am I writing this equation? Because it's going to let me know about certain important things. It is going to give me certain important things. Imagine this is the reaction which we have, okay? So first of all, I'm assuming this particular reaction. It's equilibrium constant. K1, this particular reaction, its equilibrium constant is K1 when the reaction is carried out at temperature T1. When this particular reaction is carried at temperature T1, its equilibrium constant is K1. This is something which I'm assuming, right? Similarly, its equilibrium constant, for example, is K2 when the temperature of the reaction is T2. When the reaction is carried out at temperature T1, its equilibrium constant is K1. When the reaction is carried out at temperature T2, its equilibrium constant is K2. Now, in general, if I ask you what is equilibrium constant? Equilibrium constant is nothing. It is rate constant of forward divided by rate constant of backward reaction. Something which you already must be knowing. Correct? Now, guys, here the points are. What are the points? See, what are the important points? Imagine that this particular reaction is endothermic. Imagine that this particular reaction is endothermic in nature. If this particular reaction is endothermic in nature, that means its delta H has to be positive. Its delta H has to be positive. Imagine that this particular reaction is endothermic, so its delta H, it has to be positive, right? Now guys, understand. Delta H for the reaction is positive. I'm assuming that. Okay. Now, for example, you're increasing the temperature of the reaction. You're increasing the temperature of the reaction. If you're increasing the temperature of the reaction, then T2 minus T1 value, final temperature minus initial temperature, will come out to be positive. So T2 minus T1, it will come out to be positive. This value was already positive. Now this value is also coming out to be positive. So positive and positive makes it positive. That means log of K2 divided by K1, it is coming out to be positive. When is the log of x positive? When x is greater than 1. That means k2 divided by k1 here has to be greater than 1. Okay. What does that mean? K2 divided by k1 has to be greater than 1. That means k2 value has to be greater than k1. What is k2? K2 is the equilibrium constant at temperature T2. K1 is the equilibrium constant at temperature T1. So what it means? It means when we increase the temperature, equilibrium constant increased automatically. So do remember, for an endothermic reaction, equilibrium constant is directly proportional to temperature. But this is valid for endothermic reactions. Now comes the point. What is equilibrium constant basically? It is equal to rate constant of forward reaction divided by rate constant of backward reaction. Now you got to know that on increasing the temperature, equilibrium constant increases. On increasing the temperature, equilibrium constant increases. Does that mean Kf increases and Kb decreases? Does that mean Kf increases and Kb decreases? No. Why is that? I've already told you, on increasing the temperature, rate constant of forward and backward reaction both increases. That's something which is already discussed. On increasing the temperature, this term increases, even this term increases. If this is increasing, this is increasing, then how this particular term will increase? This particular term will increase only on increasing the temperature. Equilibrium constant will increase only if the increase in the value of Kf will be greater than that of increase in the value of Kb. Do remove this particular point. This is important, which I wanted to share with you. Okay, this is important, which I wanted to share with you. Right? Okay. So do remember, when it comes to endothermic reactions, in case of endothermic reactions, conclusions which you have to remember. In case of endothermic reactions, upon increasing the temperature, equilibrium constant increases. And upon increasing the temperature, rate constant of forward as well as backward reaction increases. Right? Which is possible only if the rate constant of forward reaction increases by larger amount as that of increase in the value of Kb. Yes, this is one important point which you have to remember. And similarly, you can check for exothermic reactions as well, right? Same procedure, you can check for exothermic reactions as well. For example, let me teach you for exothermic reactions, then automatically all these things will go into your head properly. See, for example, you have got the reaction A gives B. Rate constant of forward reaction is Kf, rate constant of backward reaction is Kb, correct? Let's assume K1 represents the equilibrium constant of the reaction at temperature T1. K2 represents the equilibrium constant of the reaction at temperature T2. Okay, right? And already we know what is equilibrium constant. Equilibrium constant is nothing. It is just the ratio of rate constant of forward and that of backward reaction. It is the ratio of the two. Now, try to understand. For example, assume that this particular reaction is exothermic. If this particular reaction is exothermic in nature, what does that mean? That means delta H value has to be negative. Delta H has to be negative, right? If reaction is exothermic, means delta H is negative. Delta H is negative. Now, imagine that you are increasing the temperature of the reaction. If you increase the temperature of the reaction, therefore T2 minus T1 value will come out to be positive. If you increase the temperature of the reaction, T2 minus T1 is coming out to be positive. T2 minus T1 is positive. This term is negative. So positive negative makes it negative. That means the log of K2 by K1 is negative. That means the log of K2 divided by K1 is what? It is negative. Which is possible only if K2 divided by K1 value will be less than 1. Which is possible only if K2 is less than K1. What can you conclude from here? Check it out. You can conclude one thing. That on increasing the temperature, equilibrium constant, is it increasing or decreasing? It is decreasing. So, in case of exothermic reactions, what do you have to remember? In case of exothermic reaction, equilibrium constant is inversely proportional to temperature. Right? Sorry. In case of exothermic reactions, equilibrium constant, that is inversely proportional to temperature. Right? Now, what does it mean? It means when you increase the temperature, what happens to equilibrium constant? Equilibrium constant decreases. But equilibrium constant is basically Kf by Kb, right? Equilibrium constant is basically Kf by Kb, right? On increasing the temperature, equilibrium constant decreases. Does that mean this value decreases and this value increases? Then only Keq will decrease? No, that's not the case here. See, on increasing the temperature, rate constant of forward as well as backward reaction increase. If this is increasing as well as this is increasing, and Keq has to decrease. How Keq will decrease? KEQ will decrease only if increase in the value of KB will be more than that of increase in the value of KF. This is the point which I want you guys to remember. Yes. Perfect. I hope this point is clear. Is this point clear to you? Right? So there are few things which you have to remember. In case of exothermic reactions, on increasing the temperature, equilibrium constant will decrease, right? And at the same time, increase in the value of Kb will be more than that of increase in the value of Kf. Why is that? Why is it happening? There is one more logic behind that. That is activation energy. I'm not going into that logic, etc., right? Leave that part aside. That's the graphical reason. Okay, I'm leaving that part aside. You just have to remember these points which I told you right now. Now, guys, I'm going back to the Arrhenius equation. What is Arrhenius equation? K is equal to A e raised power minus EA by RT. Perfect. This is one of the forms of Arrhenius equation. Are there some other forms of Arrhenius equation too? Yes, there are some other forms of Arrhenius equation too. My dear students, for example, I'm multiplying this equation with ln. It becomes ln of K is equal to ln of A multiplied by e raised power minus EA by RT. Right? So it becomes ln of K is equal to ln of m into n is ln of m plus ln of e raised power minus EA by RT. Perfect. Or you can write it like this. Ln of K is equal to ln of A. Ln of m raised power n is n ln m. So minus EA divided by RT will come to the front. Then ln E is 1. So this is one more equation. This is one more form of Arrhenius equation. Minus EA divided by RT type. Right? Similarly, you can convert it into the logarithmic form as well. You can write log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 by T. This is one more form of this particular equation. These are different forms of Arrhenius equation which can be asked. Right? Yes, Anish, that's enough. That's more than sufficient. This is the first form of Arrhenius equation. This is the second form of Arrhenius equation. And this is the third form of Arrhenius equation. Right? Now, my dear students, there is one more thing which you have to remember about Arrhenius equation. What is that? One more form. Have a look. Guys. For example, you have got a reaction A gives B. Right? At temperature T1, assume that its rate constant is K1. At temperature T2, assume that its rate constant is, for example, K2. I'm assuming things. At temperature T1, rate constant K1. Temperature T2, rate constant is K2. Okay? Now, my dear students, if I introduce this particular condition into this equation, what do I get? I'll be getting log of K1 is equal to log of A minus EA divided by 2.303 R. Now it's going to be 1 divided by T1. Correct? Now what I'm going to do, I'm going to introduce this condition into the same equation. It is going to be log of K2 is equal to log of A minus EA divided by 2.303 R multiplied by 1 upon T2. Correct? If I do, for example, log of K2 minus log of K1, log of K2 minus log of K1 will eventually be log of K2 divided by K1. Right? Subtracting log of K2 minus log of K1. Log of A gets cancelled out. So my final equation becomes something like this. EA divided by 2.303 R, it's going to be 1 upon T1 minus 1 upon T2. This is one more form of the Arrhenius equation from which the questions can be asked. One more form of Arrhenius equation from which the questions can be asked. Right? From which the questions can be asked. Right, guys? Is it clear? Is it clear to everyone? This is one more form. This is the fourth form. Now there are different forms. There can be different graphs as well based on Arrhenius equation. The first graph will be something like this. I'm writing ln of K versus 1 by T. What do you think ln of K versus 1 by T graph will look like? See, the equation is ln of K is equal to ln of A minus EA divided by R multiplied by 1 by T. Correct? This is the equation. right? Now, ln of k you are plotting along y-axis, 1 by t you are plotting along x-axis. So this has to be your m, the sign is minus, and this is c. Y is equal to minus mx plus c. The graph is like this. What about the slope of this curve? Slope of this curve is equal to minus EA divided by R. What about the intercept? Intercept is C basically, and C is nothing, that's ln of A. Correct? This is the first graph. This is the first graph. Second graph. For example, you have to plot a graph between log of K, log of rate constant versus 1 by T. Again, which equation you'll be using? You'll be using this equation. Log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 upon T. Now, log K you are plotting along y-axis, 1 by T you are plotting along x-axis. This is your M, the sign is minus, and this term is equal to C. So y is equal to minus mx plus C. Graph is again like this. What about the slope of this graph? Slope of this graph will be simply minus EA divided by 2.303 R, and intercept of this particular graph has to be log of A. It has to be log of K. So these are the two graphs which you have to remember. That's all. Now, how many different types of questions can be asked? Let's have a look. Let's have a look how many different types of questions can be asked. Or before solving the questions, let me tell you just one more important thing. Just a second. One more important point. Do remember, on increasing the temperature by 10 degree or 10 Kelvin, for example. If you increase the temperature of the reaction by 10 degree, what happens to a rate? Rate of the reaction doubles. Rate of the reaction doubles, or even becomes more, or becomes even more, or becomes even more. When you basically increase the temperature of the reaction by 10 degree, or you can say by 10 Kelvin, do remember, the rate of the reaction, it doubles. It is basically the rate constant which doubles, or even becomes more. Eventually, rate of reaction increases. So my point here is, for example, you have got the reaction A gives B. You have got the reaction which is A gives B. When the reaction was carried out at temperature T Kelvin, for example, its rate constant was, for example, K. Its rate constant was, for example, K. Now I'm increasing the temperature by Kelvin. I'm increasing the temperature by 10 Kelvin. Now the temperature of the reaction is T plus 10 Kelvin. Now the rate constant would have doubled or even becomes more. Let's say the new rate constant of the reaction is now 2 times K. Is now 2 times K. My dear students, I'm defining a term, temperature coefficient, which I'm representing with N. Temperature coefficient. Temperature coefficient is nothing. It is the rate constant of the reaction. It is the rate constant of the reaction at temperature T plus 10 Kelvin divided by rate constant of the reaction at temperature T Kelvin. At temperature T Kelvin. See, this particular term is 2 times K. This particular term is K. So K cancelled, the value came out to be 2. So temperature coefficient of majority of the reactions, what you'll observe temperature coefficient of majority of the reactions will be 2. Right? But I told you, when you increase the temperature by 10 degree or 10 Kelvin, rate constant doubles or even becomes more. Over here, I've exactly considered that rate constant is doubling. It can be 2.1 also. It can be 2.2 also. Right? If it is 2.1 K, then the N value will be 2.1. If it is 2.2, N value is 2.2. So in general, N value, it is greater or equal to 2, but it is less than 3. Temperature coefficient value, it is greater or equal to less than 3. Right? Okay, do remove this particular thing. This N is something which you call as temperature coefficient. This is called as temperature coefficient. Okay, right? Now, guys, one more thing which can be asked. One more thing which can be asked. For example, you have got the reaction like this. A gives B. A gives B. Okay, A gives B. At temperature T1, assume that the rate of reaction is R1. At temperature T2, assume that the rate of reaction is R2. Right? At temperature T1, when the reaction is carried out at temperature T1, the rate of reaction is R1. When the reaction is carried out at temperature T2, the rate of reaction is R2. Now do remember, R2 divided by R1 is equal to, it will be 2 raised power T2 minus T1 divided by 10. This is one more expression from which question can be asked. One more expression from which question can be asked. For example, I'm giving you a question like this. Let's say the reaction is A gives B. The temperature of the reaction is, for example, 10 degrees centigrade, right? The temperature of the reaction is 10 degrees centigrade. Now you are increasing the temperature from 10 degree to 100 degrees centigrade. I'm asking you how many times rate of reaction has increased. You're increasing the temperature. On increasing the temperature, rate constant increases. Eventually, rate of reaction increases, right? So this is temperature T1, this is temperature T2. Let's assume at temperature T1, the rate was R1. At temperature T2, the rate is R2. So what you'll write? R2 divided by R1 is equal to 2 raised power. T2 minus T1, that's 90. 90 divided by 10 is 9. So new rate of the reaction will be equal to raised power 9 times the earlier rate of the reaction. I would say rate of the reaction has increased by this much of amount. Right? Okay. Perfect. Do remember this particular expression as well. So this particular expression is going to let you know upon increasing the temperature how many times rate of reaction will increase. That's all. How many times the rate of reaction will increase. Yeah. Right, guys? Look at this particular question. Look at this particular question. The question is calculate the activation energy of the reaction. Graph is given. Graph is given. Activation energy is to be calculated. Graph is between log K versus 1 by T. If you remember, few minutes back only I told you what is the slope of log K versus 1 by T. It used to be, I believe, minus EA divided by 2.303 R. Right? And what is the slope of this curve? Slope of this curve is tan of theta. We are given theta is equal to tan inverse minus 3. What does that mean? That means tan theta is equal to minus 3. Slope is basically tan of theta, which is minus EA divided by 2.303 R. Right? Tan of theta value will be equal to minus 3. So minus 3 is equal to minus EA divided by 2.303 R, or you can say EA will be equal to 6.909 R. EA, activation energy, is equal to 6.909 R. Now, the first question says, calculate the activation energy in kilojoules per mole, right? So, EA will be equal to 6.909 multiplied by R value I'll be using as 8.314 joules per Kelvin per mole. Since I'm using the R value in joules, so the whole term right now is going to be in joules, but I have to get in kilojoules. Divide by 1002, the answer you'll be getting in kilojoules. The second question, get the answer in kilocalories per mole. Activation energy has to be equal to 6.909, right? R value you'll be writing as 2 calories per Kelvin per mole. This whole term right now will be in calories. Now divide by 1000. Now this answer is going to be in kilocalories, right? So both equations are done and dusted. It is just by looking at the slope you solve the equation. By looking at the slope you solve the equation. Simple. Yeah. Look at this particular equation. The rate constant of the reaction at this temperature and this temperature are this and this. Calculate the activation energy. Isn't it simple? The rate constant of the reaction at temperature T1. T1 temperature. This is T1, this is T2. But convert them into Kelvin. T1, T2 is given. K1, K2 is also given. T1, T2 is given. K1, K2 is given. Calculate the activation energy. Isn't it simple? T1, T2 is given, right? And K1, K2 is also given. R value already you know 8.314. One equation, one unknown. So activation energy you can calculate easily, right? This is simple formula based equation. Nothing else. Nothing to do here. Nothing to do here. Nothing to do here. Nothing to do here. There was one question asked long back. I don't exactly remember the question, but the question was something like this. The correct form of Arrhenius equation among the following is. The correct form of Arrhenius equation among the following is. Just a second. There were few options which were given. First option was d upon dt of ln of k is equal to EA divided by RT square. Is equal to EA divided by RT square. This was the first option. Second option was integral of d upon dt of ln of k is equal to minus EA divided by RT square. Like this, a lot of options were given basically, right? Like this, a lot of options were given. Now, my dear students, how do we get the correct answer? See, Arrhenius equation is what? One of the forms is ln of k is equal to ln of A minus EA divided by RT, right? Now, what you are doing in all the things basically, you are differentiating with respect to temperature. So, differentiate with respect to temperature. So, d upon dt of what? D upon dt of ln of k. You are differentiating with respect to temperature. It's a constant, its differentiation is 0. Now, differentiation of 1 by t is minus 1 upon t square. Minus comes to the front. So, it simply becomes EA upon RT square. So, this is one more form of the Arrhenius equation, which was asked long back in the questions, right? I just differentiated the Arrhenius equation with respect to temperature and got the result, right? Clear? Clear, people? Okay, so this was your Arrhenius equation. There is one topic left, that is collision theory, but I don't think I'll be able to take collision theory now. I'll be posting a recording on collision theory. Okay, that will be like half an hour concept, half an hour topic. I'll be posting the recording soon. Right? So one topic is left here, that is collision theory, half an hour topic that is. You can, if anyways, you can do that from NCERT as well. If not, I'll be providing you one recording of that particular topic. And with that, the chapter is over. Okay? Perfect. So with this, this kinetics chapter is done and dusted also. Yes, I mean, after reading all these lectures, just go through your NCERT once, right? Just read NCERT once for kinetics, that's sufficient. Perfect, guys. So with this, I'll be taking a leave then. Okay. So our one more chapter is done and dusted. That is chemical kinetics, right? So day after tomorrow, what we shall be doing? We shall be doing IUPAC nomenclature, right? And tomorrow there is an amazing surprise coming up for all of you. Do join that session at 10 p.m. tomorrow. You are getting something interesting. Yeah? Hello. I'll be taking a leave with this. Take care. God bless you all. And bye, guys. Bye.
Unacademy. Let's crack it.